Prefatory Material of the Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marwalk. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. In Memoriam. The future is not free. The story of all human progress is one of a struggle against all odds. We learned again that this America, which Abraham Lincoln called the last best hope of man on earth, was built on heroism and noble sacrifice. It was built by men and women like our 7-star voyagers, who answered a call beyond duty, who gave more than was expected or required, and who gave it little thought of worldly reward. President Ronald Reagan, January 31, 1986. Francis R. Dick Scobie, Commander. Michael John Smith, Pilot. Ellison S. Onizuka, Mission Specialist 1. Judith Arlene Resnick, Mission Specialist 2. Ronald Irwin McNair, Mission Specialist 3. S. Krista McAuliffe, Payload Specialist 1. Gregory Bruce Jarvis, Payload Specialist 2. Letter of Committal. Presidential Commission on the Space Shuttle Challenger Accident, June 6, 1986. Dear Mr. President, on behalf of the Commission, it is my privilege to present the report of the Presidential Commission on the Space Shuttle Challenger Accident. Since being sworn in on February 6, 1986, the Commission has been able to conduct a comprehensive investigation of the Challenger accident. This report documents our findings and makes recommendations for your consideration. Our objective has been not only to prevent any recurrence of the failure related to this accident, but to the extent possible to reduce other risks in future flights. However, the Commission did not construe its mandate to require a detailed evaluation of the entire shuttle system. It fully recognizes that the risk associated with spaceflight cannot be totally eliminated. Each member of the Commission shared the pain and anguish the nation felt at the loss of 7 brave Americans in the Challenger accident on January 28, 1986. The nation's task now is to move ahead to return to safe spaceflight and to its recognized position of leadership in space. There could be no more fitting tribute to the Challenger crew than to do so. Sincerely, William P. Rogers, Chairman. Signed, William P. Rogers, Chairman, Maryland. Neil A. Armstrong, Vice Chairman, Ohio. David C. Atchison, District of Columbia. Eugene E. Covert, Massachusetts. Richard P. Feynman, California. Robert B. Hotz, Maryland. Donald J. Coutinho, Illinois. Sally K. Ride, California. Robert W. Rummel, Arizona. Joseph F. Sutter, Washington. Arthur B. C. Walker, Jr., California. Albert D. Whelan, California. Charles E. Yeager, California. Preface. The accident of Space Shuttle Challenger Mission 51-L, interrupting for a time one of the most productive engineering, scientific, and exploratory programs in history, evoked a wide range of deeply felt public responses. There was grief and sadness for the loss of 7 brave members of the crew, firm national resolve that those men and women be forever enshrined in the annals of American heroes, and a determination based on that resolve, and in their memory, to strengthen the Space Shuttle program so that this tragic event will become a milestone on the way to achieving the full potential that space offers to mankind. The President, who was moved and troubled by this accident in a very personal way, appointed an independent commission made up of persons not connected with the mission to investigate it. The mandate of the commission was to 1. Review the circumstances surrounding the accident to establish the probable cause or causes of the accident, and 2. Develop recommendations for corrective or other action based upon the Commission's findings and determinations. Immediately after being appointed, the Commission moved forward with its investigation, and with the full support of the White House, held public hearings dealing with the facts leading up to the accident. In a closed society, other options are available. In an open society, unless classified matters are involved, other options are not, either as matter of law or as a practical matter. In this case, a vigorous investigation and full disclosure of the facts were necessary. The way to deal with a failure of this magnitude is to disclose all the facts fully and openly, to take immediate steps to correct mistakes that led to the failure, and to continue the program with renewed confidence and determination. The Commission construed its mandate somewhat broadly, to include recommendations on safety matters not necessarily involved in this accident, but which require attention to make future flights safer. Careful attention was given to concerns expressed by astronauts because the Space Shuttle program will only succeed if the highly qualified men and women who fly the shuttle have confidence in the system. However, the Commission did not construe its mandate to require a detailed investigation of all aspects of the Space Shuttle program, to review budgetary matters, or to interfere or supersede Congress in any way in the performance of its duties. Rather, the Commission focused its attention on the safety aspects of future flights, based on the lessons learned from the investigation, with the objective being to return to safe flight. Congress recognized the desirability, in the first instance, of having a single investigation of this national tragedy. It very responsibly agreed to await the Commission's findings before deciding what further action might be necessary to carry out its responsibilities. For the first several days after the accident, possibly because of the trauma resulting from the accident, NASA appeared to be withholding information about the accident from the public. After the Commission began its work, and at its suggestion, NASA began releasing a great deal of information that helped to reassure the public that all aspects of the accident were being investigated and that the full story was being told in an orderly and thorough manner. Following the suggestion of the Commission, NASA established several teams of persons not involved in the Mission 51-L launch process to support the Commission and its panels. These NASA teams have cooperated with the Commission in every aspect of its work. The result has been a comprehensive and complete investigation. The Commission believes that its investigation and report have been responsive to the request of the President, and hopes that they will serve the best interest of the nation in restoring the United States space program to its preeminent position in the world. End of Prefatory Material. Recording by Marwalk.
Section 1 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in January 2021. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 1. Introduction. The Space Shuttle concept had its genesis in the 1960s, when the Apollo lunar landing spacecraft was in full development but had not yet flown. From the earliest days of the space program, it seemed logical that the goal of frequent, economical access to space might best be served by a reusable launch system. In February 1967, the President's Science Advisory Committee lent weight to the idea of a reusable spacecraft by recommending that studies be made of more economical ferrying systems, presumably involving partial or total recovery and use. In September 1969, 2 months after the initial lunar landing, a space task group, chaired by the Vice President, offered a choice of 3 long-range plans. A $8 to $10 billion per year program involving a manned Mars expedition, a space station in lunar orbit, and a 50-person Earth-orbiting station serviced by a reusable ferry or space shuttle. An intermediate program costing less than $8 billion annually that would include the Mars mission. A relatively modest $4 to $5.7 billion a year program that would embrace an Earth-orbiting space station and the space shuttle as its link to Earth. In March 1970, President Nixon made it clear that, while he favored a continuing active space program, funding on the order of Apollo was not in the cards. He opted for the shuttle-tended space base as a long-range goal, but deferred going ahead with the space station pending development of the shuttle vehicle. Thus, the reusable space shuttle, earlier considered only the transport element of a broad, multi-objective space plan, became the focus of NASA's near-term future. The Space Shuttle Design. The embryo shuttle program faced a number of evolutionary design changes before it would become a system in being. The first design was based on a fly-back concept in which 2 stages, each manned, would fly back to a horizontal, airplane-like landing. The first stage was a huge, winged, rocket-powered vehicle that would carry the smaller second stage piggyback. The carrier would provide the thrust for liftoff and flight through the atmosphere, then release its passenger, the orbiting vehicle, and return to Earth. The orbiter, containing the crew and payload, would continue into space under its own rocket power, complete its mission, and then fly back to Earth. The second stage craft, conceived prior to 1970 as a space station ferry, was a vehicle considerably larger than the later Space Shuttle orbiter. It carried its rocket propellants internally, had a flight deck sufficiently large to seat 12 space station-bound passengers, and a cargo bay big enough to accommodate space station modules. The orbiter's size put enormous weightlifting and thrust-generating demands on the first stage design. This 2-stage, fully reusable design represented the optimum space shuttle in terms of routine, economical access to space, the catchphrase that was becoming the primary guideline for development of Earth-to-orbit systems. It was, however, less than optimum in terms of the development investment required, an estimated $10 to $13 billion, a figure that met with disfavor in both Congress and the Office of Management and Budget. In 1971, NASA went back to the drawing board, aware that development cost rather than system capability would probably be the determining factor in getting a green light for shuttle development. Government and industry studies sought developmental economies in the configuration. One proposal found acceptance: eliminate the orbiter's internal tanks and carry the propellant in a single, disposable external tank. It provided a smaller, cheaper orbiter without substantial performance loss. For the launch system, NASA examined a number of possibilities. One was a winged but unmanned recoverable liquid fuel vehicle based on the eminently successful Saturn V rocket from the Apollo program. Other plans envisioned simpler but also recoverable liquid fuel systems, expendable solid rockets, and the reusable solid rocket booster. NASA had been using solid fuel vehicles for launching some small unmanned spacecraft, but solids as boosters for manned flight was a technology new to the agency. Mercury, Gemini, and Apollo astronauts had all been rocketed into space by liquid fuel systems. Nonetheless, the recoverable solid rocket booster won the nod, even though the liquid rocket offered potentially lower operating costs. The overriding reason was that pricing estimates indicated a lower cost of development for the solid booster. Emerging from this round of design decision-making was the Space Shuttle, a 3-element system composed of the orbiter, an expendable external fuel tank carrying liquid propellants for the orbiter's engines, and 2 recoverable solid rocket boosters. It would cost, NASA estimated early in 1972, $6.2 billion to develop and test a 5-orbiter space shuttle system, about half what the 2-stage fly-back design would have cost. To achieve that reduction, NASA had to accept somewhat lighter system operating costs and sacrifice full reusability. The compromise design retained recoverability and reuse of 2 of the 3 elements and still promised to trim substantially the cost of delivering payloads to orbit. The final configuration was selected in March 1972. The Space Shuttle development. In August 1972, NASA awarded a contract to Rockwell International Corporation's Space Transportation Systems Division for design and development of the Space Shuttle orbiter. Martin Marietta Denver Aerospace was assigned development and fabrication of the external tank. Morton Thiokol Corporation was awarded the contract for the solid rocket boosters, and Rocketdyne, a division of Rockwell, was selected to develop the orbiter main engines. NASA divided managerial responsibility for the program among 3 of its field centers. Johnson Space Center, Houston, Texas, was assigned management of the orbiter. Marshall Space Flight Center, Huntsville, Alabama, was made responsible for the orbiter's main engines, the external tank, and the solid rocket boosters. Kennedy Space Center, Merritt Island, Florida, was given the job of assembling the Space Shuttle components, checking them out, and conducting launches. Because these 3 centers will be mentioned repeatedly in this report, they will hereafter be identified simply as Johnson, Marshall, and Kennedy. It was in an increasingly austere fiscal environment that NASA struggled through the shuttle development years of the 1970s. The planned 5-orbiter fleet was reduced to 4. Budgetary difficulties were compounded by engineering problems and, inevitably in a major new system whose development pushes the frontiers of technology, there was cost growth. This combination of factors induced schedule slippage. The initial orbital test flights were delayed by more than 2 years. The first shuttle test flights were conducted at Dryden Flight Research Facility, California, in 1977. The test craft was the Orbiter Enterprise, a full-size vehicle that lacked engines and other systems needed for orbital flight. The purpose of these tests was to check out the aerodynamic and flight control characteristics of the orbiter in atmospheric flight. Mounted piggyback atop a modified Boeing 747, the Enterprise was carried to altitude and released for a gliding approach and landing at the Mojave Desert Test Center. 5 such flights were made. They served to validate the orbiter's computers and other systems. They also demonstrated the craft's subsonic handling qualities, in particular its performance in the precise unpowered landings that would be required on all shuttle flights. The Enterprise test flights were followed in 1977 to 80 by extensive ground tests of shuttle systems, including vibration tests of the entire assembly, orbiter, external tank, and solid rocket boosters, at Marshall. Main engine test firings were conducted at National Space Technology Laboratories at Bay St. Louis, Mississippi, and on the launch pad at Kennedy. By early 1981, the Space Shuttle was ready for an orbital flight test program. This was carefully crafted to include more than 1,000 tests and data collection procedures. All flights were to be launched from Kennedy and terminate at Edwards Air Force Base, where the Dryden Flight Research Facility is located. Actually, the 3rd flight landed at White Sands Test Facility, New Mexico, because the normally dry lake bed at Edwards was flooded. Originally intended as 6-mission program, the orbital test series was reduced to 4 flights. STS-1, Space Transportation System 1, April 12 to 14, 1981, Orbiter Columbia, was a 2-day demonstration of the orbiter's ability to go into orbit and return safely. Its main payload was a flight instrumentation pallet containing equipment for recording temperatures, pressures, and acceleration levels at various points around the orbiter. In addition, there were checkouts of the cargo bay doors, attitude control system, and orbital maneuvering system. STS-2, November 12 to 14, 1981, orbiter Columbia, marked the first test of the remote manipulator system and carried a payload of Earth survey instruments. This was the first time any spacecraft had flown twice. Failure of a fuel cell shortened the flight by about 3 days. STS-3, March 22 to 30, 1982, orbiter Columbia, was the longest of the initial test series, staying aloft 8 days. Activities included a special test of the manipulator in which the robot arm removed a package of instruments from the payload bay but did not release it into space. The flight included experiments in materials processing. STS-4, June 27 to July 4, 1982, orbiter Columbia, featured another test of the robot arm, which extended a scientific payload over the side of the payload bay, then rebirthed it. Materials processing experiments were conducted, as were a number of scientific investigations. This flight carried the first Department of Defense payload. With the landing of STS-4, the orbital flight test program came to an end, with 95% of its objectives accomplished. The interval between flights had been trimmed from 7 months to 4, then 3. NASA declared the Space Shuttle operational, a term that has encountered some criticism because it erroneously suggests that the shuttle had attained an airline-like degree of routine operation. In any event, NASA regarded all flights after STS-4 operational in the sense that payload requirements would take precedence over spacecraft testing, requiring larger crews. After completing the orbital test in mid-1982, NASA began the operational phase of the Space Shuttle program, beginning with STS-5. The STS, for Space Transportation System, sequential numbering was still in effect at that time. After STS-9, NASA changed the method of numbering missions. Thereafter, each flight was designed by 2 numbers and a letter, such as 41-B. The first digit indicates the fiscal year of the scheduled launch, 4 for 1984. The second digit identifies the launch site. 1 is Kennedy, 2 Vandenberg Air Force Base, California. The letter corresponds to the alphabetical sequence of the fiscal year, B being the second mission scheduled. Here is a brief summary of the 21 missions launched from late 1982 to January 1986. STS-5, November 11 to 16, 1982, orbiter Columbia, launched 2 communication satellites, which later were boosted to geosynchronous orbit by attached propulsion systems. STS-6, April 4 to 9, 1983, orbiter Challenger, was highlighted by the first shuttle-based spacewalk or extravehicular activity. The crew successfully deployed the 5,000-pound tracking and data relay satellite, first of 3 planned NASA communications satellites. STS-7, June 18 to 24, 1983, orbiter Challenger, delivered a second pair of commercial communications satellites. The mission also included additional payload release and recapture tests using the remote manipulator system. This flight marked the first retrieval of an object from orbit. STS-8, August 30 to September 6, 1983, orbiter Challenger, included more robot arm tests, plus deployment of a commercial public service communications satellite. STS-9, November 28 to December 8, 1983, orbiter Columbia, carried the first space lab in the payload bay. The mission marked Columbia's return to service after a year's hiatus, during which it had been extensively modified. Flight 10, 41-B, February 3 to 11, 1984, orbiter Challenger, was highlighted by the introduction of the Manned Maneuvering Unit, a backpack propulsion unit that allows astronauts to maneuver in space independent of the orbiter. The mission also launched 2 communication satellites, but their boosters failed to put them into geosynchronous orbit. For the first time, the shuttle landed on the concrete runway at Kennedy Space Center. Flight 11, 41-C, April 6 to 13, 1984, Orbiter Challenger, featured an important demonstration of shuttle ability, the retrieval, repair, and redeployment of the malfunctioning Solar Maximum mission spacecraft with the help of a manned maneuvering unit. Other activity included deployment of the Long Duration Exposer Facility, a large cylinder containing material samples to be retrieved and examined after long exposure to the space environment. Flight 12, 41-D, August 30 to September 5, 1984, Orbiter Discovery, was devoted primarily to launch of 3 communications satellites. The mission demonstrated repeated deployment and retraction of a large, foldable solar array to investigate the practicability of using such solar wings as power sources for extended shuttle missions, space platforms, or the space station. Flight 13, 41-G, October 5 to 13, 1984, Orbiter Challenger, launched the NASA Earth Radiation Budget Explorer. A cargo bay pallet carried instruments for Earth observations, including an advanced imaging radar. Flight 14, 51-A, November 8 to 16, 1984, Orbiter Discovery, launched 2 communication satellites and retrieved 2 others that had been sent into unusable orbits after deployment on Flight 10. Flight 15, 51-C, January 24 to 27, 1985, Orbiter Discovery, carried a Department of Defense payload. Flight 16, 51-D, April 12 to 19, 1985, Orbiter Discovery, deployed 2 commercial satellites. One, LiSat-3, remained in low orbit when the upper stage booster failed to activate. Flight 17, 51-B, April 29 to May 6, 1985, Orbiter Challenger, carried a second Spacelab mission and materials processing experiments. Flight 18, 51-G, June 17 to 24, 1985, Orbiter Discovery, delivered 3 communication satellites, deployed a low-cost Spartan scientific satellite, and retrieved it after a period of free flight. Flight 19, 51-F, July 29 to August 6, 1985, Orbiter Challenger, carried the third Spacelab mission, which covered a broad range of experiments in plasma physics, astrophysics, solar astronomy, and materials processing. Flight 20, 51-I, August 27 to September 3, 1985, Orbiter Discovery, deployed 3 communication satellites. The LiSat-3 satellites, which failed to activate after deployment on Flight 16, was retrieved, repaired, and successfully redeployed. Flight 21, 51-J, October 3 to 10, 1985, Orbiter Atlantis, was devoted to another Department of Defense mission. Flight 22, 61-A, October 30 to November 6, 1985, Orbiter Challenger, carried the fourth Spacelab mission, devoted to materials processing experimentation. Flight 23, 61-B, November 26 to December 3, 1985, Orbiter Atlantis, was highlighted by an experiment in astronaut assembly of structures in orbit and attendant study of extravehicular dynamics and human factors. The mission also deployed 3 communication satellites. Flight 24, 61-C, January 12 to 18, 1986, Orbiter Columbia, launched a commercial communication satellite, deployed a hitchhiker secondary payload, conducted experiments in infrared imaging, acquired photos and spectral images of comet Halley. Flight 25, 51-L, January 28, 1986, Orbiter Challenger. The accident. Including the initial orbital tests, the Space Shuttle flew 24 successful missions over a 57-month period. Columbia made 7 trips into space, Discovery 6, and Atlantis 2. Challenger flew most frequently, 9 times prior to its fateful last flight. In those 24 flights, the shuttle demonstrated its ability to deliver a wide variety of payloads, its ability to serve as an orbital laboratory, its utility as a platform for erection of large structures, and its use for retrieval and repair of orbiting satellites. Elements of the Space Shuttle. The Space Shuttle is the principal component of a national space transportation system designed to accommodate not only NASA's predictable needs, but also those of the Department of Defense and commercial payload sponsors. Technically speaking, transportation system hardware embraces not only the shuttle, but its Space Lab laboratory component, the upper stage propulsion units, contemplated heavy lift vehicles, and space tugs for moving payloads from one orbit to another. To provide for the broadest possible spectrum of civil/military missions, the Space Shuttle was designed to deliver 65,000 pounds of payload to an easterly low Earth orbit or 32,000 pounds to a polar orbit. The following sections describe the main elements of the shuttle system. The orbiter. The orbiter is as large as a mid-size airline transport and has a structure like that of an aircraft, an aluminum alloy skin stiffened with stringers to form a shell over frames and bulkheads of aluminum or aluminum alloy. The major structural sections of the orbiter are the forward fuselage, which encompasses the pressurized crew compartment, the mid-fuselage, which contains the payload bay doors, the aft fuselage, from which the main engine nozzles project, and the vertical tail, which splits open along the trailing edge to provide a speed brake used during entry and landing. The crew compartment is divided into 2 levels, the flight deck on top and the mid-deck below. Besides working space, the crew compartment contains the systems needed to provide a habitable environment, atmosphere, temperature, food, water, the crew sleep facilities, and waste management. It also houses the electronic, guidance, and navigation systems. The orbiter crew may include as many as 8 people, although generally the limit is 7. The crew consists of the commander, the captain of the ship, the pilot, second in command, and 2 or more mission specialists. 1 or more payload specialists can also be accommodated. A mission specialist coordinates activities of the orbiter and crew in support of a given payload objective. A payload specialist may manage specific experiments. The commander, pilot, and mission specialists are career astronauts assigned to the mission by NASA. Payload specialists do not come from the astronaut office. They are assigned by payload sponsors in coordination with NASA. Cargoes up to 24 tons have been carried in the payload bay. Clamshell doors on the top of the orbiter meet along the craft's spine to enclose the bay, which is 15 feet wide and 60 feet long. The payload bay is designed to hold securely a wide range of objects. They may include 1 or more communication satellites to be launched from orbit, an autonomous space lab for experiments in space, or cargo disposed on special pallets. To handle cargo in orbital flight, the payload bay has the 50-foot mechanical arm that is controlled from within the crew compartment. A television camera and lights mounted near the end of the arm enable the operator to see what the hand is doing. Just as important as delivering cargo to orbit is recovering a satellite and bringing it back to Earth, retrieving a satellite in need of refurbishment, for example. The orbiter can carry 16 tons of cargo back from space. The feasibility of a reusable space shuttle hinges on a particularly vital requirement: protecting the orbiter from the searing heat generated by friction with the atmosphere when the craft returns to Earth. Temperatures during entry may rise as high as 2,750 degrees Fahrenheit on the landing edge of the wing and 600 degrees on the upper fuselage, the coolest area. The thermal protection system devised for the orbiter must prevent the temperature of the aluminum skin from rising above 350 degrees during either ascent or entry. The orbiter has 4 kinds of external insulation that are applied to various parts of the structure according to the temperature each is likely to experience. The craft's nose cap and the leading edges of the wings are protected with an all-carbon composite, consisting of layers of graphite cloth in a carbon matrix. The outer layers are converted chemically to silicon carbide, the same material that has long been used as an abrasive in grindstones. Areas subjected to the next greatest heat are shielded with high-temperature ceramic tiles about 6 inches square and varying in thickness from 1 to 5 inches, depending on the protection needed. So-called low-temperature tiles are of the same material, nearly pure glass, of which 90% of the volume is air, for use on areas requiring less protection. Low temperature is relative. Tiles so designated can withstand a temperature of 1,200 degrees Fahrenheit. About 30,000 tiles, each different, are installed on each orbiter. Space Shuttle main engines. The 3 high-performance rocket engines in the aft section of the orbiter fire for about the first 8.5 minutes of flight after liftoff. At sea level, each engine generates 375,000 pounds of thrust at 100% throttle. The propellants for the engines are the fuel, liquid hydrogen, and the oxidizer, liquid oxygen, carried in the external tank. Combustion takes place in 2 stages. First, the propellants are mixed and partly burned in pre-burners. Hot gases from the pre-burners drive the high-pressure turbopumps which deliver propellants to the main injector. Combustion, once initiated by electrical igniters, is self-sustaining. Before firing, the very cold liquid propellant is allowed to flow into the system as far as the pre-burners and combustion chamber to cool the pumps and ducts so that the hydrogen and oxygen in the system will remain liquid when the engine is started. The main engines have been throttled over a range of 65 to 104% of the thrust at sea level. At liftoff, they are thrusting at 100%. Computers command engine thrust to 104% as soon as the shuttle clears the tower. They throttle to 65% to reduce the maximum aerodynamic loads that occur at an altitude of about 34,000 feet. Thereafter, the thrust is again increased to provide an acceleration of 3 times that of gravity in the last minute or so of powered flight. External tank. The external tank carries the propellants for the orbiter's main engines, 143,000 gallons of liquid oxygen and 383,000 gallons of liquid hydrogen, which is much lighter than a comparable volume of oxygen. Together, the propellants weigh a little more than 790 tons. Martin Marietta Denver Aerospace, Michaud, Louisiana, builds the tank, a welded aluminum alloy cylinder with an ogive nose and a hemispherical tail. It is 154 feet long and 27.5 feet in diameter. Because the orbiter and the 2 solid rocket boosters are attached to it at liftoff, the external tank absorbs the thrust of the combined propulsion system. It withstands complex load effects and pressures from the propellants. The liquid oxygen tank forms the nose of the external tank. It contains oxidizer kept liquid at a temperature of -297 degrees Fahrenheit. A removable conical nose cap acts as an aerodynamic fairing. Inside the tank, baffles reduce sloshing and the associated control problems. The liquid hydrogen tank does not need baffles because the fuel is so light that sloshing does not induce significant forces. The liquid hydrogen tank accounts for the greater part of the external tank. Its contents are even colder than the LOX, -423 degrees Fahrenheit. The intertank structure, or intertank, connects the two propellant tanks. It is a cylindrical structural section that houses instruments and receives and distributes most of the thrust load from the solid rocket boosters. The front end of each booster is connected to the external tank at the intertank midsection. A multi-layered thermal coating covers the outside of the external tank to protect it from extreme temperature variations during pre-launch, launch, and the first 8.5 minutes of flight. That insulation reduces the boil-off rate of the propellants, which must be kept at very low temperatures to remain liquid. It also is meant to minimize ice that might form from condensation on the outside of the propellant tanks. In addition to the solid rocket booster forward attachment points on either side of the intertank, 3 other attachment points link each booster to the aft major ring frame of the external tank. The boosters are thus connected to the tank at 4 points, 1 forward and 3 aft. 3 structural elements link the orbiter to the external tank. A wishbone attachment beneath the crew compartment connects the forward end of the orbiter to the tank. The 2 aft connections are tripods at the base of the external tank. A command from the orbiter computer jettisons the external tank 18 seconds after main engine cutoff, about 8.5 minutes after liftoff. To ensure that it will travel a predictable path, a tumble system rotates the tank end over end at a minimum rate of 2 revolutions per minute. The tank breaks up upon atmospheric entry, falling into the planned area of the Indian or Pacific Ocean about an hour after liftoff. The external tank is the only main component of the space shuttle that is not recovered and reused. Solid rocket boosters. The 2 solid propellant rocket boosters are almost as long as the external tank and attached to each side of it. They contribute about 80% of the total thrust of liftoff. The rest comes from the orbiter's 3 main engines. Roughly 2 minutes after liftoff and 24 miles downrange, the solid rockets have exhausted their fuel. Explosives separate the boosters from the external tank. Small rocket motors move them away from the external tank and the orbiter, which continue toward orbit under thrust of the shuttle's main engines. The solid rocket booster is made up of several subassemblies: the nose cone, solid rocket motor, and the nozzle assembly. Marshall is responsible for the solid rocket booster. Morton Thiokol Inc., Wasatch Division, Brigham City, Utah, is the contractor for the solid rocket motors. Each solid rocket motor case is made of 11 individual cylindrical weld-free steel sections about 12 feet in diameter. When assembled, they form a tube almost 116 feet long. The 11 sections are the forward dome section, 6 cylindrical sections, the aft external tank attach ring section, 2 stiffener sections, and the aft dome section. The 11 sections of the motor case are joined by tang and clevis joints held together by 177 steel pins around the circumference of each joint. After the sections have been machined to fine tolerances and fitted, they are partly assembled at the factory into 4 casting segments. Those 4 cylindrical segments are the parts of the motor case into which the propellant is poured, or cast. They are shipped by rail in separate pieces to Kennedy. Joints assembled before the booster is shipped are known as factory joints. Joints between the 4 casting segments are called field joints. They are connected at Kennedy when the booster systems are stacked for final assembly. Orbital Maneuvering System. The 2 engine pods on the aft fuselage of the orbiter contain maneuvering engines and their propellant, monomethyl hydrazine, the fuel, and nitrogen tetroxide, the oxidizer. Helium pressurizes the propellant tanks, and the fuel and the oxidizer ignite on contact. 44 small rocket motors in the orbiter's nose and aft section maneuvering system pods allow adjustments of the vehicle's attitude in pitch, yaw, and roll axis. They also may be used to make small changes of velocity along one of the orbiter's 3 axes. Flight of a shuttle. Except for ascent and entry, all of the shuttle's typical 7-day mission is in orbit. That is where the goals of a given mission are accomplished, scientific experiments carried out, satellites deployed into orbit, retrieved or repaired, observations made of the Earth and the solar system. The shuttle makes 1 revolution of the Earth approximately every 90 minutes during the satellite mission. When it comes out of orbit, the shuttle is moving at about 17,500 miles an hour. Reaction engines position the orbiter nose forward again for entry into the atmosphere. Those thrusters continue to control the orbiter's attitude until the atmosphere becomes dense enough for the aerodynamic surfaces to take effect. The shuttle enters the ever-thickening blanket of atmosphere at 400,000 feet of altitude and a speed of more than 17,000 miles an hour, about Mach 25. The orbiter's nose is positioned 40 degrees above its flight path. That attitude increases aerodynamic drag, thus helping to dissipate the tremendous amount of energy that the spacecraft has when it enters the atmosphere. Friction heats the surface of the orbiter, which is protected by thermal tiles, and ionizes the surrounding air, preventing radio communication with Earth for the next 13 minutes. The Flight Control System's computer program allows use of the reaction thrusters and the aerodynamic surfaces in combination to control the spacecraft. At Mach 4.2, the rudder is activated, and the last reaction thrusters are deactivated at Mach 1. Thereafter, the craft is entirely maneuvered like an airplane by movement of the aerodynamic control surfaces, elevons, rudder, speed brake, and body flap. In the landing approach, the orbiter has no propulsion. It has only its velocity and altitude. Its energy must be carefully managed to maneuver the shuttle aerodynamically to a safe landing. Beginning this terminal phase, the glide slope is steep, 19 degrees, as the orbiter descends towards the runway. Half a minute before touchdown and 2 miles from the runway, the craft flares to a shallow, almost flat 1.5-degree glide slope. Touchdown occurs at 225 miles per hour. On the runway, the orbiter rolls to a stop, and the mission is complete. End of Section 1. Section 2 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in January 2021. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 2. Events leading up to the Challenger mission. Preparations for the launch of Mission 51-L were not unusual, though they were complicated by changes in the launch schedule. The sequence of complex, interrelated steps involved in producing the detailed schedule and supporting logistics necessary for a successful mission always requires intense effort and close coordination. Flight 51-L of the Challenger was originally scheduled for July 1985, but by the time the crew was assigned in January 1985, launch had been postponed to late November to accommodate changes in payloads. The launch was subsequently delayed further and finally rescheduled for late January 1986. After the series of payload changes, the Challenger cargo included 2 satellites in the cargo bay and equipment in the crew compartment for experiments that would be carried out during the mission. The payloads flown on Mission 51-L are listed in this table. Mission 51-L payloads: Tracking and Data Relay Satellite B, Spartan Halley Satellite, Comet Halley Active Monitoring Program, Fluid Dynamics Experiment, Phase Partitioning Experiment, Teacher in Space Project, Shuttle Student Involvement Program, Radiation Monitoring Experiment. The primary payloads were the Tracking and Data Relay Satellite, a NASA communications satellite, and the Spartan satellite that would be deployed into orbit carrying special instruments for the observation of Halley's comet. The NASA communications satellite was to have been placed in a geosynchronous orbit with the aid of a booster called the inertial upper stage. The satellite would have supported communications with the Space Shuttle and up to 23 other spacecraft. The Spartan satellite was to have been deployed into low Earth orbit using the remote manipulator system. The Spartan instruments would have watched Halley's comet when it was too close to the Sun for other observatories to do so. Subsequently, the satellite would have been retrieved and returned to Earth in the shuttle payload bay. Crew assignments. On January 27, 1985, 1 year before launch, NASA announced the names of the astronauts assigned to Mission 51-L. Commander: Francis R. Scobie. Pilot: Michael J. Smith. Mission Specialist 1: Ellison S. Onizuka. Mission Specialist 2: Judith A. Resnick. Mission Specialist 3: Ronald E. McNair. The mission commander, Francis R. Dick Scobie, first flew on the Space Shuttle as the pilot of Mission 41-C in April 1984. Mr. Scobie, a native of Auburn, Washington, received his bachelor's degree in aerospace engineering from the University of Arizona. A former Air Force test pilot with 7,000 hours in 45 aircraft types, he became an astronaut in 1978. The mission pilot, Captain Michael J. Smith, U.S. Navy, was on his first shuttle flight after being selected as an astronaut in 1980. A native of Beaufort, North Carolina, Captain Smith, a 1967 graduate of the United States Naval Academy, received a master's degree from the Naval Postgraduate School. He was a Navy test pilot with extensive experience in a variety of aircraft. Mission Specialist Lieutenant Colonel Ellison S. Onizuka, U.S. Air Force, from Kealakekua, Kona, Hawaii, received his master's degree in aerospace engineering at the University of Colorado. A flight test engineer in the Air Force, he became an astronaut in 1978 and flew on the first military mission, 51-C, in January 1985 aboard the Space Shuttle Discovery. Mission Specialist Judith A. Resnick, Ph.D., flew on the first flight of the orbiter Discovery on Mission 41-D in August 1984. Born in Akron, Ohio, Dr. Resnick received her doctorate in electrical engineering from the University of Maryland in 1976. After working for several industrial firms, she became an astronaut in 1978. Mission specialist Ronald E. McNair, Ph.D., a native of Lake City, South Carolina, received his doctorate in physics from the Massachusetts Institute of Technology in 1976. After working as a research physicist in civilian industry, he became an astronaut in 1978 and first flew on mission 41-B in February 1984 aboard the Space Shuttle Challenger. Payload specialists are members of a space shuttle crew who are not career astronauts. Two such specialists, Krista McAuliffe and Gregory B. Jarvis, were added to the crew of mission 51-L. Ms. McAuliffe was born in Boston and raised in Framingham, Massachusetts, where she graduated from Framingham State College. After teaching a variety of junior high and high school subjects in Maryland and New Hampshire, she was selected as the Teacher in Space. She was assigned to the 51-L crew in July 1985. Mr. Jarvis was a former Air Force engineer who specialized in satellite design. He was born in Detroit, Michigan, and received his master's degree in electrical engineering from Northeastern University in Boston. He was assigned to the 51-L crew in October 1985 as a representative of the Hughes Aircraft Company. The payload specialists each had responsibilities for mission 51-L. Ms. McAuliffe was to conduct a series of classroom lessons from orbit and conduct several basic classroom experiments. Mr. Jarvis was to perform a series of fluid dynamics experiments that would support satellite redesign. Preparations for flight. Planning for mission 51-L began in 1984, but 10 major change documents adding or deleting payload items caused some disruption in the preparation process. Because the 12 to 18-month process is a series of repetitive cycles that define a flight design in progressively more specific detail, significant changes can require extensive time and effort to incorporate. The closer to the planned launch date the changes occur, the more difficult and disruptive it becomes to repeat the cycles necessary to complete a mission plan. See the mission 51-L milestone summary chart. Although there were several significant changes to the cargo manifest, most occurred early enough in the planning cycle to minimize their impact on the flight preparation. The Cargo Integration Review is one of the crucial coordination meetings in the flight preparation process. At that meeting, requirements for all payloads are examined to ensure that, collectively, they are within the capabilities of the vehicle and crew. For mission 51-L, the Cargo Integration Review was rescheduled 6 times, primarily because of payload changes. All major payload changes were made, however, before the review eventually took place on June 18, 1985, 7 months before the launch. Until the Cargo Integration Review for a mission is completed, the development of the final flight design products cannot really get underway. Because the mission 51-L payload changes were made before the Cargo Integration Review, however, changes to the manifest did not seriously disrupt the preparation cycle. Once the principal payload items were determined and the Cargo Integration Review was completed, the flight design process became relatively straightforward. The flight design process is the central element in flight preparation. The process transforms the broad objectives of the flight into a detailed sequence of events from launch to landing. For mission 51-L, the objectives consisted of placing one satellite in orbit, deploying and retrieving Spartan, and conducting the 6 experiments. From that base, the flight design process produced a detailed schedule of events, trajectory data, requirements for consumable items, communications requirements, and the necessary computer programming for the orbiter, the mission control center, and the shuttle simulator used to train the crew for this particular mission. The launch minus 5 months flight planning and stowage review was conducted on August 20, 1985, to address any unresolved issues and any changes to the plan that had developed to that point. Ideally, the mission events are firmly determined before the review takes place. For Mission 51-L, however, Mr. Jarvis was not added to the crew until October 25, 1985, and his activities could not be incorporated into mission planning until that time. The crew activity plan, the formal flight requirements, and the flight design status were reviewed, as well as the current status of the engineering integration, the photo and TV requirements, and crew compartment stowage. The flight planning and stowage review did identify the need for further consideration of the launch window and of the then undefined requirements for the Teacher in Space program. There were changes to mid-deck payloads resulting from the addition of Mr. Jarvis that occurred less than 3 months before launch. The most negative result of the changes was a delay in publishing the crew activity plan. The crew activity plan specifies the in-flight schedule for all crew members, which in turn affects other aspects of flight preparation. Because the NASA communications satellite training requirements were quite similar to those for a previous flight, the crew training began using that existing crew activity plan and associated checklists. Considerable time was saved as a result. The requirements unique to Spartan did not involve major departures from the standard satellite deployment and rendezvous techniques that had been developed on Mission 51-G. The experiment packages did not require any new orbiter procedures, and the ascent and entry techniques were standard. Thus, Mission 51-L did not involve radical departures from previous flight patterns. The crew began training 37 weeks before launch. Preparing in the Shuttle mission simulator, a fully instrumented mock-up of the Shuttle interior began at launch minus 36 weeks. Integrated training in the simulator, which allows the crew to train with the flight controllers who will be controlling the flight in both the Mission Control Center and remote centers, began at launch minus 9 weeks. For the crew, Shuttle simulator training included preparation for the use of the robot arm, a rendezvous in space, inertial upper stage deployment, ascent and entry procedures, and a variety of other activities that must be practiced repeatedly if a shuttle mission is to be carried out successfully. All NASA crew members exceeded the number of training hours required and were certified proficient in all mission tasks. The 2 payload specialists also fulfilled their training requirements. All Mission 51-L astronauts and flight controllers were certified ready for flight. From a flight design process point of view, Mission 51-L was a fairly typical mission. The most noticeable effect of the delays in the production process was a delay in the start of shuttle mission simulator training specific to the flight. That training began at launch minus 9 weeks for the crew of 51-L, 2 weeks later than the original schedule required. Compressed training time was becoming a concern in late 1985. The crew of Mission 51-L trained for an average of 48.7 hours per week during those 9 weeks before launch, with peaks reaching 65 to 70 hours per week. Much more compression in their training schedule would not have been possible. See the crew workload comparisons graph. Launch date delays for Mission 61-C also became a scheduling factor for the integrated simulations for Mission 51-L. Originally scheduled for the 3rd week in December, the 61-C launch was delayed until January 12, 1986. During the last weeks before the Challenger launch, the 51-L schedule was changed several times as a result of launch delays of 61-C. The final impact on the Challenger crew training was reduced spacing between the ascent and entry simulations during the last 2 weeks before launch, but no training time was lost. Flight Readiness Review. The Level 1 Flight Readiness Review for Mission 51-L took place on January 15, 1986. The Flight Readiness Review should address all aspects of flight preparation about which any questions have arisen. In addition, attendees confirm that all equipment and operational plans have been certified ready by the responsible manager within NASA. Solid rocket booster joints were not discussed during the review on January 15. The period during the day when a particular flight can be launched is determined by the requirements of the orbiter and the payloads. The launch period for Mission 51-L was limited in order to provide the best lighting conditions for Spartan's observations of Halley's comet. The resulting launch window was a topic of some discussion at the Flight Readiness Review. The Challenger launch originally had been scheduled for a morning liftoff. When Spartan was added to the mission, the launch window was changed to the afternoon. This change would have required a landing at night if a transatlantic abort landing had become necessary. Because the alternate transatlantic site, Casablanca, was not equipped for a night landing, the afternoon launch eliminated that backup site. As January drew to a close, however, the conditions for optimum telescopic viewing of the comet could not be met. The launch window was shifted back to the morning hours so that the transatlantic abort site would be in daylight and a backup site, Casablanca, would be available. The results of the flight design process were summarized at the Flight Readiness Review. The predicted ascent performance, including expected trajectory, main engine throttling profile, expected dynamic pressure, and the amount of propellant reserve expected at main engine cutoff, were presented and discussed. The expected landing parameters, weight and center of gravity figures were also presented for a variety of contingencies. It should be noted that a waiver was required because the weight of the orbiter exceeded the allowable limits for an abort landing. The flight design data presented at the Flight Readiness Review are available in the appendix in the NASA Mission Planning and Operations Team Report. No outstanding concerns were identified in the discussion of flight design. The detailed flight plan and schedule of crew activities also were presented at the Flight Readiness Review. The Challenger was to circle the Earth for 6 days at an orbital altitude of approximately 153 nautical miles, landing early on the 7th day at Kennedy in Florida. The major activities were to include deployment of the tracking and data relay satellite 10 hours after launch, deployment of the Spartan satellite on the 3rd day of the flight, and subsequent retrieval of the Spartan 2 days later. A summary of the planned activities is provided in the table that follows. Mission 51-L Orbital Activity Schedule. Day 1. After arriving in orbit, the crew had 2 periods of scheduled high activity. First, they were to check the readiness of the NASA satellite prior to planned deployment. After a lunch break, they were to deploy the satellite and inertial upper stage and to perform a series of separation maneuvers. The first sleep period was scheduled to be 8 hours long, starting about 18 hours after crew wake-up on launch morning. Day 2. The Comet Halley Active Monitoring Program experiment was scheduled to begin on the 2nd day. Also scheduled were the initial Teacher in Space videotaping and the firing of the orbital maneuvering engines to place the orbiter at the 152-mile orbital altitude from which the Spartan would be deployed. Day 3. The 3rd day was to start with the crew programming the Spartan satellite with data sent from Johnson. The satellite was to be deployed using the remote manipulator system, the robot arm, and then the orbiter would be maneuvered to produce, by day 4, a 90-mile separation from Spartan. Day 4. The orbiter was to begin closing on Spartan, while Jarvis continued the fluid dynamics experiments started on day 2 and day 3. In addition, 2 lessons telecast live were to be conducted by Ms. McAuliffe. Day 5. After rendezvous with Spartan, the crew was to use the robot arm to capture the satellite and re-stow it in the payload bay. Day 6. Entry preparations were to dominate the last full day in space. Flight control system checks, test firing of maneuvering jets needed for entry, and cabin stowage. A crew news conference also was scheduled following the lunch period, if requested by the NASA Public Affairs Office. Day 7. The 7th day would have been spent preparing the Space Shuttle for deorbit and entry into the atmosphere. The Challenger was scheduled to land at Kennedy 144 hours and 34 minutes after launch. Launch delays. The launch of Mission 51-L was postponed 3 times and scrubbed once from the planned date of January 22, 1986. The first postponement was announced on December 23, 1985. That change established the launch date as January 23, 1986, in order to accommodate the final integrated simulation schedule that resulted from the slip in the launch date of Mission 61-C. On January 22, 1986, the Program Requirements Change Board first slipped the launch from January 23 to January 25. That date subsequently was changed to January 26, 1986, primarily because of Kennedy work requirements produced by the late launch of Mission 61-C. The third postponement of the launch date occurred during an event management conference on January 25, 1986, to review the weather forecast for the Kennedy area. Because the forecast was for unacceptable weather throughout the launch window on January 26, early countdown activities that had already started were terminated. The launch attempt of January 27 began the day before, as the complex sequence of events leading to liftoff commenced. Fueling of the external tank began at 12:30 a.m. Eastern Standard Time. The crew was awakened at 5:07 a.m., and events proceeded normally with the crew strapped into the shuttle at 7:56 a.m. At 9:10, however, the countdown was halted when the ground crew reported a problem with an exterior hatch handle. By the time the hatch handle problem was solved at 10:30 a.m., winds at the Kennedy runway designated for a return to launch site abort had increased and exceeded the allowable velocity for crosswinds. The launch attempt for January 27 was cancelled at 12:35 p.m. Eastern Standard Time. The Challenger countdown was rescheduled for January 28. The weather was forecast to be clear and very cold, with temperatures dropping into the low 20s overnight. The management team directed engineers to assess the possible effects of temperature on the launch. No critical issues were identified to management officials, and while evaluation continued, it was decided to proceed with the countdown and the fueling of the external tank. Ice had accumulated in the launch pad area during the night, and it caused considerable concern for the launch team. In reaction, the ice inspection team was sent to the launch pad at 1:35 a.m. January 28 and returned to the Launch Control Center at 3 a.m. After a meeting to consider the team's report, the Space Shuttle program manager decided to continue the countdown. Another ice inspection was scheduled at launch -3 hours. Also, during the night, prior to fueling, a problem developed with a fire detector in the ground liquid hydrogen storage tank. Though it was ultimately tracked to a hardware fault and repaired, fueling was delayed by 2½ hours. By continuing past the planned hold at launch minus 3 hours, however, the launch delay was reduced to 1 hour. Crew wake-up was rescheduled for 6:18 a.m. January 28, but by that time the crew was already up. Because of forecast rain and low ceilings at Casablanca, the alternate abort site, that site was declared a no-go at 7:30 a.m. The change had no mission impact, however, because the weather at the primary transatlantic abort landing site at Dakar, Senegal, was acceptable. The abort once around site was Edwards Air Force Base, California. With an extra hour, the crew had more than sufficient time to eat breakfast, get a weather briefing, and put on flight gear. At the weather briefing, the temperature and ice on the pad were discussed, but neither then nor in earlier weather discussions was the crew told of any concern about the effects of low temperature on the shuttle system. The 7 crew members left the crew quarters and rode the astronaut van to launch pad B, arriving at 8:03. They were in their seats in the Challenger at 8:36 a.m. At 8:44 a.m., the ice team completed its second inspection. After hearing the team's report, the program manager decided to allow additional time for ice to melt on the pad. He also decided to send the ice team to perform one final ice assessment at launch minus 20 minutes. When the count was resumed, launch had been delayed a second hour beyond the original liftoff time of 9:38 a.m. Eastern Standard Time. At 11:15, the ice inspection was completed, and during the hold at launch minus 9 minutes, the Mission 51-L crew and all members of the launch team gave their go for launch. The final flight of the Challenger began at 11 hours 38 minutes 0.01 seconds a.m. Eastern Standard Time, January 28, 1986. The flight of the Challenger. The events that followed liftoff were brief. Launch time minus 6.6 seconds. Space Shuttle engines ignition. Launch time 0 seconds. Solid rocket booster ignition. Launch time plus 7 seconds. Roll program. Challenger. Roger. Roll Challenger. Houston. Launch time plus 24 seconds. Main engines throttled down to 94%. Launch time plus 42 seconds. Main engines throttled down to 65%. Launch time plus 59 seconds. Main engines throttled up to 104%. Launch time plus 65 seconds. Challenger, go at throttle up. Houston. Roger, go at throttle up. Challenger. Launch time plus 73 seconds. Loss of signal from Challenger. From liftoff until the signal from the shuttle was lost, no flight controller observed any indication of a problem. The shuttle's main engines throttled down to limit the maximum dynamic pressure, then throttled up to full thrust as expected. Voice communications with the crew were normal. The crew called to indicate the shuttle had begun its roll to head due east and to establish communication after launch. 57 seconds later, Mission Control informed the crew that the engines had successfully throttled up and all other systems were satisfactory. The commander's acknowledgement of this call was the last voice communication from the Challenger. There were no alarms sounded in the cockpit. The crew apparently had no indication of a problem before the rapid breakup of the Space Shuttle system. The first evidence of an accident came from live video coverage. Radar then began to track multiple objects. The flight dynamics officer in Houston confirmed to the flight director that RSO, Range Safety Officer, reports vehicle exploded, and 30 seconds later he added that the Range Safety Officer had sent the destruct signal to the solid rocket boosters. During the period of the flight when the solid rocket boosters are thrusting, there are no survivable abort options. There was nothing that either the crew or the ground controllers could have done to avert the catastrophe. End of section 2.
Section 3 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 3. The Accident. Flight of the Space Shuttle Challenger on Mission 51-L began at 11:38 a.m. Eastern Standard Time on January 28, 1986. It ended 73 seconds later in an explosive burn of hydrogen and oxygen propellants that destroyed the external tank and exposed the orbiter to severe aerodynamic loads that caused complete structural breakup. All 7 crew members perished. The 2 solid rocket boosters flew out of the fireball and were destroyed by the Air Force Range Safety Officer 110 seconds after launch. The ambient air temperature at launch was 36 degrees Fahrenheit, measured at ground level approximately 1,000 feet from the 51-L mission launch pad 39B. This temperature was 15 degrees colder than that of any previous launch. The following description of the flight events is based on visual examination and image enhancement of film from NASA-operated cameras and telemetry data transmitted from the Space Shuttle to ground stations. The last telemetry data from the Challenger was received 73.618 seconds after launch. At 6.6 seconds before launch, the Challenger's liquid-fueled main engines were ignited in sequence and run up to full thrust while the entire shuttle structure was bolted to the launch pad. Thrust of the main engines bends the shuttle assembly forward from the bolts anchoring it to the pad. When the shuttle assembly springs back to the vertical, the solid rocket booster's restraining bolts are explosively released. During this pre-release twang of motion, structural loads are stored in the assembled structure. These loads are released during the first few seconds of flight in a structural vibration mode at a frequency of about 3 cycles per second. The maximum structural loads on the aft field joints of the solid rocket boosters occur during the twang, exceeding even those of the maximum dynamic pressure period experienced later in flight. Just after liftoff, at 0.678 seconds into the flight, photographic data showed a strong puff of gray smoke was spurting from the vicinity of the aft field joint on the right solid rocket booster. The 2 Pad 39B cameras that would have recorded the precise location of the puff were inoperative. Computer graphic analysis of film from other cameras indicated the initial smoke came from the 270 to 310 degree sector of the circumference of the aft field joint of the right solid rocket booster. This area of the solid booster faces the external tank. The vaporized material streaming from the joint indicated there was not complete sealing action within the joint. 8 more distinctive puffs of increasingly blacker smoke were recorded between 0.836 and 2.500 seconds. The smoke appeared to puff upwards from the joint. While each smoke puff was being left behind by the upward flight of the shuttle, the next fresh puff could be seen near the level of the joint. The multiple smoke puffs in this sequence occurred at about 4 times per second, approximating the frequency of the structural load dynamics and resulting joint flexing. Computer graphics applied to NASA photos from a variety of cameras in the sequence again placed the smoke puff's origin in the 270 to 310 degree sector of the original smoke spurt. As the shuttle increased its upward velocity, it flew past the emerging and expanding smoke puffs. The last smoke was seen above the field joint at 2.733 seconds. At 3.375 seconds, the last smoke was visible below the solid rocket boosters and became indiscernible as it mixed with rocket plumes and surrounding atmosphere. The black color and dense composition of the smoke puffs suggest that the grease, joint installation, and rubber O-rings in the joint seal were being burned and eroded by the hot propellant gases. Launch sequence films from previous missions were examined in detail to determine if there were any prior indications of smoke of the color and composition that appeared during the first few seconds of the 51-L mission. None were found. Other vapors in this area were determined to be melting frost from the bottom of the external tank or steam from the rocket exhaust sound suppression water trays. Shuttle main engines were throttled up to 104% of their rated thrust level. The Challenger executed a programmed roll maneuver, and the engines were throttled back to 94%. At approximately 37 seconds, Challenger encountered the first of several high-altitude wind shear conditions, which lasted until about 64 seconds. The wind shear created forces on the vehicle with relatively large fluctuations. These were immediately sensed and countered by the guidance, navigation, and control system. Although Flight 51-L loads exceeded prior experience in both yaw and pitch planes at certain instances, the maxima had been encountered on previous flights and were within design limits. The steering system, thrust vector control of the solid rocket booster responded to all commands and wind shear effects. The wind shear caused the steering system to be more active than on any previous flight. At 45 seconds into the flight, 3 bright flashes appeared downstream of the Challenger's right wing. Each flash lasted less than 1/30th of a second. Similar flashes have been seen on other flights. Another appearance of a separate bright spot was diagnosed by film analysis to be a reflection of main engine exhaust on the orbital maneuvering system pods, located at the upper rear section of the orbiter. The flashes were unrelated to the later appearance of the flame plume from the right solid rocket booster. Both the shuttle main engines and the solid rockets operated at reduced thrust, approaching and passing through the area of maximum dynamic pressure of 720 pounds per square foot. Main engines had been throttled up to 104% thrust, and the solid rocket boosters were increasing their thrust when the first flickering flame appeared on the right solid rocket booster in the area of the aft field joint. This first very small flame was detected on image-enhanced film at 58.788 seconds into the flight. It appeared to originate at about 305 degrees around the booster circumference at or near the aft field joint. One film frame later from the same camera, the flame was visible without image enhancement. It grew into a continuous, well-defined plume at 59.262 seconds. At about the same time, 60 seconds, telemetry showed a pressure differential between the chamber pressures in the right and left boosters. The right booster chamber pressure was lower, confirming the growing leak in the area of the field joint. As the flame plume increased in size, it was deflected rearward by the aerodynamic slipstream and circumferentially by the protruding structure of the upper ring, attaching the booster to the external tank. These deflections directed the flame plume onto the surface of the external tank. This sequence of flame spreading is confirmed by analysis of the recovered wreckage. The growing flame also impinged on the strut attaching the solid rocket booster to the external tank. At about 62 seconds into the flight, the control system began to react to counter the forces caused by the plume and its effects. The left solid rocket booster thrust vector control moved to counter the yaw caused by reduced thrust from the leaking right side solid rocket booster. During the next 9 seconds, Space Shuttle control systems worked to correct anomalies in pitch and yaw rates. The first visual indication that swirling flame from the right solid rocket booster breached the external tank was at 64.660 seconds, when there was an abrupt change in the shape and color of the plume. This indicated that it was mixing with leaking hydrogen from the external tank. Telemeter changes in the hydrogen tank pressurization confirmed the leak. Within 45 milliseconds of the breach of the external tank, A bright, sustained glow developed on the back-tiled underside of the Challenger, between it and the external tank. Beginning at about 72 seconds, a series of events occurred extremely rapidly that terminated the flight. Telemeter data indicate a wide variety of flight systems actions that support the visual evidence of the photos, as the shuttle struggled futilely against the forces that were destroying it. At about 72.20 seconds, the lower strut linking the solid rocket booster and the external tank was severed or pulled away from the weakened hydrogen tank, permitting the right solid rocket booster to rotate around the upper attachment strut. This rotation is indicated by divergent yaw and pitch rates between the left and right solid rocket boosters. At 73.124 seconds, a circumferential white vapor pattern was observed blooming from the side of the external tank bottom dome. This was the beginning of the structural failure of the hydrogen tank that culminated in the entire aft dome dropping away. This released massive amounts of liquid hydrogen from the tank and created a sudden forward thrust of about 2.3 million pounds, pushing the hydrogen tank upward into the intertank structure. At about the same time, the rotating right solid rocket booster impacted the intertank structure and the lower part of the liquid oxygen tank. These structures failed at 73.137 seconds, as evidenced by the white vapors appearing in the intertank region. Within milliseconds, there was massive, almost explosive, burning of the hydrogen streaming from the failed tank bottom and the liquid oxygen breach in the area of the intertank. At this point in its trajectory, while traveling at a Mach number of 1.92 at an altitude of 46,000 feet, the Challenger was totally enveloped in the explosive burn. The Challenger's reaction control system ruptured, and a hypergolic burn of its propellants occurred as it exited the oxygen-hydrogen flames. The reddish-brown colors of the hypergolic fuel burn are visible on the edge of the main fireball. The orbiter, under severe aerodynamic loads, broke into several large sections which emerged from the fireball. Separate sections that can be identified on film include the main engine tail section with the engines still burning, one wing of the orbiter, and the forward fuselage, trailing a mass of umbilical lines pulled loose from the payload bay. Evidence in the recovered wreckage from the 51-L mission hardware supports this final sequence of events. Table 37-39, STS-51-L Sequence of Major Events. Mission time, GMT, 1600 hours, 37 minutes, 53.44 seconds. Main Engine 3 Ignition Command. Elapsed time, 6.566 seconds. Source, General Purpose Computer. 37 minutes, 53.56 seconds. Main Engine 2 Ignition Command. Elapsed time, 6.446 seconds. Source, General Purpose Computer. 37 minutes, 53.68 seconds. Main Engine 1 Ignition Command. Elapsed time, 6.326 seconds. Source, General Purpose Computer. 38 minutes, 00.01 seconds. Solid Rocket Motor Ignition Command. T = 0. Source, General Purpose Computer. 38 minutes, 00.02 seconds. Hold down Post 2. Pyrotechnics Initiator Control Firing. Source, E8 Camera. 38 minutes, 00.26 seconds. First continuous vertical motion. Elapsed time, 0.25 seconds. Source, E9 Camera. 38 minutes, 00.69 seconds. Confirmed smoke above fuel joint on right-hand solid rocket motor. Elapsed time, 0.678 seconds. Source, E60 Camera. 38 minutes, 00.85 seconds. 8 puffs of smoke from 0.836 through 2.500 seconds. Mission elapsed time. Elapsed time 0.836 seconds. Source E63 camera. 38 minutes 2.74 seconds. Last positive evidence of smoke above right aft solid rocket booster external tank attach ring. Elapsed time 2.733 seconds. Source CZR-1 camera. 38 minutes 3.39 seconds. Last positive visual indication of smoke. Elapsed time 3.375 seconds. Source E60 camera. 38 minutes 4.35 seconds. Space Shuttle main engine 104% command. Elapsed time 4.339 seconds. Channel identifier source E41M276D with a sample rate of 25 samples per second. Main engine 3 vehicle command. 38 minutes 5.68 seconds. Right hand solid rocket motor pressure 11.8 psi above nominal. Elapsed time 5.674 seconds. Channel identifier source B47P232C with a sample rate of 12.5 samples per second and a sample period of 0.8 seconds. Right-hand solid rocket motor chamber pressure. 38 minutes 7.73 seconds. Roll maneuver initiated. Elapsed time 7.724 seconds. Channel identifier selected rate gyro assembly roll rate. 39 minutes 19.87 seconds. Space Shuttle main engine 94% command. Elapsed time 19.859 seconds. Channel identifier source selected rate gyro assembly roll rate. Main engine 3 vehicle command. 38 minutes 21.13 seconds. Roll maneuver completed. Elapsed time 21.124 seconds. Channel identifier source selected rate gyro assembly roll rate. 38 minutes 35.39 seconds. Space Shuttle main engine 65% command. Elapsed time 35.379 seconds. Channel identifier source E41M2076D with a sample rate of 25 samples per second and a sample period of 0.04 seconds. Main engine 3 vehicle command. 38 minutes 37.00 seconds. Roll and yaw attitude response to wind 36.990 to 62.990 seconds. Elapsed time 36.99 seconds. Channel identifier source V9H3523C with a sample rate of 12.5 samples per second and a sample period of 0.08 seconds. Body roll attitude error. 38 minutes 51.87 seconds. Space Shuttle main engine 104% command. Elapsed time 51.86 seconds. Channel identifier source E41M276D with a sample rate of 25 samples per second and a sample period of 0.04 seconds. Main engine 3 vehicle command. Mission time GMT 1600 hours, 38 minutes 58.80 seconds. First evidence of flame on right hand solid rocket motor. Elapsed time 58.788 seconds. Source E207 camera. 38 minutes 59.01 seconds. Reconstructed maximum dynamic pressure 720 pounds per square foot. Elapsed time 59 seconds. Source best estimated trajectory. 38 minutes 59.27 seconds. Continuous well-defined plume on right hand solid rocket motor. Elapsed time 59.262 seconds. Source E207 camera. 38 minutes 59.76 seconds. Flame from right hand solid rocket motor in down direction seen from south side of vehicle. Elapsed time 59.73 seconds. Source E204 camera. 39 minutes 00.01 seconds. Solid rocket motor pressure divergence, right hand versus left hand. Elapsed time, 60.004 seconds. Channel identifier source, right hand solid rocket motor chamber pressure. 39 minutes, 00.25 seconds. First evidence of plume deflection, intermittent. Source, E207 camera. 39 minutes, 00.26 seconds. First evidence of solid rocket booster plume attaching to external ring frame. Source, E203 camera. 39 minutes, 00.99 seconds. First evidence of plume deflection continuous. Elapsed time, 60.248 seconds. Source, E203 camera. 39 minutes, 00.99 seconds. First evidence of plume deflection continuous. Elapsed time, 60.988 seconds. Source, E207 camera. 39 minutes, 1.73 seconds. Peak roll rate response to wind. Elapsed time, 61.724 seconds. Channel identifier source, selected gyro assembly roll rate. Mission time GMT, 1600 hours, 39 minutes, 1.73 seconds. Peak roll rate response to wind. Elapsed time, 61.724 seconds. Channel identifier source, selected rate gyro assembly roll rate. 39 minutes, 2.09 seconds. Peak thrust vector control response to wind. Elapsed time, 62.084 seconds. Channel identifier source, left-hand solid rocket booster. Thrust vector control tilt actuator position. 39 minutes, 2.41 seconds. Peak yaw rate response to wind. Elapsed time, 62.404 seconds. Channel identifier, V90R5341C. Selected rate gyro assembly yaw rate. 39 minutes, 2.49 seconds. Right-hand outboard elevon actuator hinge moment spike. Elapsed time, 62.484 seconds. Channel identifier source, right-hand OB elevon primary delta P. 39 minutes, 3.93 seconds. Right-hand outboard elevon actuator delta pressure change. Elapsed time, 63.924 seconds. Channel identifier source, right-hand OB elevon primary delta P. Mission time, 1600 hours GMT, 39 minutes, 3.97 seconds. Start of planned pitch rate maneuver. Elapsed time, 63.964 seconds. Channel identifier source, V90R5321C. Selected rate gyro assembly pitch rate with a sample rate of 5 samples per second and a sample period of 0.2 seconds. 39 minutes, 4.67 seconds. Change in anomalous plume shape. Liquid hydrogen tank leak near 2058 ring frame. Elapsed time, 64.66 seconds. Source, E204 camera. 39 minutes, 4.72 seconds. Bright sustained glow on sides of external tank. Elapsed time, 64.705 seconds. Source, E204 camera. 39 minutes, 4.95 seconds. Start of Space Shuttle main engine gimbal angle, large pitch variations. Elapsed time, 64.937 seconds. Channel identifier source, V58H1100A, with a sample rate of 25 samples per second and a sample period of 0.04 seconds. Main engine pitch actuator position. 39 minutes, 5.17 seconds. Beginning of transient motion due to changes in aero forces due to plume. Elapsed time, 65.164 seconds. Channel identifier source, V90R5321C. Selected rate gyro assembly pitch rate. 39 minutes, 5.53 seconds. Left-hand outboard elevon actuator delta pressure change. Elapsed time, 65.524 seconds. Channel identifier source, left-hand OB elevon primary delta P. 39 minutes, 6.77 seconds. Start of external tank liquid hydrogen pressure deviations. Elapsed time 66.764 seconds. Channel identifier source T41P1700C with a sample rate of 5 samples per second and a sample period of 0.2 seconds. External tank liquid hydrogen ullage pressure. Mission time 1600 hours GMT, 39 minutes, 12.21 seconds. Start of divergent yaw rate, right hand versus left hand, solid rocket booster. Elapsed time 72.204 seconds. Channel identifier source. Select right hand, solid rocket booster yaw rate. 39 minutes, 12.29 seconds. Start of divergent pitch rates, right hand versus left hand, solid rocket booster. Channel identifier source, selected left hand, solid rocket booster pitch rate. 39 minutes, 12.49 seconds. Solid rocket booster major high rate actuator command. Elapsed time 72.478 seconds. Channel identifier source, left hand, solid rocket booster tilt actuator driver. 39 minutes, 12.51 seconds. Space Shuttle main engine roll gimbal rates 5 degrees per second. Elapsed time 72.497 seconds. Channel identifier source, main engine pitch actuator position. 39 minutes, 12.53 seconds. Vehicle max right toward the wingtip, lateral acceleration, plus 0.227 g. Elapsed time 72.525 seconds. Channel identifier source, lateral acceleration. 39 minutes, 12.57 seconds. Solid rocket booster, major high rate actuator motion. Elapsed time 72.564 seconds. Channel identifier source, left hand solid rocket booster, thrust vector control, ROCK actuator position. 39 minutes, 12.57 seconds. Start of H2 tank pressure decrease with 2 flow control valves open. Elapsed time 72.564 seconds. Channel identifier source, T41P1700C. External tank liquid hydrogen ullage pressure. 39 minutes, 12.63 seconds. Last state vector downlinked. Elapsed time 72.624 seconds. Source, data reduction. Mission time 1600 hours GMT, 39 minutes, 12.97 seconds. Start of sharp main propulsion system LOX inlet pressure drop. Elapsed time 72.964 seconds. Channel identifier source, main propulsion system, liquid oxygen inlet pressure, main engine 3. 39 minutes, 13.02 seconds. Last full computer frame of TDRS data. Elapsed time 73.01 seconds. Source, data reduction. 39 minutes, 13.05 seconds. Start of sharp main propulsion system liquid hydrogen inlet pressure drop. Elapsed time 73.044 seconds. Channel identifier source V41P1100C with a sample rate of 12.5 samples per second and a sample period of 0.8 seconds. Main propulsion system liquid hydrogen inlet pressure, main engine 1. 39 minutes, 13.05 seconds. Vehicle max left toward the left wing tip, lateral acceleration, minus 0.254 g. Elapsed time, 73.045 seconds. Channel identifier source, V98A1581C, with a sample rate of 25 samples per second and a sample period of 0.04 seconds, lateral acceleration. 39 minutes, 13.13 seconds. Circumferential white pattern on external tank aft dome, liquid hydrogen tank failure. Elapsed time 73.124 seconds. Source, E204 camera. 39 minutes, 13.134 seconds. Right-hand solid rocket motor pressure, 19 pounds per square inch lower than the left-hand solid rocket motor. Elapsed time 73.124 seconds. Channel identifier, B47P232C, sample rate of 12.5 samples per second, and a sample period of 0.08 seconds, right-hand solid rocket motor chamber pressure. 39 minutes, 13.15 seconds, first hint of vapor at intertank. Elapsed time, 73.137 seconds, source, E207 camera. Mission time, 1600 hours GMT, 39 minutes, 13.15 seconds. All engine systems start responding to loss of fuel and LOX inlet pressure. Elapsed time, 73.143 seconds. Source, Space Shuttle Main Engine Team. 39 minutes, 13.17 seconds. Sudden cloud along external tank between intertank and aft dome. Elapsed time, 73.162 seconds. Source, E207 camera. 39 minutes, 13.20 seconds. Flash between orbiter and liquid hydrogen tank. Elapsed time, 73.191 seconds. Source, E204 camera. 39 minutes, 13.22 seconds. Space Shuttle main engine telemetry data. Interference from 73.211 to 73.303. Elapsed time, 73.211 seconds. 39 minutes, 13.22 seconds. Flash near solid rocket booster. Forward attach and brightening of flash between orbiter and external tank. Elapsed time, 73.213 seconds. Source, E204 camera. 39 minutes, 13.29 seconds. First indication, intense white flash at solid rocket booster, forward attach point. Elapsed time, 73.282 seconds. E204 camera. 39 minutes, 13.34 seconds. Greatly increased intensity of white flash. Elapsed time, 73.327 seconds. E204 camera. 39 minutes, 13.39 seconds. Start of reaction control system. Jet chamber pressure fluctuations. Elapsed time, 73.377 seconds. Channel identifier V42P1552A, with a sample rate of 25 samples per second. Sample period of 0.04 seconds. Reaction control system thruster, chamber pressure. Mission time, 1600 hours, 39 minutes, 13.39 seconds GMT. All engines approaching high-pressure fuel turbopump discharge temp red line levels. Elapsed time, 73.383 seconds. Channel identifier E41T1010D, with a sample rate of 25 samples per second, and a sample period of 0.04 seconds. Main engine 1, high-pressure fuel turbopump, discharge temp channel A. 39 minutes, 13.49 seconds. Main engine 2, high-pressure fuel turbopump, discharge, temperature channel A, vote for shutdown, 2 strikes on channel B. Elapsed time, 73.482 seconds. Source, main engine controller data. 13 minutes, 13.49 seconds. Main engine 2, controller, last time word update. Elapsed time, 73.482 seconds. Main engine controller data. 39 minutes, 13.51 seconds. Main engine 3 in shutdown due to high-pressure fuel turbopump, discharge temperature redline exceedance. Elapsed time, 73.503 seconds. Source, main engine controller data. 30 minutes, 13.51 seconds. Main engine 3 controller, last time word update. Elapsed time, 73.503 seconds. Main engine controller data. 39 minutes, 13.53 seconds. Main engine 1 in shutdown due to high-pressure fuel turbopump, discharge temperature redline exceeding. Elapsed time, 73.523 seconds. Source, calculation. 39 minutes, 13.55 seconds. Main engine 1, last telemetered data point. Elapsed time, 73.543 seconds. Source, calculation. 39 minutes, 13.55 seconds. Main engine 1, last telemetered data point. Elapsed time 73.543 seconds. Source calculation. Mission time 1600 hours GMT, 39 minutes 13.63 seconds. Last validated orbiter telemetry measurement. Elapsed time 73.618 seconds. Channel identifier source V46PO1208. Sample rate 100 samples per second. Sample period of 0.01 seconds. EPU-1 gas generator chamber pressure. 39 minutes 13.64 seconds. End of last reconstructed data frame with valid synchronization and frame count. Elapsed time 73.631 seconds. Source data reduction. 39 minutes 14.14 seconds. Last radio frequency signal from orbiter. Elapsed time 74.13 seconds. Source data reduction. 39 minutes 14.14 seconds. Last radio frequency signal from orbiter. Elapsed time 74.13 seconds. Data reduction. 39 minutes 14.60 seconds. Bright flash in vicinity of orbiter nose. Elapsed time 74.587 seconds. Source E204 camera. 39 minutes 16.45 seconds. Right-hand solid rocket booster, nose cap, separator chute deployment. Elapsed time 76.437 seconds. Source E207 camera. Mission time 1600 hours GMT. 39 minutes 50.26 seconds. Right-hand solid rocket booster, range safety system destruct. Elapsed time 110.25 seconds. Source E202 camera. 39 minutes 50.26 seconds. Left hand solid rocket booster range safety system destruct. Elapsed time 110.252 seconds. Source E230 camera. End of Section 3.
Section 4 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 4, The Cause of the Accident, Part 1. The consensus of the Commission and participating investigative agencies is that the loss of the Space Shuttle Challenger was caused by a failure in the joint between the two lower segments of the right solid rocket motor. The specific failure was the destruction of the seals that are intended to prevent hot gases from leaking through the joint during the propellant burn of the rocket motor. The evidence assembled by the Commission indicates that no other element of the Space Shuttle system contributed to this failure. In arriving at this conclusion, the Commission reviewed in detail all available data, reports, and records, directed and supervised numerous tests, analyses, and experiments by NASA, civilian contractors, and various government agencies, and then developed specific failure scenarios and the range of most probable causative factors. The sections that follow discuss the results of that investigation. Analysis of the accident. The results of the accident investigation and analysis will be presented in this and the following sections. Throughout the investigation, 3 critical questions were central to the inquiry, namely, what were the circumstances surrounding Mission 51L that contributed to the catastrophic termination of that flight, in contrast to 24 successful flights preceding it? What evidence pointed to the right solid rocket booster as the source of the accident, as opposed to other elements of the space shuttle? Finally, what was the mechanism of that failure? Using mission data, subsequently completed tests and analyses, and recovered wreckage, The Commission identified all possible faults that could originate in the respective flight elements of the Space Shuttle, which might have the potential to lead to loss of the Challenger. Potential contributors to the accident examined by the Commission were the launch pad, exonerated in Chapter 9 of this report, the external tank, the Space Shuttle main engines, the orbiter and related equipment, payload-orbiter interfaces, the payload, solid rocket boosters, and solid rocket motors. In a parallel effort, the question of sabotage was examined in detail and reviewed by the Commission in executive session. There is no evidence of sabotage, either at the launch pad or during other processes prior to or during launch. External tank. The external tank contains propellants used by the orbiter's 3 main engines during shuttle launch and ascent to orbit. Structurally, the tank is attached to and serves as the backbone of the orbiter and the 2 solid rocket boosters. 3 primary structures, the liquid oxygen tank, the intertank, and the liquid hydrogen tank, comprise the configuration. The external tank delivers oxidizer and fuel from the propellant tanks to the orbiter. The electrical subsystem includes instrumentation sensors, heaters, range safety electronics and explosives, and lightning protection and associated cabling. All flight instrumentation and electrical power are wired directly to the orbiter. The thermal protection subsystem is the insulation applied to the tank's exterior. Its function is to prevent heat leakage into the propellants, to protect the external tank from overheating during flight, and to minimize ice formation while the shuttle is on the pad. Approximately 20% of the external tank structure was recovered after the accident, and the majority of the pieces were from the intertank and liquid hydrogen tank. The Commission initially considered all external tank systems and subsystems in identifying possible faults or failures potentially contributing to the Challenger accident. Those potential contributors were premature detonation of the external tank range safety system, a structural flaw, damage at liftoff, load exceedance, overheating. The Commission examined the possibility that the STS-51L accident could have been triggered by accidental detonation of the range safety system explosives. This potential fault was assessed using flight data, observed events, and recovered hardware. Most of the explosive charges for the external tank emergency destruction system were recovered. Examination of this material established that none of it had exploded, and thus could not have contributed to the accident. Flight data verified that the external tank range safety system was not activated. The possibility of an imperfection existing in either the pressurized or non-pressurized external tank structural elements that could grow to a sufficient size to cause structural failure was examined in detail. All construction history, structural qualification test data, proof test inspection records, and X-rays were reviewed. One previously undetected imperfection that was discovered during a re-examination of the X-rays was found in recovered hardware with no propagation indicated. Other data from the pre-launch ice and frost team inspections, film and video coverage, pressurization records, and flight data revealed no evidence of leakage. The Commission concluded that no structural imperfections existed that could have grown to a size to create a leak or cause catastrophic failure of the external tank. Possible damage to the liquid hydrogen tank at liftoff was considered. The ice and frost team observed no vapor or frost that would indicate a leak. The liquid hydrogen vent arm retracted as expected during launch, and did not recontact the tank or the solid booster. Photo analysis and television monitoring did not indicate that any debris contacted the tank. Therefore, damage to the liquid hydrogen tank at liftoff was determined to be highly improbable. The possibility that abnormally high structural loads caused an external tank failure was examined. Analysis indicated that there were no excessive loading conditions based on liftoff and flight data prior to the explosion. The maximum structural load produced was less than 80% of the allowable design load. The structural implications of vent and flow control valve operation was examined and found not to be a factor. The possibility of a structural failure due to overheating was assessed, with several causes postulated: high heating due to abnormal trajectory, loss of the thermal protection system, a hot gas leak from the solid rocket motor, and a liquid hydrogen leak from the external tank. The trajectory was normal until well after the solid rocket motor leak was observed at 58 seconds. Maximum aerodynamic heating would not have occurred until approximately 90 seconds. At 73 seconds, heating was well within tank component structural capability. Based on careful review of pre-launch and flight films and data, the Commission found no evidence that any thermal protection foam was lost during the launch and ascent. The possibility of a leak from the hydrogen tank, resulting in overheating, was addressed. Tests indicated that small leaks, 0.037 pounds per second, would have been visible. In addition, if there was a liquid hydrogen leak at liftoff, it would have been ignited by either the solid rocket booster ignition or Space Shuttle main engine ignition. The resultant flame would have ignited the solid rocket booster attach ring foam insulation almost immediately. Copious quantities of dense black smoke and open flames would be evident in such a case, and would have continued for as long as the leak burned. Smoke and flames in these quantities were not observed at liftoff nor any time throughout the flight. It is therefore concluded that an initial liquid hydrogen tank leak was improbable, and that the only possible cause for overheating the tank was the impingement of leaking solid rocket motor gases. This resulted in the ultimate breakup of the external tank. The recovered external foam insulation on the external tank was scorched and discolored in various locations. Burn patterns across the pieces of insulation on the external tank indicate that various areas were subjected to fire both before and after the external tank broke up in flight. The Commission reviewed the external tank's construction records, acceptance testing, pre-launch and flight data, and recovered hardware, and found nothing relating to the external tank that caused or contributed to the cause of the accident. A cluster of 3 Space Shuttle main engines operates simultaneously with the solid rocket boosters during the initial ascent phase of flight, and provides primary propulsion until the shuttle has attained orbital velocity. These engines use liquid hydrogen as the fuel and liquid oxygen as the oxidizer. Both the liquid hydrogen and oxygen are stored in the external tank and are transferred to the engines under pressure. During the mission, the engines operate for about 8.5 minutes. Engine thrust is controlled by throttling and has ranged from 65 to 104% of a specified thrust level. At sea level, 100% equals 375,000 pounds of thrust per engine. Pitch, yaw, and roll control of the orbiter is provided by gimbals on each engine. Gimbaling is operated by 2 hydraulic servo actuators, one for pitch motion and the other for yaw motion, with roll controlled by a combination of both pitch and yaw. These servo actuators are commanded by the orbiter's computer. An electronic controller is attached to the forward end of each engine. Each controller is a self-contained system that monitors engine checkout, control, and status, and sends the data to the orbiter. Each of the 3 engine interface units, in turn, sends its data to the orbiter computers and relays commands from the computers to the engines. A propellant management subsystem of manifolds, distribution lines, and valves controls the flow of liquids from the external tank to the engines, and the flow of gaseous hydrogen and oxygen from the engines into the external tank to maintain pressurization. All 3 main engines from the Challenger, number 2020 in position 2, number 2021 in position 3, and number 2023 in position 1, were recovered in large part on February 23, 1986, off the Florida coast in about 85 feet of water. All parts were recovered close to one another, and the engines were still attached to the thrust structure. All engine gimbal bearings had failed, apparently because of overload on water impact. All metallic surfaces were damaged by marine life, except titanium surfaces or those parts that were buried under the ocean bottom. The metal fractures, examined at 3 times magnification, showed rough texture and shear lips, which appeared to be caused by overloads due to water impact. No pre-accident material defects were noted. The engine nozzles were sheared at the manifolds. The main combustion chambers, main injectors, and pre-burners of each engine were attached to one another. The 6 hydraulic servo actuators used to control engine gimbaling were attached to segments of the orbiter thrust structure. Sections of the main propulsion system fuel and liquid oxygen feed lines and feed line manifolds were recovered, as well as the external tank orbiter disconnect assembly in the mated configuration. A portion of the oxidizer inlet duct was attached to the interface of engine 2020. All pre-burner valves were recovered. The main engine controllers for both engines 2020 and 2021 were recovered. One controller was broken open on one side, and both were severely corroded and damaged by marine life. Both units were disassembled and the memory units flushed with deionized water. After they were dried and vacuum baked, data from these units were retrieved. All engines had burn damage caused by internal overtemperature typical of oxygen-rich shutdown. Thus, the loss of hydrogen fuel appears to have initiated the shutdown. The Commission reviewed engine and ground measurements made while the 3 engines were prepared for launch. Ambient temperature during pre-launch was the coldest to date, but pre-flight engine data were normal. These data were also compared with Challenger engine data during the Flight 61A pre-flight period. All differences seen between the 2 missions were due either to planned variations in the pre-launch sequence or the cold ambient conditions during the pre-flight period for Flight 51L. These differences did not affect engine performance during the powered flight phase of the mission. Pre-flight data gave no evidence of any propellant leaks, fuel or oxidizer, in the aft compartment. For the powered flight phase, all the parameters of the engine aft compartment that could give an indication of a leak were selected from the overall Flight 51L measurement list. The majority of those parameters were either ground measurements or those recorded during the flight but not telemetered to the ground. Among parameters that were telemetered during the flight were skin temperature measurements that gave no indication of a hot gas or other leak in the engine compartment. Analysis of the engine start data showed all 3 engine starts were normal and no anomalies were found. An assessment of the engine performance in the final seconds of the mission before the accident was compared with similar periods on all flights of the Challenger engines. The assessment showed the engine performance on Flight 51L was consistent with previous flights. The first abnormal engine indication was a drop in engine fuel tank pressure at 72.564 seconds. As fuel pressure dropped, the control system automatically responded by opening the fuel flow rate valve. The turbine temperatures then increased because of the leaner fuel mixture. The increased temperature caused an increase in pump speed. This could not, however, increase the fuel pressure because of a decrease in fuel tank top ullage pressure resulting from the burned-through hydrogen tank leakage. When the fuel pump pressures dropped below 140 pounds per square inch, the programmed control system disqualified the measured data because it was past reasonable limits. This caused the fuel flow rate and high-pressure fuel pump discharge pressure to decrease, while the lack of load allowed the pump speed to increase. The decreased fuel flow caused a drop in fuel pre-burner chamber pressure, though the fuel pre-burner oxygen valve was then advancing toward a more open position. The mixture ratio in the fuel pre-burner became leaner, which raised high-pressure fuel turbine discharge temperatures above the red line limits. This caused the engine control system to start automatic shutdown of the engine. The engine flight history showed that engine 2023 flew 4 previous times, while engines 2020 and 2021 had flown 5 previous missions. The flight data from Flight 51L compared well with flight data from all previous flights. The analysis of flight data confirmed that the Space Shuttle main engines operated properly while reacting to changing external conditions. Previous engine tests suggest that the high-pressure pumps are the most likely components to fail because of either bearing or turbine blade failure. There was no evidence of either in Flight 51L. Engine operation was normal until the fuel inlet pressure dropped. As the pressure decreased, the engine responded in a predictable manner. Automatic shutdown of engine 2023 was verified by telemetry data. Data recovered from the salvaged engine 2021 control computer verify that this engine also had begun shutdown. Salvaged control computer data from engine 2020 showed that this engine was within 20 milliseconds of shutdown when the computer stopped. Inspection of recovered engine hardware verified that all engines were shut down in a fuel-lean or oxygen-rich condition, which resulted in burn-through and erosion of the engine hot gas circuits. The Commission concluded that the Space Shuttle main engines did not cause or contribute to the cause of the Challenger accident. Orbiter and related equipment. The orbiter subsystems include propulsion and power, avionics, structures, thermal and environmental control and life support, mechanical and interface, and other government-furnished essential equipment. Onboard government-furnished equipment for STS-51L included the Remote Manipulator Arm System, extravehicular mobility units, extravehicular activity hardware, television, equipment worn by the crew, storage provisions, and communication equipment. The significant pieces of orbiter structure recovered included all 3 Space Shuttle main engines, the forward fuselage including the crew module, the right inboard and outboard elevons, a large portion of the right wing, a lower portion of the vertical stabilizer, 3 rudder speed brake panels, and portions of mid-fuselage side walls from both the left and right sides. This represents about 30% of the orbiter, but does not provide sufficient evidence to establish conclusively the complete failure sequence of the entire orbiter spacecraft. However, there was sufficient evidence to establish some of the structural failure modes that resulted in the orbiter's destruction. All fractures and material failures examined on the orbiter, with the exception of the main engines, were the result of overload forces, and they exhibited no evidence of internal burn damage or exposure to explosive forces. This indicated that the destruction of the orbiter occurred predominantly from aerodynamic and inertial forces that exceeded design limits. There was evidence that during the breakup sequence, the right solid rocket booster struck the outboard end of the orbiter's right wing and right outboard elevon. Additionally, chemical analysis indicated that the right side of the orbiter was sprayed by hot propellant gases exhausting from the hole in the inboard circumference of the right solid rocket booster. Evaluation of the orbiter main engines showed extensive internal thermal damage to the engines as a consequence of oxygen-rich shutdown that resulted from a depletion of the hydrogen fuel supply. The supply of hydrogen fuel to the main engines would have been abruptly discontinued when the liquid hydrogen tank in the external tank disintegrated. The crew module wreckage was found submerged in about 90 feet of ocean water, concentrated in an area of about 20 feet by 80 feet. Portions of the forward fuselage outer shell structure were found among the pieces of crew module recovered. There was no evidence of an internal explosion, heat, or fire damage on the forward fuselage crew module pieces. The crew module was disintegrated, with the heaviest fragmentation and crash damage on the left side. The fractures examined were typical of overload breaks and appeared to be the result of high forces generated by impact with the surface of the water. The sections of lower forward fuselage outer shell found floating on the ocean surface were recovered shortly after the accident. They also contained crush damage indicative of an impact on the left side. The consistency of damage to the left side of the outer fuselage shell and crew module indicates that these structures remained attached to each other until impact with the water. The orbiter investigation consisted of a review of all orbiter data and vehicle parts retrieved. Also reviewed were vehicle and equipment processing records and pre-mission analyses. All orbital maneuvering system measurements, such as temperatures, pressures, events, commands, stimuli, and switch positions, were reviewed with all related computer data. There were no indications of abnormal behavior. All temperature and pressure transducers active during ascent for the reaction control system were reviewed, including thruster chamber pressure, leak temperature, line temperature, propellant tank, helium tank, and propellant line transducers. Nothing was found that could have contributed to the accident. Auxiliary power unit pressures and temperatures were reviewed, and no abnormal conditions were observed during ascent. Selected hydraulic measurements, including system pressures, fluid quantities, and most temperatures in the aft compartment and in the wing cavity containing the elevon actuator supply lines, were reviewed by the Commission, and no abnormality was found. All fuel cells and power reactant storage and distribution subsystem measurements were reviewed and found to be normal during all phases of ground and flight operation prior to the accident. All available pyrotechnic firing control circuit measurements were reviewed, along with radiography, shear bolt review, and debris reports, and there were no unintentional firing command indications. All available data regarding range safety and recovery system batteries were reviewed, and no indications were found that the batteries were involved in initiating the accident. Guidance, navigation, and control subsystems data were reviewed, and it appears that the subsystems performed properly. All subsystem sensors and software apparently performed as designed until data loss. Inertial measurement unit data from the pre-flight calibration through signal loss were found to be normal. All data processing system-related data were reviewed, and nothing significant was found. Data review of the electrical power distribution and control subsystem indicated that its performance was normal until the time of the accident. All communication and tracking system parameters active during launch were evaluated and found to be normal. No instrumentation abnormalities were observed during the pre-launch and launch period before signal loss. Structures evaluation included analysis of ground and flight data, loads, temperatures, pressures, and purge flows, hardware changes and discrepancy reports since the last Challenger flight, and wreckage. The Commission found that no orbiter structural elements contributed to the accident. Orbiter structural pre-launch temperature measurements were evaluated and found to be within specified limits. Data related to the atmospheric revitalization system, which maintains cabin atmosphere, was evaluated. During pre-launch, launch, and until signal loss, data indicated that both of the water coolant loops were normal, the pressure control system functioned normally, all fans functioned normally, and all switches and valve positions were proper. Active thermal control subsystem data indicated that both of the Freon coolant loops functioned normally, the ammonia boiler system was normal, and all switch and valve positions were proper. The water management subsystem functioned normally during the flight. The smoke detection and fire suppression subsystem and airlock support subsystem both functioned normally. The waste collection subsystem is inoperative during the launch phase and no data were available. No mechanical system abnormalities were identified. The vent doors remained open throughout the launch. The payload bay doors remained latched. All landing gear were up and locked. All doors remained closed and locked, and the remote manipulator system and payload retention system remained latched. Film and orbiter interface data showed that there was no premature orbiter external tank separation. Videotapes and photographs indicated the crew egress hatch, which caused the launch delay on the preceding day, operated properly. The onboard government-furnished equipment configuration and pre-launch processing were reviewed and determined to have been flight-ready with no unusual or abnormal conditions. Based on this review and assessment, the Commission concluded that neither the orbiter nor related equipment caused or contributed to the cause of the accident. Payload orbiter interfaces. Interfaces between the orbiter and the payload serve to attach the cargo to the orbiter or provide services from the orbiter to cargo items. These interfaces are mechanical, thermal, avionics, power, and fluid systems. The Spartan Halley payload was located in the front of the payload bay, attached to the Equipment Support Structure Carrier. The Tracking and Data Relay Satellite, TDRS, was attached to the Inertial Upper Stage IUS booster rocket used to move the TDRS into geosynchronous orbit. In the aft flight deck, payload interfaces consisted of a standard switch panel, a payload deployment and retention system, and display and control panels for use with the payload. Payloads in the mid-deck area were in the stowage lockers. These were the radiation monitoring, phase partitioning, fluid dynamics experiments, 3 student experiments, the Teacher in Space project, and the Comet Halley monitoring program. Thermal interfaces between the orbiter and the payload in the aft flight deck and mid-deck consisted of the orbiter's purge, vent, and fluid heat exchanger systems. Thermal interface for TDRS, IUS, Spartan Halley, and the experiments and projects were provided by the Orbiter Environment Control and Life Support System. Electrical power and avionics were provided to the payload through standard interface panels along both sides of the cargo bay. In the aft flight deck, the control and display panels, supplied by the orbiter, provided the avionics and power interfaces for TDRS-IUS. The experiments and projects constituting the mid-deck payload had no interfaces with avionics and power systems. The only direct payload loads data from STS-51L were accelerometer data recorded through the orbiter umbilical prior to liftoff. Accelerometer data from the payload bay and the crew cabin compared favorably with previous flights. Results indicate that payload loads on the STS-51L were similar to those of STS-6 and were within design levels and pre-launch predictions. The Commission found that all payload elements had been certified safe for flight, and records for integration of hardware met engineering requirements. Temperatures during pre-launch and ascent were normal. Reconstructed liftoff loads were below those used in the flight readiness certification. The relay satellite's rate gyro data correlated with those for the orbiter and boosters during ascent. Fittings attaching the payloads to the orbiter remained in operation, as shown by telemeter data from monitoring microswitches. The Commission found no discrepancies in the orbiter payload interface performance that might have contributed to the Challenger accident. End of Section 4. Recording by Maria Kasper. Section 5 of Report to the President by the Presidential Commission on the Space Shuttle Challenger accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger accident. Chapter 4, The Cause of the Accident, Part 2. Payloads, inertial upper stage, and support equipment. The payload bay of the orbiter Challenger contained a tracking and data relay satellite, TDRS, attached to an inertial upper stage IUS booster rocket and associated airborne support equipment. The IUS contained two solid rocket motors, SRMs, SRM-1 and SRM-2. The combined weight of these components was about 40,000 pounds. About 5% of the payload, IUS, and support equipment package was recovered from the ocean. Components recovered included segments of the cases of both IUS SRMs, the ignition-safe arm device for each SRM, the igniter for SRM-2, fragments of unburnt propellant from each SRM, 5 explosive separation bolts that secure the two SRMs together, the forward support equipment trunnions, the aft trunnions with spreader beams, and an undetonated section of explosive fasteners. There was no evidence of scorching, burning, or melting on any of the components and structure recovered, and all fractures were typical overload fractures. The safe arm device for each IUS SRM was in the safe position. The 5 explosive SRM-1, SRM-2 separation bolts were intact, and the pieces of propellant were not burned, indicating that the SRMs had not ignited. The 2 aft trunnion spreader beams were intact, but were bent in the downward direction relative to the orbiter. The right spreader beam was cracked and deformed about 7.5 inches, and the left spreader beam was cracked and deformed about 1.5 inches. These deformations indicate that the payload and upper stage package was intact and secure in the cargo bay while being subjected to significant inertial flight loads. The inertial upper stage is a 2-stage, solid rocket-propelled, 3-axis controlled, inertially navigated upper stage rocket used to deliver spacecraft weighing up to approximately 5,000 pounds from the shuttle parking orbit to geosynchronous orbit. It includes the stage structure, solid rocket motors, a reaction control subsystem, avionics for telemetry, tracking, and command, guidance, navigation and control, data management, thrust vector control, electrical power sources and electrical cabling, and airborne software. Assessment of possible upper stage contribution to the accident centered on the elimination of 3 possible scenarios: premature upper stage rocket ignition, explosion or fire in the payload bay, and payload shift in the payload bay. Premature ignition of either the upper stage, stage 1 and/or stage 2 motor while still in the orbiter bay would have resulted in catastrophic failure of the orbiter. Potential causes for premature ignition were electrostatic discharge, inadvertent ignition command, and auto-ignition. Each would have caused a rapid increase in the orbiter payload bay temperature and pressure, and would have been immediately followed by structural damage to the payload bay doors. The payload bay temperatures remained essentially constant, and the orbiter photographic and telemetry data indicated the payload doors remained closed and latched from liftoff until signal loss. Both indications verified that there was no ignition of the IUS solid rocket motors. An IUS component explosion or fire could have damaged critical systems in the orbiter by overheating or impact. 5 sources, other than an upper stage motor pre-ignition, were identified as potential origins of a fire or explosion in the payload bay. 1. Release and ignition of IUS hydrazine from the reaction control system tanks. 2. Fire or explosion from an IUS battery. 3. Impact or rupture of a motor case and subsequent ignition of exposed propellant. 4. Fire of electrical origin due to a short. And 5. Fire or inadvertent ignition of pyrotechnic devices due to radio frequency radiation. Thermal measurements in the propellant tank and in components adjacent to the propellant tanks indicated no abnormalities. Pre-launch and thermal measurements in the orbiter payload bay and in TDRS near the reaction control system were stable throughout the ascent period. A fire and/or explosion resulting in shrapnel from an IUS battery was eliminated based on pre-launch monitoring of open circuit voltages on all batteries except the support equipment batteries. Location of these batteries made the potential for damage to critical systems very small if they burned or exploded. Motor case impact or rupture and resulting exposure and propellant ignition was determined improbable because batteries and reaction control system burning or explosion were eliminated by flight data analysis. They were the only potential sources for IUS heating and high-velocity shrapnel. Propellant burning was not indicated by payload bay thermal measurements. Electrical shorting was eliminated as a fire source in the payload bay because IUS electrical and orbiter voltage monitors were normal at launch and during STS-51L ascent. Fires initiated by radio frequency radiation due to inadvertent IUS, TDRS, or ground emittance were eliminated because data showed worst-case radio frequency radiation during ascent was less than ground-emitted radiation to the payload bay during pre-launch checkout. The ground-emitted radiation was within specified limits. IUS TDRS payload shifting or breaking free within the orbiter due to structural failure or premature separation was investigated. Such a shift could have resulted in severe orbiter damage from a direct impact or could have induced a significant shift in the Challenger vehicle's center of gravity and possibly affected flight control. 4 possible faults that could have led to orbiter damage or substantial payload shift were considered. IUS Stage 2 TDRS separation, IUS Stage 1 Stage 2 separation, IUS TDRS separation from the airborne support equipment, and IUS airborne support equipment separation from the orbiter. All were eliminated because dynamic response data conclusively showed that IUS TDRS responded normally until the final loss of data. Further, TDRS data, which passed through the IUS Stage 1, Stage 2, and support equipment, were continuous until data loss, verifying that these elements did not separate. The TDRS spacecraft weighs approximately 4,905 pounds and is 9.5 feet in diameter and 19.5 feet long. The forward 11 feet contains 6 deployable appendages, 2 solar arrays, 1 space ground link antenna, and 2 single-access antennas. The spacecraft body structure consists of a payload structure and a spacecraft structure. These structures house the tracking and telemetry and command subsystem, power subsystem, thermal control subsystem, ordnance subsystem, reaction control subsystem, and attitude control subsystem. Telemetry data were transmitted from TDRS from approximately 48 hours prior to launch through signal loss. The telemetry system was functioning properly, and the data indicated that the telemetry processor was in its normal operational mode, and all power supply voltages and calibration voltages were normal. There were no changes through the countdown to the time of structural breakup, when all telemetry abruptly halted. The telemetry tracking and control subsystems, command and tracking elements, were inactive during the countdown through ascent, and no changes were noted, indicating that the TDRS was not commanded to alter its launch configuration. The TDRS power subsystem had a total of 138 telemetry indications. These were the main data source used to determine the power subsystem activity. Analyzing this telemetry showed all subsystem elements performed normally. The TDRS thermal control subsystem was designed to maintain proper temperatures primarily by passive means. Also, there is a thermostatically controlled heater system to ensure minimum required temperatures are maintained. The thermal subsystem was monitored by 82 configuration status indicators and 137 analog temperature channels. This telemetry showed that the TDRS remained in its normal thermal configuration and experienced normal temperatures until signal loss. No data indicated that the IUS separated from the TDRS, that any deployable appendage ordnance had been fired, or that any appendage motion had begun. The TDRS reaction control system was inactive at launch and required an IUS command and 2 ground commands to activate any propellant. Telemetry indicated no valve actuation, changes in tank pressures or temperatures, or propellant line temperature violations. Further, there was no telemetry that would suggest a hydrazine leakage or abnormality, and no indications that the TDRS reaction control system contributed to the accident. During the launch phase, the attitude control subsystem was disabled, except for the gyros and associated electronics necessary to provide the telemetry. All telemetry parameters reflecting attitude control subsystem configuration remained normal and unchanged during the STS-51L pre-launch and post-launch periods. The TDRS was mounted in a cantilevered fashion to the IUS by an adapter ring that provided structural, communications, and power interfaces. Structural integrity loss indications would have been observed by interruptions in telemetry or electrical power. TDRS telemetry during the launch phase was transmitted by electrical cable to the IUS and interleaved with upper stage data. If separation had occurred at either the TDRS-IUS interface or the IUS support equipment interface, TDRS data would have stopped. There was no abnormal telemetry until signal loss of all vehicle telemetry. TDRS also received power from the shuttle via the IUS through the same interfaces. There were no indications of TDRS batteries coming online. This indicates that structural integrity at the TDRS and IUS interfaces was maintained until the structural breakup. Additionally, an inspection of the recovered debris gives the following indications that the TDRS-IUS remained intact until the structural breakup. First, the separation bank lanyards frayed at the end where they attached to the band, indicating that the spacecraft was pulled forcefully from the adapter. Second, the V-groove ring structure at the top of the adapter was torn from its riveted connection to the adapter, indicating that a strong shear existed between the spacecraft and IUS, which would only be generated if the two were still attached. Finally, the adapter base was torn where it attached to the IUS, again indicating high tension and shear forces. There were no indications from telemetry or recovered debris that showed that the structural integrity of the satellite or the satellite stage interface had been compromised. The TDRS records at Kennedy were reviewed for technical correctness and to verify that no open safety-related issues existed. There were no findings that revealed unsafe conditions or that any safety requirements had been violated or compromised. A review and assessment of Spartan-Halley performance was conducted to establish any possible contributions to the STS-51L accident. The Spartan-Halley was unpowered except for the release engage mechanism latch monitor. Its electrical current was in the order of milliamps, and the telemetry records obtained from the orbiter indicated that the latches were in the proper configuration, and thus Spartan-Halley remained firmly attached during flight. In addition, the TDRS spacecraft data indicated there was no interaction from Spartan. Therefore, the Spartan-Halley and its support structure remained intact. The payload bay temperature in the vicinity of Spartan was 55 degrees Fahrenheit, indicating no abnormal thermal conditions. As a result of detailed analyses of the STS-51L orbiter, the payload flight data, payload recovered hardware, flight film, available payload pre-launch data, and applicable hardware processing documentation, the Commission concluded that the payload did not cause or contribute to the cause of the accident. Solid rocket booster. The solid rocket booster comprises 7 subsystems: structures, thrust vector control, range safety, separation, electrical and instrumentation, recovery, and the solid rocket motor. All recovered solid rocket booster pieces were visually examined and selected areas were extracted for chemical and metallurgical analysis. The exterior surfaces of the solid rocket boosters are normally protected from corrosion by an epoxy resin compound. There were several small areas where this protective coating was gouged or missing on the pieces recovered, and as a result, the exposed metallic surfaces in the areas were corroded. The damage to the protective coating was most likely the result of detonation of the linear-shaped charges and water impact. There was no obvious evidence of major external flame impingement or molten metal found on any of the pieces recovered. All fracture surfaces exhibited either the characteristic markings of rapid tensile overload, a complete bending failure due to overload, or a separation fracture due to the detonation of the linear-shaped charges. Other pieces of the right solid rocket motor aft field joint showed extensive burn damage centered at the 307-degree position. Most of the solid rocket motor case material recovered contained pieces of residual unburned propellant still attached to the inner lining of the case structure. The severed propellant edges were sharp, with no unusual burn patterns. Propellant recovered with a forward segment of the booster exhibited the star pattern associated with the receding shape of the propellant at the front end of the solid rocket motor. There was no evidence found of propellant grain cracking or debonding on the pieces recovered. Casting flow lines could be distinguished on the propellant surfaces in several areas. This is a normal occurrence due to minor differences in the propellant cast during the installation of the propellant in the motor case structure. Hardness tests of each piece of the steel casing material were taken before the propellant was burned from the piece. All of the tests showed normal hardness values. One of the pieces of casing showed evidence of O-ring seal tracks on the tang of the field joint. The tracks were cleaned with hexane to remove the grease preservative that had been applied after recovery of the piece, and samples of the track material were removed for analysis. Chemical analysis of the track material showed that the tracks were not composed of degraded O-ring seal material. The possible solid rocket booster faults or failures assessed were structural overload, solid rocket motor pressure integrity violation, and premature linear-shaped charge detonation. Reconstructed liftoff and flight loads were compared with design loads to determine if a structural failure may have caused the accident. The STS-51L loads were within the bounds of design and capability and were not a factor. Photographic and video imagery confirmed that both solid rocket boosters remained structurally intact until the time of the explosion, except for the leak observed on the right solid rocket motor. The possibility that the range safety system prematurely operated, detonating the linear-shaped charges, was investigated. The linear-shaped charges were photographically observed to destroy both solid rocket boosters at 110 seconds after launch when commanded to do so by the range safety officer, and therefore could not have discharged at 73 seconds after launch, causing the accident. The possibilities of the solid rocket boosters separating prematurely from the external tank, the nozzle exit cone prematurely separating, or early deployment of the recovery system were examined. Premature activation of the separation system was eliminated as a cause of failure based on telemetry that showed no separation commands. There were no indications that the nozzle exit cone separated. The recovery system was observed photographically to activate only after the solid rocket boosters had exited the explosion. In addition to the possible faults or failures, STS-51L solid rocket booster hardware manufacturing records were examined in detail to identify and evaluate any deviations from the design, any handling abnormalities or incidents, any material usage issues, and or other indication of problems that might have importance in the investigation. Based on these observations, the Commission concluded that the left solid rocket booster and all components of the right solid rocket booster, except the right solid rocket motor, did not contribute to or cause the accident. The right solid rocket motor. As the investigation progressed, elements assessed as being improbable contributors to the accident were eliminated from further consideration. This process of elimination brought the focus to the right solid rocket motor. As a result, 4 areas related to the functioning of that motor receive detailed analysis to determine their part in the accident. Structural loads evaluation, failure of the case wall, case membrane, propellant abnormalities, loss of the pressure seal at the case joint, and where appropriate, the investigation considered the potential for interaction between these areas. Structural loads evaluation. Structural loads for all STS-51L launch and flight phases were reconstructed using test-verified models to determine if any loading condition exceeded design limits. Seconds prior to liftoff, the Space Shuttle main engines start, while the solid rocket boosters are still bolted to the launch pad. The resultant thrust loads on the solid rocket boosters prior to liftoff were derived in two ways. One, through strain gauges on the hold-down posts, and two, from photographic coverage of solid rocket booster and external tank tip deflections. These showed that the hold-down post-strain data were within design limits. The solid rocket booster tip deflection, or twang, was about 4 inches less than seen on a previous flight, STS-6, which carried the same general payload weight and distribution as STS-51L. The period of oscillation was normal. These data indicate that the Space Shuttle main engine thrust buildup, the resulting forces and movements, vehicle and pad stiffness, and clearances were as expected. The resultant total bending moment experienced by STS-51L was 291 times 10 to the 6th inch-pounds, which is within the design allowable limit of 347 times 10 to the 6th inch-pounds. The STS-51L liftoff loads were compared to design loads and flight-measured loads for STS-1 through STS-7. The shuttle strut identification is shown in Figure 10. The loads measured on the struts are good indicators of stress, since all loads between shuttle elements are carried through the struts. The STS-51L liftoff loads were within the design limit. Because the solid rocket motor field joints were the major concern, the reconstructed joint loads were compared to design loads. Most of the joint load is due to the booster's internal pressure, but external loads and the effects of inertia dynamics also contribute. The solid rocket motor field joint axial tension loads at liftoff were within the design load limit, 17.2 times 10 to the 6th pounds. The highest load occurred at the forward field joint, 15.2 times 10 to the 6th pounds. The mid-joint load was 13.9 times 10 to the 6th pounds, while the aft joint showed 13.8 times 10 to the 6th pounds load. Loads were constructed for all in-flight events, including the roll maneuver and the region of maximum dynamic pressure. A representative measure of these loads is the product of dynamic pressure, Q, and the angle of attack, A, Greek letter alpha. Since the shuttle is designed to climb out at a negative angle of attack, the product is a negative number. The loads in the Q times alpha pitch plane are shown in Figure 11. Although the Q times alpha variations in loads due to wind shear were larger than expected, they were well within the design limit loads. The solid rocket motor field joint axial tension loads were substantially lower at maximum dynamic pressure than at liftoff, 11.6 times 10 to the 6th pounds for the forward field joint, and 10.6 times 10 to the 6th pounds for the aft field joint. Compared to the internal pressure loads, the dynamic variations due to wind shear were small, about 1/15 those of the pressure loads. These loads were well below the design limit loads and were not considered the cause of the accident. Case membrane failure. The case membrane is the half-inch thick steel wall of the rocket between the joints. The possibility that the failure was initiated by anomalies associated with the case membrane was evaluated by analysis of design and test criteria. Potential failure modes were constrained by the following flight data and photographic observations. 1. A burn through the membrane would have to occur at or near the aft field joint. 2. The failure could have little or no influence on motor internal pressure, since no deviation in pressure occurred prior to 60 seconds. 3. The failure must cause a burn through the membrane in 58 seconds. The hypothesis of a membrane failure requires that the initial smoke, observed at 0.678 seconds, was an independent occurrence. It is an unlikely hypothesis for initiation of the accident. Fracture mechanics analysis indicates that a hole in the case larger than 1 inch would cause the entire case to rupture in a few milliseconds. This would give rise to the appearance of a large longitudinal flame, an event that is contrary to the flight films. Evaluation of potential insulation or inhibitor flaws against the 3 criteria above resulted in elimination of all candidates except a defect in the forward-facing inhibitor. This potential failure mode was evaluated by assuming a 1-inch diameter hole in the inhibitor. Analysis indicated that the change in motor internal pressure resulting from this failure would probably not be detected. However, an erosion rate substantially higher than the observed values would be required to burn through the membrane by 58 seconds. In addition, the assumed flaw is unlikely, since the inhibitor is constructed by vulcanizing 8 individual plies of the material. Subsequent damage of the magnitude required is improbable and would be easily detected. A review of the segment inspection and of proof tests was conducted. Prior to vehicle assembly, each segment was pressurized to 112% of the maximum design operational pressure. A magnetic particle inspection of each membrane was then conducted. These procedures are designed to screen critical flaws and are capable of detecting cracks greater than 0.1 inches. Fracture mechanics analysis indicates that a flaw 0.1 inch long and 0.050 inch deep would grow to only 0.122 inches long and 0.061 inches deep in 80 uses of that segment. The flaw would be less than the critical size required to cause rupture. Furthermore, as noted previously, a failure resulting in a case rupture is not consistent with the photographic observations. Subsequent to these evaluations, sections of the right solid rocket motor case containing holes burned through in the area of the aft field joint were recovered. Assessments of the sections do not support a failure that started in the membrane and progressed slowly to the joint, or one that started in the membrane and grew rapidly the length of the solid rocket motor segment. Propellant. An examination of propellant characteristics and flight data was accomplished to determine if any anomalous conditions were present in the STS-51L right solid rocket motor. Propellant cracking and propellant mean bulk temperatures were evaluated. Historically, the propellant family used in the solid rocket motor, TP-H1148, has exhibited good mechanical properties and an absence of grain structural problems. Should a crack occur, however, the effects would be evident by changes in chamber pressure. Shortly after liftoff, the STS-51L right solid rocket motor chamber pressure was 22 pounds per square inch higher than that of the left solid. This would correlate to a postulated radial crack through the grain spanning a 90-degree pie-shaped wedge of the solid. However, with a crack of this nature, the chamber pressure would have remained high for approximately 60 seconds. Telemetry shows that the right solid rocket motor chamber pressure did not remain high past 20 or 24 seconds, and therefore the existence of a propellant crack was ruled out. Propellant mean bulk temperature calculations were made using the ambient temperature over the 2-week period prior to the launch. The lowest bulk temperature experienced was 57 degrees Fahrenheit on the day of the launch. This was 17 degrees Fahrenheit above the minimum specified. Based on this assessment and subscale lot acceptance motor firing evaluations, it is improbable that propellant anomalies contributed to the STS-51L accident. End of Section 5. Recording by Maria Kasper. Section 6 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 4, The Cause of the Accident, Part 3. Joint Seal Failure. Enhanced photographic and computer graphic positioning determined that the flame from the right solid rocket booster near the aft field joint emanated at about the 305-degree circumferential position. The smoke at liftoff appeared in the same general location. Thus, early in the investigation, the right solid rocket booster aft field joint seal became the prime failure suspect. This supposition was confirmed when the salvage team recovered portions of both sides of the aft joint containing large holes extending from 291 degrees to 318 degrees. Several possible causes could have resulted in this failure. These possible causes are treated in the following paragraphs of this report. During stacking operations at the launch site, 4 segments are assembled to form the solid rocket motor. The resulting joints are referred to as field joints, located as depicted in Figures 8 and 13. Joint sealing is provided by 2 rubber O-rings with diameters of 0.280 inches plus 0.005 minus 0.003, which are installed, as received from Morton Thiokol, during motor assembly. O-ring static compression during and after assembly is dictated by the width of the gap between the tang and the inside leg of the clevis. This gap between the tang and clevis at any location, after assembly, is influenced by the size and shape, concentricity of the segments, as well as the loads on the segments. Zinc chromate putty is applied to the composition rubber NBR insulation face prior to assembly. In the assembled configuration, the putty was intended to act as a thermal barrier to prevent direct contact of combustion gas with the O-rings. It was also intended that the O-rings be actuated and sealed by combustion gas pressure displacing the putty in the space between the motor segments. The displacement of the putty would act like a piston and compress the air ahead of the primary O-ring and force it into the gap between the tang and clevis. This process is known as pressure actuation of the O-ring seal. This pressure-actuated sealing is required to occur very early during the solid rocket motor ignition transient, because the gap between the tang and clevis increases as pressure loads are applied to the joint during ignition. Should pressure actuation be delayed to the extent that the gap has opened considerably, the possibility exists that the rocket's combustion gases will blow by the O-ring and damage or destroy the seals. The principal factor influencing the size of the gap opening is motor pressure, but gap opening is also influenced by external loads and other joint dynamics. The investigation has shown that the joint sealing performance is sensitive to the following factors, either independently or in combination. A. Damage to the joints, seals, or generation of contaminants as joints are assembled, as influenced by 1. Manufacturing tolerances, 2. Out of round due to handling, 3. Effects of reuse. B. Tang clevis gap opening due to motor pressure and other loads. C. Static O-ring compression. D. Joint temperature as it affects O-ring response under dynamic conditions, resiliency, and hardness. E. Joint temperature as it relates to forming ice from water intrusion in the joint. F. Putty performance effects on 1. O-ring pressure actuation timing, 2. O-ring erosion. The sensitivity to each factor was evaluated independently and in appropriate combinations to assess the potential to cause or contribute to the 51L aft field joint failure. Most of the testing was done on either laboratory or subscale equipment. In many cases, the data from these tests are considered to be directly applicable to the seal performance in full scale. However, in some cases, there is considerable uncertainty in extrapolating the data to full-scale seal performance. When such is the case, it is noted in the following discussions. Assembly damage contamination. It is possible that the assembly operation could influence joint sealing performance by damaging the O-rings or by generating contamination. The shapes of the solid rocket segments, which include the tang and clevis, are not perfect circles because of dimensional tolerances, stresses, distortions from previous use, and the effects of shipping and handling. The most important effect is from the load of propellant, a plastic and rubbery material which can take a set that relaxes very slowly. For example, since the segments are shipped in a horizontal position on railroad cars, their weight can make them somewhat elliptical, a shape they can maintain for some time. At assembly, after the lower segment with the clevis on top is placed vertically, the tang of the next segment is lowered into it. To make the fit easier, the upper segment is purposely reshaped by connecting the lifting crane in an appropriate position, and on occasion, 51L was one of these, directly squeezing the tang section with a special tool. To monitor the fit, the diameters of the clevis, DC, and the tang, DR, in Figure 15, are measured at 6 positions 30 degrees apart, and the difference of these measurements, dr minus dc, are noted. When these differences are such that the tang encroaches somewhat into the outer clevis, slanted edges, chamfers, permit the pieces to slide together. If the difference is too great, flat areas of the tang meet flat areas of the clevis. What really counts, of course, are differences of radii, which diameter measurements alone do not determine, for one does not know during the assembly how far off the centers are. This is a circumstance to be avoided, but one that can be detected during assembly. Experience has shown that a diameter difference of less than plus 0.25 inches usually permits assembly without a flat-on-flat condition arising. A negative diameter difference means the tang encroaches on the inside of the clevis. The possibility was noted that contaminants from sliding metal and direct O-ring pinching might occur if this overlap is large. If it is too great, a flat-on-flat condition can arise inside the joint, where it is very difficult to see. These dimensions shift as the pieces slide together, and they change further as the propellant stresses relax during the period between assembly and launch. Therefore, a condition such as that which occurred during assembly of the aft segment for Flight 51L, wherein the maximum interference between tang and clevis at the O-rings was at approximately 300 degrees, may or may not have persisted until launch 7 weeks after assembly. The O-rings are heavily greased to prevent damage. This grease adds another element of uncertainty to the configuration and action of the seal under pressurization, especially at low temperatures. Testing was conducted during the investigation to evaluate the potential for assembly damage and contaminant generation and its effect on seal performance. A subscale section of a field joint was configured in a test fixture, and simulated assembly operations were conducted. This section was much stiffer than the full-scale booster segments and did not fully simulate actual assembly conditions. However, under these test conditions, metal slivers were generated during situations wherein the tang flat overlapped the flat end of the clevis leg by 0.005 to 0.010 inches. The metal slivers, in turn, were carried into the joint and deposited on and around the O-rings. A second finding from this test series was that the O-ring section increased in length as the tang entered the clevis and compressed the O-ring diameter. The implication of this finding is that canted tang entry in a full diameter segment, while unlikely, could chase the O-ring around the circumference, resulting in gathering, bulging from the groove on the opposite side. This could make the O-ring more vulnerable to damage. There is no known experience of such bulging during previous assemblies. To understand the effects of potential contaminants on sealing performance, tests were conducted employing metal contaminants simulating those generated in the segment assembly tests. The tests were to determine if joints with metal shavings positioned between the O-ring and the sealing surface could pass a static leak check but fail under dynamic conditions. The contaminants that passed the 50 pounds per square inch leak check were between 0.001 and 0.003 inches thick. Testing to determine seal performance under dynamic conditions with these representative contaminations is not complete. However, the possibility cannot be dismissed that contamination generated under some assembly conditions could pass a leak check and yet cause the seal to leak under dynamic conditions. A second concern was structural damage to the clevis due to abnormal loading during assembly. An analysis was made to determine the deflections and stresses experienced during assembly of the right solid rocket motor aft center segment to the aft segment. These stresses were then used in a fracture mechanics analysis of the O-ring groove to determine the maximum flaw size that would not fail under the 51L case segment life cycle history. Included in this analysis was the single point load needed to deflect a suspended segment to the side by 0.200 inches, and the maximum stress on the case clevis that this causes. The analysis further addressed a condition that has been encountered, where the tang sits on top of the inner clevis leg on one side and slips down into the clevis groove on the opposite side. The result of this analysis is that the stresses induced during the operation were low and would not have resulted in hardware damage. Also, the stresses would have resulted in significant growth of an undetected flaw, which would then be detectable by inspection on its next use. Gap opening. The gap to be sealed between the tang and the inside leg of the clevis opens as the combustion gas pressure rises. This gap opening was calculated as a function of pressure and time by an analysis that was calibrated to joint deflections measured on a structural test article. The analysis extended the results beyond test calibration conditions to include propellant effects and external loads. The initial static gap dimensions combined with the time history of the gap opening determined the minimum and maximum gap conditions used for testing the capability of the O-rings to seal. The joint deflection analysis established time histories for gap openings for primary and secondary O-rings for all field joints. For the aft field joints, these data indicate gap opening increases of approximately 0.029 inches and 0.017 inches for the primary and secondary O-rings, respectively. These values were used for subscale dynamic tests. Due to differences in motor pressure and loads, the gap opening increases for forward field joints are approximately 0.008 inches greater than for the aft field joints. Gap opening changes, called delta gap openings, versus time are shown in Figure 17 for the aft field joints. The total gap at any time also depends on the initial static gap, on rounding effects during segment pressurization, and on loadings due to struts and air loads. Subscale tests were run containing combinations of the above variables, but did not include the effects of the struts and air loads. O-ring compression at launch, static. As noted previously, diameters measured just prior to assembly do not permit determination of conditions at launch, because among other things the propellant slowly relaxes. For STS-51L, the difference in the true diameters of the surfaces of tang and clevis measured at the factory was 0.008 inches. Thus, the average gap at the O-rings between the tang and clevis was 0.004 inches. The minimum gap could be somewhat less, and possibly metal-to-metal contact, zero gap, could exist at some locations. During the investigation, measurements were made on segments that had been refurbished and reused. The data indicate that segment circumferences at the sealing surfaces change with repeated use. This expectation was not unique to this joint. Recent analysis has shown, and tests tend to confirm, that O-ring sealing performance is significantly improved when actuating pressure can get behind the entire face of the O-ring on the upstream side of the groove within which the O-ring sits. If the groove is too narrow, or if the initial squeeze is so great as to compress the O-ring to the extent that it fills the entire groove and contacts all groove surfaces, pressure actuation of the seal could be inhibited. This latter condition is relieved as the joint gap opens and the O-ring attempts to return to its uncompressed shape. However, if the temperature is low, resiliency is severely reduced, and the O-ring is very slow in returning towards its original shape. Thus, it may remain compressed in the groove, contact all three surfaces of that groove, and inhibit pressure actuation of the seal. In addition, as the gap opens between the O-ring and tang surface, allowing pressure bypass, O-ring actuation is further inhibited. Two subscale dynamic test fixtures were designed and built that simulated the initial static gap, gap opening rate, maximum gap opening, and ignition transient pressures. These fixtures were tested over a temperature range with varying initial static gap openings. A summary of results with initial gap openings of 0.020 and 0.004 inches is provided in Figure 19. The results indicate that with a 0.020 inch maximum initial gap, sealing can be achieved in most instances at temperatures as low as 25 degrees Fahrenheit, while with the initial 0.004 inch initial gap, sealing is not achieved at 25 degrees Fahrenheit and is marginal even in the 40 and 50 degree Fahrenheit temperature range. For the 0.004 inch initial gap condition, sealing without any gas blow-by did not occur consistently until the temperature was raised to 55 degrees Fahrenheit. To evaluate the sensitivity to initial gap opening, Tour tests were conducted at 25 degrees Fahrenheit with an initial gap of 0.010 inch. In contrast to the tests at a 0.004 inch gap, these tests resulted in sealing, with some minimal O-ring blow-by observed during the sealing process. These tests indicate the sensitivity of the O-ring seals to temperature and O-ring squeeze in a joint with the gap opening characteristics of the solid rocket motors. It should be noted that the test fixture placed the O-rings at a specific initial gap and squeeze condition uniformly around the circumference. It is not certain what the effect of differences in circumferential gaps might be in full-size joints. Such effects could not be simulated in the subscale test results reported above. Joint temperature. Analyses were conducted to establish STS-51L joint temperatures at launch. Some differences existed among the 6 51L field joints. The joints on the right solid rocket motor had larger circumferential gradients than those on the left motor at launch. It is possible that the aft field joint of the right solid rocket booster was at the lowest temperature at launch, although all joints had calculated local temperatures as low as 28 plus or minus 5 degrees Fahrenheit. Estimated transient temperature for the several circumferential locations on the joints are shown for the right solid rocket motor aft field joint and the left motor aft field joint in figures 20 and 21. These data are representative of other joints on the respective solid rocket motors. The investigation has shown that the low launch temperatures had two effects that could potentially affect the seal performance. 1. O-ring resiliency degradation, the effects of which are explained above, and 2. The potential for ice in the joints. O-ring hardness is also a function of temperature, and may have been another factor in joint performance. Consistent results from numerous O-ring tests have shown a resiliency degradation with reduced temperatures. Figure 23 provides O-ring recovery from 0.040 inches of initial compression versus time. This shows how quickly an O-ring will move back towards its uncompressed shape at temperatures ranging from 10 to 75 degrees Fahrenheit. When these data are compared with the gap openings versus time from Figure 17, it can be seen that the O-rings will not track or recover to the gap opening by 600 milliseconds, gap full open, at low to moderate temperatures. These data show the importance of timely O-ring pressure actuation to achieve proper sealing. It is possible that water got into some, if not all, STS-51L field joints. Subsequent to the Challenger accident, it was learned that water had been observed in the STS-9 joints during restacking operations, following exposure to less rain than that experienced by STS-51L. It was reported that water had drained from the STS-9 joint when the pins were removed, and that approximately 0.5 inch of water was present in the clevis well. While on the pad for 38 days, STS-51L was exposed to approximately 7 inches of rain. Analyses and tests conducted show that water will freeze under the environmental conditions experienced prior to the 51L launch, and could unseat the secondary O-ring. To determine the effects of unseating, tests were conducted on the subscale dynamic test fixture at Thiokol to further evaluate seal performance. For these tests, water was frozen downstream of the secondary O-ring. With ice present, there were conditions under which the O-ring failed to seal. Putty performance. The significance of the possibility that putty could keep the motor pressure from promptly reaching the O-rings to pressure actuate and seal them was apparently not fully appreciated prior to the Challenger accident. During the investigation, it became evident that several variables may affect the putty performance, and in turn seal performance. However, limited test data and lack of fidelity in full-scale joint simulation prevented a complete engineering assessment of putty performance. Tests were conducted over a range of putty conditions, including temperature at ignition, pre-test conditioning to simulate the environmental effects, and dimensional variations within the joint. These test results demonstrated that putty performance as a pressure seal is highly variable. The results may be interpreted to indicate that the putty can maintain pressure during the ignition transient and prevent O-ring sealing. For example, one test conducted with putty, which had been conditioned for 10 hours at 80% relative humidity and 75 degrees Fahrenheit, delayed the pressure rise at the primary O-ring for 530 milliseconds at a temperature of 75 degrees. Tests at 20 degrees Fahrenheit with similarly conditioned putty delayed the pressurization time by 1.9 seconds. Such delays would allow full joint gap opening before a seal could pressure actuate. To evaluate this effect, a subscale test fixture was fabricated that effectively simulated gap opening at the time of putty rupture and pressure application. The tests simulate the O-ring pressure actuation delay due to the putty temporarily holding the motor pressure. They were conducted over a range of temperatures, putty rupture time, and initial O-ring squeeze. Test results demonstrated that sealing performance is dependent on temperature and initial squeeze, both of which affect the pressure actuation capability of the O-rings. The tests indicate that sealing capability is marginal for maximum squeeze conditions, that is, a 0.004-inch gap at 50 degrees Fahrenheit with a pressure delay of 500 milliseconds. For the temperature and O-ring squeeze conditions that existed for several of the STS-51L field joints, O-ring sealing was not achieved in these tests, with simulated putty rupture times delayed to 250 to 500 milliseconds. Note that the subscale tests do not faithfully reproduce what happens in the real joint. These data do indicate, however, that the potential exists for O-rings not to seal as a result of variables related to the putty. The seal is checked by pressurizing the volume between the primary and secondary O-rings. This action seats the secondary seal and drives the primary seal upstream into its groove. Because of concern that the putty could mask a leaking primary seal, the pressure was first increased from 50 pounds per square inch to 100 pounds per square inch and then to 200 pounds per square inch. Clearly, the increased pressure used in the leak check increased the likelihood of a gas path through the putty to the primary seal. That is, with increased pressure, blowholes in the putty are more likely, with a resulting greater potential for erosion damage to the O-ring. On the positive side, the blowholes tend to prevent the delay in pressurization discussed in the previous paragraphs. This further illustrates the influence of putty variables on the performance of the solid rocket motor seals. The dynamic characteristics of the field joint seal. The discussion of static factors which affect joint performance is based on the assumption that motor segments remain perfectly round and that stacked segments are always a perfectly straight column. At launch, the boosters are subjected to forces which bend and twist them. These forces cause physical changes in the shape of the boosters, actually squashing them out of round and bending them along their entire length. The dynamic effects of this out-of-roundness are most significant just after booster ignition, when the hold-down bolts have been released, because in the previous 6.6 seconds the boosters have actually been bent forward by the thrust from the main engines. The elastic energy stored in the entire system is then released, inducing a bending vibration in the boosters. This bending causes the case to change its shape from circular to elliptical, the maximum out-of-roundness occurring on the 45 to 315 degree line on the outside of the right booster. This deflection is a consequence of a vibration and occurs at a frequency of about 3 cycles per second. The same occurs in the left booster, only the deflection axis is oriented differently, being a mirror image of that which takes place on the right side. The dynamic effects cause an increase in the joint rotation, and hence increase the gap between the tang and clevis by about 10%. Another dynamic load results from the geometry of the struts, which attach the booster to the external tank. Strut P12 is attached to the booster at about the 314 degree point and imposes additional inertial forces on the booster, which tend to additionally increase the gap by 10 to 21%. Analysis of the wreckage. The investigation of the sequence of events that led to the final breakup of the Challenger rests upon 3 primary sources of data: launch photographs, telemetry and tracking data, and the recovered pieces of the shuttle wreckage. The third source of data is presented here, which is largely descriptive. It provides support for the conclusions reached through the use of the data from the other 2 sources. A more detailed analysis that provides technical details to be used for subsequent redesign or accident analysis is available in the appendix. Figure 24 shows an overview of the search areas, with the general location of parts of both the left and right solid rocket boosters indicated. The area is at the edge of the Gulf Stream in water depth that ranged from 100 to 1,200 feet. Pertinent pieces were examined by use of a remotely controlled submarine containing a floodlight and a television camera. The television picture was available on shipboard and was transmitted to Kennedy and to Marshall. The arrangement allowed a number of people who were familiar with the solid rocket booster to comment upon the merit of recovering a particular piece. The aft left side of the orbiter contained its original paint markings and showed no apparent sign of heat damage. Thermal distress, however, was apparent on the right rudder speed brake panel and elevon. The paint was scorched and blackened on the right side panels of the aft part of the fuselage and vertical fin. The remaining recovered parts of the orbiter did not seem to be affected by a hydrogen fire. The bottom side of the right wing showed some indentation on the tiles that make up the thermal protection system. This indentation was consistent with impact with the right booster as it rotated following loss of restraint of one or more of its lower struts. The frustum of the nose cone of the right solid rocket booster was damaged, as if it had struck the external tank, but there were no signs of thermal distress. The frustum of the nose cone of the left solid rocket booster was essentially undamaged. A substantial part of the external tank was recovered. Analysis of this recovered structure showed some interesting features. Interpretation of the photographs suggests that the flame from the right-hand solid rocket booster encircled the external tank. A short time later, the dome at the base of the external tank was thought to break free. Since the internal pressure of the liquid hydrogen tank is at approximately 33 pounds per square inch, a sudden venting at the aft section will produce a large initial thrust that tails off as the pressure drops. The intertank region of the wreckage contained buckling in the fore and aft direction consistent with this impulsive thrust. Similarly, the right side of the intertank showed signs of crushing. This crushing is consistent with the rotational impact of the frustum of the right solid rocket booster with the external tank, following complete loss of restraint at the aft lower strut attachment area. The telemetered signals from the rate gyros in the right solid rocket booster clearly show a change in angular velocity of the booster with respect to the orbiter. It is believed that this velocity change was initiated by a failure at or near the P12 strut connecting the booster to the external tank. Photographs of the flight could not define the failure point, and none of the connecting struts to the right solid rocket booster or the corresponding area on the external tank in this region were recovered. Therefore, the exact location of the initial separation could not be determined by the evidence. At the time of relative booster movement, the hole in the shell of the right solid rocket booster was calculated to be 6 to 8 inches in diameter, located 12 to 15 inches forward, and adjacent to the P-12 strut. This location was within the center of the burned-out zone on the right solid rocket booster. As a matter of interest, the P-12 strut is located close to the point on the circumference where the booster case experiences maximum radial deflection due to flight loads. It seems likely that the plume from the hole in the booster would impact near the location of the P-12 strut connection and the external tank. Using geometric considerations alone suggests this strut separated from the external tank before it separated from the right-hand solid rocket booster. Figure 25 shows a sketch of an interior unrolled view of the aft part of the right-hand solid rocket booster, with the recovered burned pieces 131 and 712 noted. The critical region is between parts 131, the upper segment tang region, and part 712, the lower clevis region of the joint. This burned upper area extends roughly from station 1476 in the upper section to 1517 on the lower region. In a circumferential direction, the lower end of the eroded region extends from roughly 291 degrees to 320 degrees, and the upper eroded section extends between 296 and 318 degrees. Note that the region at about 314 degrees includes the attachment region of the strut to the attachment ring on the right solid rocket booster. Some observations were made from a detailed examination of the aft center section of the joint, contact 131. This piece shows a large hole that is approximately centered on the 307-degree circumferential position. Although irregular, the hole is roughly rectangular in shape, extending approximately 27 inches circumferentially along the tang, 296 to 318 degrees, with the total burnout extension approximately 15 inches forward of the tang. At either side in the interior of the hole, the insulation and steel case material showed evidence of hot gas erosion that beveled these surfaces, indicative of combustion products flowing through the hole from the interior of the solid rocket motor. The top surface of the hole was hardly beveled at all. The tang O-ring sealing surface, next to either side of the hole, showed distinct erosion grooves starting from the O-ring locations. These erosion grooves indicate the O-rings were sealing the joint away from the central area during the later stages of the trajectory. No other evidence of thermal distress, melting, or burning was noted in the tang section of the joint. The part of the aft section of the right solid rocket booster in the circumferential position of the hole was recovered. This piece, contact 712, showed evidence of a burned hole edge extending from 291 degrees to 318 degrees, approximately 33 inches long. The burned surface extended into the aft attach stub region of the case adjacent to the P-12 strut attach point. The box structure of the aft attachment ring was missing from the attach stubs. The piece displayed fractures, which led circumferentially or aft from the hole and the burned surface. Booster pieces on either side have not been recovered. Thus, in the burn area, no portion of the clevis or attachment ring, other than the stubs, was available for examination. The exterior surface of the aft case piece also contained a large heat-affected area. The shape and location of this area indicates a plume impingement from the escaping gases. The light-colored material at the downstream edge of the area is probably asbestos from the insulator. The rust-colored line, more or less parallel to the stubs, may be a stagnation line produced in the gas flow when the gases passed around the attachment ring. Secondary flow of metal from the aft attach stub ring also shows this feature. There was a small burn hole in the case wall, which appeared to have penetrated the case from the exterior toward the interior. This may also have been due to a swirling flow of hot gases within the attachment ring box structure. The shadow of the insulation downstream of the attach box can also be seen. This evidence suggests strongly that a hot gas plume impinged against the attachment ring, passed around and through it, and ultimately destroyed its structural integrity, probably late in the flight of the solid rocket booster. The photographs L, M, N, and O view the lower case piece in the inverted position. A correct orientation of this piece is shown in a composite view of the burn area located in Photo P. End of Section 6. Recording by Maria Kasper. Section 7 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 4, The Cause of the Accident, Part 4. Findings. 1. A combustion gas leak through the right solid rocket motor aft field joint, initiated at or shortly after ignition, eventually weakened and or penetrated the external tank, initiating vehicle structural breakup and loss of the Space Shuttle Challenger during STS Mission 51L. 2. The evidence shows that no other STS-51L shuttle element or the payload contributed to the causes of the right solid rocket motor aft field joint combustion gas leak. Sabotage was not a factor. 3. Evidence examined in the review of space shuttle material, manufacturing, assembly, quality control, and processing of nonconformance reports found no flight hardware shipped to the launch site that fell outside the limits of shuttle design specifications. 4. Launch site activities, including assembly and preparation, from receipt of the flight hardware to launch, were generally in accord with established procedures and were not considered a factor in the accident. 5. Launch site records show that the right solid rocket motor segments were assembled using approved procedures. However, significant out-of-round conditions existed between the two segments joined at the right solid rocket motor aft field joint, the joint that failed. A. While the assembly conditions had the potential of generating debris or damage that could cause O-ring seal failure, these were not considered factors in this accident. B. The diameters of the two solid rocket motor segments had grown as a result of prior use. C. The growth resulted in a condition at time of launch wherein the maximum gap between the tang and clevis in the region of the joint's O-rings was no more than 0.008 inches, and the average gap would have been 0.004 inches. D. With a tang to clevis gap of 0.004 inches, the O-ring in the joint would be compressed to the extent that it pressed against all three walls of the O-ring retaining channel. E. The lack of roundness of the segments was such that the smallest tang to clevis clearance occurred at the initiation of the assembly operation at positions of 120 degrees and 300 degrees around the circumference of the aft field joint. It is uncertain if this tight condition and the resultant greater compression of the O-rings at these points persisted to the time of launch. 6. The ambient temperature at time of launch was 36 degrees Fahrenheit, or 15 degrees lower than the next coldest previous launch. A. The temperature at the 300-degree position on the right aft field joint circumference was estimated to be 28 degrees plus or minus 5 degrees Fahrenheit. This was the coldest point on the joint. B. Temperature on the opposite side of the right solid rocket booster facing the sun was estimated to be about 50 degrees Fahrenheit. 7. Other joints on the left and right solid rocket boosters experienced similar combinations of tang to clevis gap clearance and temperature. It is not known whether these joints experienced distress during the flight of 51L. 8. Experimental evidence indicates that due to several effects associated with the solid rocket booster's ignition and combustion pressures and associated vehicle motions, the gap between the tang and clevis will open as much as 0.017 and 0.029 inches at the secondary and primary O-rings, respectively. A. This opening begins upon ignition, reaches its maximum rate of opening at about 200 to 300 milliseconds, and is essentially complete at 600 milliseconds when the solid rocket booster reaches its operating pressure. B. The external tank and right solid rocket booster are connected by several struts, including one at 310 degrees near the aft field joint that failed. This strut's effect on the joint dynamics is to enhance the opening of the gap between the tang and clevis by about 10 to 20% in the region of 300 to 320 degrees. 9. O-ring resiliency is directly related to its temperature. A warm O-ring that has been compressed will return to its original shape much quicker than will a cold O-ring when compression is relieved. Thus, a warm O-ring will follow the opening of the tang to clevis gap. A cold O-ring may not. B. A compressed O-ring at 75 degrees Fahrenheit is 5 times more responsive in returning to its uncompressed shape than a cold O-ring at 30 degrees Fahrenheit. C. As a result, it is probable that the O-rings in the right solid booster aft field joint were not following the opening of the gap between the tang and clevis at time of ignition. 10. Experiments indicate that the primary mechanism that actuates O-ring sealing is the application of gas pressure to the upstream, high-pressure side of the O-ring as it sits in its groove or channel. A. For this pressure actuation to work most effectively, a space between the O-ring and its upstream channel wall should exist during pressurization. B. A tang to clevis gap of 0.004 inches, as probably existed in the failed joint, would have initially compressed the O-ring to the degree that no clearance existed between the O-ring and its upstream channel wall and the other two surfaces of the channel. C. At the cold launch temperature experienced, the O-ring would be very slow in returning to its normal rounded shape. It would not follow the opening of the tang to clevis gap. It would remain in its compressed position in the O-ring channel, and not provide a space between itself and the upstream channel wall. Thus it is probable the O-ring would not be pressure actuated to seal the gap in time to preclude joint failure due to blow-by and erosion from hot combustion gases. 11. The sealing characteristics of the solid rocket booster O-rings are enhanced by timely application of motor pressure. A. Ideally, motor pressure should be applied to actuate the O-ring and seal the joint prior to significant opening of the tang to clevis gap, 100 to 200 milliseconds after motor ignition. B. Experimental evidence indicates that temperature, humidity, and other variables in the putty compound used to seal the joint can delay pressure application to the joint by 500 milliseconds or more. C. This delay in pressure could be a factor in initial joint failure. 12. Of 21 launches with ambient temperatures of 61 degrees Fahrenheit or greater, only 4 showed signs of O-ring thermal distress, that is, erosion or blow-by and soot. Each of the launches below 61 degrees Fahrenheit resulted in 1 or more O-rings showing signs of thermal distress. A. Of these improper joint sealing actions, 1/2 occurred in the aft field joints, 20% in the center field joints, and 30% in the upper field joints. The division between left and right solid rocket boosters was roughly equal. Each instance of thermal O-ring distress was accompanied by a leak path in the insulating putty. The leak path connects the rocket's combustion chamber with the O-ring region of the tang and clevis. Joints that actuated without incident may also have had these leak paths. 13. There is a possibility that there was water in the clevis of the STS-51L joints, since water was found in the STS-9 joints during a destack operation after exposure to less rainfall than STS-51L. At the time of launch, it was cold enough that water present in the joint would freeze. Tests show that ice in the joint can inhibit proper secondary seal performance. 14. A series of puffs of smoke were observed emanating from the 51L aft field joint area of the right solid rocket booster between 0.678 and 2.500 seconds after ignition of the shuttle solid rocket motors. A. The puffs appeared at a frequency of about 3 puffs per second. This roughly matches the natural structural frequency of the solids at liftoff and is reflected in slight cyclic changes of the tang-to-clevis gap opening. B. The puffs were seen to be moving upward along the surface of the booster above the aft field joint. C. The smoke was estimated to originate at a circumferential position of between 270 degrees and 315 degrees on the booster aft field joint, emerging from the top of the joint. 15. This smoke from the aft field joint at shuttle liftoff was the first sign of the failure of the solid rocket booster O-ring seals on STS-51L. 16. The leak was again clearly evident as a flame at approximately 58 seconds into the flight. It is possible that the leak was continuous but unobservable, or non-existent in portions of the intervening period. It is possible in either case that thrust vectoring and normal vehicle response to wind shear, as well as planned maneuvers, reinitiated or magnified the leakage from a degraded seal in the period preceding the observed flames. The estimated position of the flame, centered at a point 307 degrees around the circumference of the aft field joint, was confirmed by the recovery of 2 fragments of the right solid rocket booster. A. A small leak could have been present that may have grown to breach the joint in flame at a time on the order of 58 to 60 seconds after liftoff. B. Alternatively, the O-ring gap could have been resealed by the deposition of a fragile buildup of aluminum oxide and other combustion debris. This resealed section of the joint could have been disturbed by thrust vectoring, space shuttle motion, and flight loads induced by changing winds aloft. C. The winds aloft caused control actions in the time interval of 32 seconds to 62 seconds into the flight that were typical of the largest values experienced on previous missions. Conclusion. In view of the findings, the Commission concluded that the cause of the Challenger accident was the failure of the pressure seal in the aft field joint of the right solid rocket motor. The failure was due to a faulty design, unacceptably sensitive to a number of factors. These factors were the effects of temperature, physical dimensions, the character of materials, the effects of reusability, processing, and the reaction of the joint to dynamic loading. End of Section 7. Recording by Maria Kasper. Section 8 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 5, The Contributing Cause of the Accident. Part 1. The decision to launch the Challenger was flawed. Those who made that decision were unaware of the recent history of problems concerning the O-rings and the joint, and were unaware of the initial written recommendation of the contractor advising against the launch at temperatures below 53 degrees Fahrenheit, and of the continuing opposition of the engineers at Thiokol after the management reversed its position. They did not have a clear understanding of Rockwell's concern that it was not safe to launch because of ice on the pad. If the decision-makers had known all of the facts, it is highly unlikely that they would have decided to launch 51L on January 28, 1986. Flaws in the decision-making process. In addition to analyzing all available evidence concerning the material causes of the accident on January 28th, the Commission examined the chain of decisions that culminated in approval of the launch. It concluded that the decision-making process was flawed in several ways. The actual events that produced the information upon which the approval of the launch was based are recounted and appraised in the sections of this chapter. The discussion that follows relies heavily on excerpts from the testimony of those involved in the management judgments that led to the launch of the Challenger under conditions described. That testimony reveals failures in communication that resulted in a decision to launch 51L based on incomplete and sometimes misleading information, a conflict between engineering data and management judgments, and a NASA management structure that permitted internal flight safety problems to bypass key shuttle managers. The Shuttle Flight Readiness Review is a carefully planned, step-by-step activity established by NASA Program Directive SPO-PD 710.5A, designed to certify the readiness of all components of the Space Shuttle assembly. The process is focused upon the Level 1 Flight Readiness Review, held approximately 2 weeks before a launch. The Level 1 Review is a conference chaired by the NASA Associate Administrator for Spaceflight and supported by the NASA Chief Engineer, the Program Manager, the Center Directors, and Project Managers from Johnson, Marshall, and Kennedy, along with senior contractor representatives. The formal portion of the process is initiated by directive from the Associate Administrator for Spaceflight. The directive outlines the schedule for the Level 1 Flight Readiness Review and for the steps that precede it. The process begins at Level 4 with the contractors formally certifying, in writing, the flight readiness of the elements for which they are responsible. Certification is made to the appropriate Level 3 NASA project managers at Johnson and Marshall. Additionally, at Marshall, the review is followed by a presentation directly to the Center Director. At Kennedy, the Level 3 review, chaired by the Center Director, verifies the readiness of the launch support elements. The next step in the process is the certification of flight readiness to the Level 2 Program Manager at Johnson. In this review, each Space Shuttle program element endorses that it has satisfactorily completed the manufacture, assembly, test, and checkout of the pertinent element, including the contractor's certification that design and performance are up to standard. The Flight Readiness Review process culminates in the Level 1 review. In the initial notice of the review, the Level 1 directive establishes a mission management team for the particular mission. The team assumes responsibility for each shuttle's readiness for a period commencing 48 hours before launch and continuing through post-landing crew egress and the safing of the orbiter. On call throughout the entire period, the mission management team supports the Associate Administrator for Spaceflight and the Program Manager. A structured mission management team meeting, called by Level 1, is held 24 hours or 1 day prior to each scheduled launch. Its agenda includes closeout of any open work, a closeout of any flight readiness review action items, a discussion of new or continuing anomalies, and an updated briefing on anticipated weather conditions at the launch site and at the abort landing sites in different parts of the world. It is standard practice of Level 1 and 2 officials to encourage the reporting of new problems or concerns that might develop in the interval between the Flight Readiness Review and the Level 1 meeting, and between the Level 1 and the launch. In a procedural sense, the process described was followed in the case of Flight 51L. However, in the launch preparation for 51L, relevant concerns of Level 3 NASA personnel and element contractors were not in the following crucial areas adequately communicated to the NASA Level 1 and 2 management responsible for the launch. The objections to launch voiced by Morton Thiokol engineers about the detrimental effect of cold temperatures on the performance of the solid rocket motor joint seal, the degree of concern of Thiokol and Marshall about the erosion of the joint seals in prior shuttle flights, notably 51C, January 1985, and 51B, April 1985. On December 13, 1985, the Associate Administrator for Spaceflight, Jesse Moore, sent out a message distributed among NASA headquarters, NASA field centers, and U.S. Air Force units that scheduled the Flight Readiness Review for January 15, 1986, and prescribed the dates for the other steps in the standard procedure. The message was followed by directives from James A. Gene Thomas, Deputy Director of Launch and Landing Operations at Kennedy, on January 2, 1986, by the National Space Transportation System Program Manager Arnold Aldrich on January 3rd, by William R. Lucas, the Marshall Center Director, on January 7th, and by the Marshall Shuttle Projects Office on January 8th. Each of these implementing directives prescribed for Level 3 the preparatory steps for the Flight Readiness Review. The Flight Readiness Review was held as scheduled on January 15th. On the following day, Aldrich issued the schedule for the combined Level 1 Mission Management Team meetings. He also announced plans for the Mission Management Team meetings continuing throughout the mission and included the schedule for the Level 1 review. On January 23rd, Moore issued a directive stating that the Flight Readiness Review had been conducted on the 15th and that 51L was ready to fly, pending closeout of open work, satisfactory countdown, and completion of remaining Flight Readiness Review action items, which were to be closed out during the Level 1 meeting. No problems with the solid rocket booster were identified. Since December 1982, the O-rings had been designated a Criticality 1 feature of the solid rocket booster design, a term denoting a failure point without backup that could cause a loss of life or vehicle if the component fails. In July 1985, after a nozzle joint on STS-51B showed erosion of a secondary O-ring, indicating that the primary seal failed, a launch constraint was placed on Flight 51F and subsequent launches. These constraints had been imposed and regularly waived by the Solid Rocket Booster Project Manager at Marshall, Lawrence B. Malloy. Neither the launch constraint the reason for it, or the 6 consecutive waivers prior to 51L were known to Moore, Level 1, or Aldrich, Level 2, or Thomas at the time of the Flight Readiness Review process for 51L. It should be noted that there were other and independent paths of system reporting that were designed to bring forward information about the solid rocket booster joint anomalies. One path was the task force of Thiokol engineers and Marshall engineers who had been conducting subscale pressure tests at Wasatch during 1985, a source of documented rising concern and frustration on the part of some of the Thiokol participants and a few of the Marshall participants. But Level 2 was not in the line of reporting for this activity. Another path was the examination at each flight readiness review of the evidence of earlier flight anomalies. For 51L, the data presented in this latter path, while it reached levels 1 and 2, never referred to either test anomalies or flight anomalies with O-rings. In any event, no mention of the O-ring problems in the solid rocket booster joint appeared in the certification of flight readiness, signed for Thiokol on January 9, 1986, by Joseph Kilminster for the solid rocket booster set designated BI-026. Similarly, no mention appeared in the certification endorsement signed on January 15, 1986, by Kilminster and by Malloy. No mention appears in several inches of paper comprising the entire chain of readiness reviews for 51L. In the 51L readiness reviews, it appears that neither Thiokol management nor the Marshall Level 3 project managers believed that the O-ring blow-by and erosion risk was critical. The testimony and contemporary correspondence show that Level 3 believed there was ample margin to fly with O-ring erosion, provided the leak check was performed at 200 pounds per square inch. Following the January 15th Flight Readiness Review, each element of the shuttle was certified as flight ready. The Level 1 Mission Management Team meeting took place as scheduled at 11 a.m. Eastern Standard Time, January 25th. No technical issues appeared at this meeting, or in the documentation, and all Flight Readiness Review actions were reported closed out. Mr. Malloy testified as follows regarding the Flight Readiness Review record about O-ring concerns. Chairman Rogers: Why wasn't that a cause for concern on the part of the whole NASA organization? Mr. Malloy: It was cause for concern, sir. Chairman Rogers: Who did you tell about this? Mr. Malloy: Everyone, sir. Chairman Rogers: And they all knew about it at the time of 51L? Mr. Malloy: Yes, sir. You will find in the Flight Readiness Review record that went all the way to the Level 1 review. It is disturbing to the Commission that, contrary to the testimony of the Solid Rocket Booster Project Manager, the seriousness of concern was not conveyed in Flight Readiness Review to Level 1, and the 51L Readiness Review was silent. The only remaining issue facing the mission management team at the Level 1 review was the approaching cold front, with forecasts of rain showers and temperatures in the mid-60s. There had also been heavy rain since 51L had been rolled out to the launch pad, approximately 7 inches, compared with the 2.5 inches that would have been normal for that season and length of exposure, 35 days. At 12:36 p.m. on the 27th, the mission management team scrubbed the launch for that day due to high crosswinds at the launch site. In the accompanying discussion that ran for about half an hour, all appropriate personnel were polled as to the feasibility of a launch within 24 hours. Participants were requested to identify any constraints. This meeting, aimed at launch at 9:38 a.m. on January 28th, produced no constraints or concerns about the performance of the solid rocket boosters. At 2:00 p.m. on the 27th, the mission management team met again. At that time, the weather was expected to clear, but it appeared that temperatures would be in the low 20s for about 11 hours. Issues were raised with regard to the cold weather effects on the launch facility, including the water drains, the eyewash and shower water, fire suppression system, and overpressure water trays. It was decided to activate heaters in the orbiter, but no concerns were expressed about the O-rings in the solid rocket boosters. The decision was to proceed with the countdown and with fueling, but all members of the team were asked to review the situation and call if any problems arose. At approximately 2:30 p.m. Eastern Standard Time, at Thiokol's Wasatch plant, Robert Ebeling, after learning of the predicted low temperature for the launch, convened a meeting with Roger Boisjoli and with other Thiokol engineers. A brief chronology of the subsequent chain of events begins on page 104. Ebeling was concerned about predicted cold temperatures at Kennedy Space Center. In a post-accident interview, Mr. Ebeling recalled the substance of that meeting. The meeting lasted 1 hour, but the conclusion of that meeting was engineering, especially Arnie, Roger Boisjoli, Brian Russell, myself, Jerry Burns, they come to mind, were very adamant about their concerns on this lower temperature, because we were way below our database and we were way below what we were qualified for. Later in the afternoon of the same day, Alan MacDonald, Thiokol's liaison for the solid rocket booster project at Kennedy Space Center, received a telephone call from Ebeling expressing concern about the performance of the solid rocket booster field joints at low temperatures. During testimony before the Commission on February 28th, MacDonald recounted that conversation. Mr. MacDonald: "Well, I had first become aware of the concern of the low temperatures that were projected for the Cape. It was late in the afternoon of the 27th. I was at Carver Kennedy's house. He is a vice president of, as I mentioned, our Space Operations Center at the Cape, and supports the stacking of solid rocket motors, SRMs. And I had a call from Bob Ebeling. He is the manager of our ignition system and final assembly, and he worked for me as program manager at Thiokol in Utah. And he called me and said that they had just received some word earlier that the weatherman was projecting temperatures as low as 18 degrees Fahrenheit sometime in the early morning hours of the 28th, and that they had had some meetings with some of the engineering people and had some concerns about the O-rings getting to those kind of temperatures. And he wanted to make me aware of that, and also wanted to get some more updated and better information on what the actual temperature was going to be depicted, so that they could make some calculations on what they expected the real temperature the O-rings may see. I told him that I would get that temperature data for him and call him back. Carver Kennedy then, when I hung up, called the Launch Operations Center to get the predicted temperatures from Pad B, as well as what the temperature history had been during the day up until that time. He obtained those temperatures from the Launch Operations Center, and they basically said that they felt it was going to get near freezing or freezing before midnight. It would get as low as 22 degrees as a minimum in the early morning hours, probably around 6 o'clock, and that they were predicting a temperature of about 26 degrees at the intended time, about 9:38 the next morning. I took that data and called back to the plant and sent it to Bob Ebeling and relayed that to him and told him he ought to use this temperature data for his predictions. But I thought this was very serious, and to make sure that he had the vice president, engineering, involved in this and all of his people, that I wanted them to put together some calculations and a presentation of material. Chairman Rogers: "Who is the Vice President Engineering?" Mr. MacDonald: "Mr. Bob Lund is our Vice President Engineering at our Morton Thiokol facility in Utah. To make sure he was involved in this, and that this decision should be an engineering decision, not a program management decision, and I told him that I would like him to make sure they prepared some charts and were in a position to recommend the launch temperature and to have a rationale for supporting that launch temperature." I then hung up and I called Mr. Malloy. He was staying at the Holiday Inn in Merritt Island and they couldn't reach him. And so I called Cecil Houston. Cecil Houston is the resident manager for the Marshall Space Flight Center office at KSC, Kennedy Space Center, and told him about our concerns with the low temperatures and the potential problem with the O-rings. And he said that he would set up a teleconference. He had a 4-wire system next to his office. His office is right across from the VAB, Vehicle Assembly Building, in the Trailer Complex C over there, and he would set up a 4-wire teleconference involving the engineering people at Marshall Space Flight Center at Huntsville, our people back at Thiokol in Utah, and that I should come down to his office and participate at Kennedy from there, and that he would get back to me and let me know when that time would be. Soon thereafter, Cecil Houston called Dr. Judson Lovingood, Deputy Shuttle Project Manager at Marshall Space Flight Center, to inform him of the concerns about the O-rings, and asked Lovingood to set up a teleconference with senior project management personnel, with George Hardy, Marshall's Deputy Director of Science and Engineering, and with Morton Thiokol personnel. Lovingood called Stanley Reinertz, Shuttle Project Manager, a few minutes later and informed him of the planned telecon. The first phase of the teleconference began at 5:45 p.m. Eastern Standard Time. Participants included Reinertz, Lovingood, Hardy, and numerous people at Kennedy, Marshall, and Thiokol-Wasatch. Alan MacDonald missed this phase. He did not arrive at Kennedy until after 8 p.m. Concerns for the effects of low temperature on the O-rings and the joint seal were presented by Morton Thiokol, along with an opinion that launch should be delayed. A recommendation was also made that Aldrich, Program Manager at Johnson, Level 2, be informed of these concerns. The following are excerpts from testimony before the Commission relating to the teleconference. Dr. Keel: You just indicated earlier that, based upon that teleconference, you thought there was a good possibility of delay. Is that what Thiokol was recommending then, was delay? Dr. Lovingood: That is the way I heard it, and they were talking about the 51C experience, and the fact that they had experienced the worst-case blow-by as far as the arc and the soot and so forth, and also they talked about the resiliency data that they had. So it appeared to me, and we didn't have all of the proper people there, that was another aspect of this, it appeared to me that we had better sit down and get the data so that we could understand exactly what they were talking about and assess that data. And that is why I suggested that we go ahead and have a telecon within the center so that we could review that. Dr. Keel: So as early as after that first afternoon conference at 5:45, it appeared that Thiokol was basically saying delay. Is that right? Dr. Lovingood: That is the way it came across to me. I don't know how other people perceived it, but that's the way it came across to me. Dr. Keel: Mr. Reinertz, how did you perceive it? Mr. Reinertz: I did not perceive it that way. I perceived that they were raising some questions and issues which required looking into by all the right parties, but I did not perceive it as a recommendation delay. Dr. Keel: Some prospects for delay? Mr. Reinertz: Yes, sir, that possibility is always there. Dr. Keel: Did you convey that to Mr. Malloy and Mr. Hardy before the 8:15 conference? Mr. Reinertz: Yes, I did. As a matter of fact, we had a discussion. Mr. Malloy was just out of communication for about an hour, and then after that I got in contact with him, and we both had a short discussion relating to the general nature of the concerns, with Dr. Lucas and Mr. Kingsbury at the motel before we both departed for the telecon that we had set up out at the Cape. Dr. Keel: But based upon that, Mr. Lovingood, that impression, you thought it was a significant enough possibility that Mr. Aldrich should have been contacted? Dr. Lovingood: Yes. Dr. Keel: In addition, did you recommend that Mr. Lucas, who is director of Marshall, of course, and Mr. Kingsbury, who is Mr. Hardy's boss, participate in the 8:15 conference? Dr. Lovingood: Yes, I did. Dr. Keel: And you recommended that to whom? Dr. Lovingood: I believe I said that over the net. I said that I thought we ought to have an inter-center meeting involving Dr. Lucas and Mr. Kingsbury, and then plan to go on up the line to Level 2 and Level 1. And then it was after we broke off that first telecon, I called Stan at the motel and told him that he ought to go ahead and alert Arnie to that possibility. Dr. Keel: And Mr. Reinertz, you then visited the motel room of Mr. Lucas with Mr. Kingsbury, and also was Mr. Malloy with you then? Mr. Reinertz: Yes, sir, he was. In the first couple of minutes, I believe I was there by myself, and then Mr. Malloy joined us. Dr. Keel: And did you discuss with them Mr. Lovingood's recommendation that the two of them, Lucas and Kingsbury, participate? Mr. Reinertz: No, sir, I don't recall discussing Mr. Lovingood's recommendations. I discussed with them the nature of the telecon, the nature of the concerns raised by Thiokol, and the plans to gather the proper technical support people at Marshall for examination of the data, and I believe that was the essence of the discussion. Chairman Rogers: But you didn't recommend that the information be given to Level 2 or Level 1? Mr. Reinertz: I don't recall that I raised that issue with Dr. Lucas. I told him what the plans were for proceeding. I don't recall, Mr. Chairman, making any statement regarding that. Mr. Hotz: Mr. Reinertz, are you telling us that you, in fact, are the person who made the decision not to escalate this to a Level 2 item? Mr. Reinertz: That is correct, sir. At approximately 8:45 p.m. Eastern Standard Time, Phase 2 of the teleconference commenced, the Thiokol charts and written data having arrived at Kennedy Space Center by telefax. A table of teleconference participants is included with the chronology of events. The charts presented a history of the O-ring erosion and blow-by in the solid rocket booster joints of previous flights, presented the results of subscale testing at Thiokol, and the results of static tests of solid rocket motors. In the following testimony, Roger Boisjoli, Alan MacDonald, and Larry Malloy expressed their recollections of this teleconference up to the point when an off-net caucus was required. Mr. Boisjoli: I expressed deep concern about launching at low temperature. I presented Chart 2-1 with emphasis. Now, 2-1, if you want to see it, I have it, but basically that was the chart that summarized the primary concerns, and that was the chart that I pulled right out of the Washington presentation without changing one word of it because it was still applicable, and it addresses the highest concern of the field joint in both the ignition transient condition and the steady state condition, and it really sets down the rationale for why we were continuing to fly. Basically, if erosion penetrates the primary O-ring seal, there is a higher probability of no secondary seal capability in the steady state condition. And I had 2 sub-bullets under that, which stated bench testing showed O-ring not capable of maintaining contact with metal parts, gap opening rate to maximum operating pressure. I had another bullet which stated bench testing showed capability to maintain O-ring contact during initial phase, 0 to 170 milliseconds of transient. That was my comfort basis of continuing to fly under normal circumstances, normal being within the database we had. I emphasized when I presented that chart about the changing of the timing function of the O-ring as it attempted to seal. I was concerned that we may go from that first beginning region into that intermediate region, from 0 to 170 being the first region, and 170 to 330 being the intermediate region, where we didn't have a high probability of sealing or seating. I then presented Chart 2-2 with added concerns related to the timing function. And basically on that chart, I started off talking about a lower temperature than current database results in changing the primary O-ring sealing timing function, and I discussed the SRM-15 Flight 51C January 1985 observations, namely the 15A left solid rocket motor Flight 51C motor had 80 degrees arc black grease between the O-rings. And make no mistake about it, when I say black, I mean black just like coal. It was jet black. And solid rocket motor 15B, right SRM Flight 51C, had a 110-degree arc of black grease between the O-rings. We would have low O-ring squeeze due to low temperature, which I calculated earlier in the day. We should have higher O-ring shore hardness. Now that would be harder. And what that material really is, it would be likened to trying to shove a brick into a crack versus a sponge. That is a good analogy for purposes of this discussion. I also mentioned that thicker grease, as a result of lower temperatures, would have a higher viscosity. It wouldn't be as slick and slippery as it would at room temperature, and so it would be a little bit more difficult to move across it. We would have higher O-ring pressure actuation time, in my opinion, and that is what I presented. These are the sum and substance of what I just presented. If action time increases, then the threshold of secondary seal pressurization capability is approached. That was my fear. If the threshold is reached, then secondary seal may not be capable of being pressurized, and that was the bottom line of everything that had been presented up to that point. Chairman Rogers: Did anybody take issue with you? Mr. Boisjoli: Well, I am coming to that. I also showed a chart of the joint with an exaggerated cross-section to show the seal lifted off, which has been shown to everybody. I was asked, yes, at that point in time, I was asked to quantify my concerns. And I said I couldn't quantify it. I had no data to quantify it. But I did say I knew that it was away from goodness in the current database. Someone on the net commented that we had soot blow by on SRM-22, Flight 61A, October 1985, which was launched at 75 degrees. I don't remember who made the comment, but that is where the first comment came in about the disparity between my conclusion and the observed data, because SRM-22 had blow-by at essentially a room temperature launch. I then said that SRM-15, Flight 51C, January 1985, had much more blow-by indication, and that it was indeed telling us that lower temperature was a factor. This was supported by inspection of flown hardware by myself. I was asked again for data to support my claim, and I said I have none other than what is being presented, and I had been trying to get resilience data, Arnie and I both, since last October, and that statement was mentioned on the net. Others in the room presented their charts, and the main telecon session concluded with Bob Lund, who is our Vice President of Engineering, presenting his conclusions and recommendations charts, which were based on our data input up to that point. Listeners on the telecon were not pleased with the conclusions and the recommendations. Chairman Rogers: What was the conclusion? Mr. Boisjoli: The conclusion was we should not fly outside of our database, which was 53 degrees. Those were the conclusions. And we were quite pleased because we knew in advance, having participated in the preparation, what the conclusions were, and we felt very comfortable with that. Mr. Atchison: Who presented that conclusion? Mr. Boisjoli: Mr. Bob Lund. He had prepared those charts. He had input from other people. He had actually physically prepared the charts. It was about that time that Mr. Hardy from Marshall was asked what he thought about the MTI, or Morton Thiokol, recommendation, and he said he was appalled at the MTI decision. Mr. Hardy was also asked about launching, and he said no, not if the contractor recommended not launching. He would not go against the contractor and launch. There was a short discussion that ensued about temperature not being a discriminator between SRM-15, Flight 51C, and SRM-22, Flight 51A. And shortly after, I believe it was Mr. Kilminster asked if... Excuse me, I'm getting confused here. Mr. Kilminster was asked by NASA if he would launch, and he said no because the engineering recommendation was not to launch. Then MTI management then asked for a 5-minute caucus. I'm not sure exactly who asked for that, but it was asked in such a manner that I remember it was asked for, a 5-minute caucus, which we put on the line on mute and went offline with the rest of the net. Chairman Rogers: Mr. Boisjoli, at the time that you made that Thiokol made the recommendation not to launch, was that the unanimous recommendation as far as you knew? Mr. Boisjoli: Yes. I have to make something clear. I have been distressed by the things that have been appearing in the paper and things that have been said in general, and there was never one positive pro-launch statement ever made by anybody. There have been some feelings since then that folks have expressed that they would support the decision, but there was not one positive statement for launch ever made in that room. Mr. McDonald's testimony. Mr. McDonald: I arrived at the Kennedy Space Center at about 8:15 p.m., and when I arrived there at the Kennedy Space Center, the others that had already arrived were Larry Malloy, who was there. He is the manager, the project manager for the SRB, the solid rocket booster, for Marshall. Stan Reinertz was there, and he is the manager of the Shuttle project office. He is Larry Malloy's boss. Cecil Houston was there, the resident manager for Marshall, and Jack Buchanan was there. He happens to be our manager, Morton Thiokol's manager of our Launch Support Services office at Kennedy. The telecon hadn't started yet. It came on the network shortly after I got there. Chairman Rogers: Was it essentially a telephone conference, or was there actually a network of pictures? Mr. McDonald: It was a telephone conference, but I will relay what I heard at the conference as best I can. The teleconference started, I guess, close to 9 o'clock, and even though all the charts weren't there, we were told to begin, and that Morton Thiokol should take the lead and go through the charts that they had sent to both centers. The charts were presented by the engineering people from Thiokol, in fact by the people that had made those particular charts. Some of them were typed, some of them were handwritten, and they discussed their concerns with the low temperatures relative to the possible effects on the O-rings, primarily the timing function to seal the O-rings. They presented a history of some of the data that we had accumulated, both in static test and in flight tests, relative to temperatures and the performance of the O-rings, and reviewed the history of all our erosion studies of the O-rings in the field joints, any blow-by of the primary O-ring with soot, or products of combustion or decomposition that we had noted, and the performance of the secondary O-rings. And there was an exchange amongst the technical people on that data as to what it meant. But the real exchange never really came until the conclusions and recommendations came in. At that point in time, our Vice President, Mr. Bob Lund, presented those charts, and he presented the charts on the conclusions and recommendations. And the bottom line was that the engineering people would not recommend a launch below 53 degrees Fahrenheit. The basis for that recommendation was primarily our concern with the launch that had occurred about a year earlier, in January of 1985. I believe it was 51C. End of Section 8. Recording by Maria Kasper. Section 9 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 5, The Contributing Cause of the Accident, Part 2. Mr. Malloy's Testimony. Mr. Malloy: That telecon was a little late starting. It was intended to be set up at 8:15, and the telecon was begun at 8:45. And Thiokol will then present to you today the data that they presented to us in that telecon. I will not do that. The bottom line of that, though, initially, was that Thiokol Engineering, Bob Lund, who is the Vice President and Director of Engineering, who is here today, recommended that 51L not be launched if the O-ring temperatures predicted at launch time would be lower than any previous launch, and that was 53 degrees. Dr. Walker: May I ask a question? I wish you would distinguish between the predicted bulk temperatures and the O-ring temperatures. In fact, as I understand it, you really don't have any official O-ring temperature prediction in your models, and it seems that the assumption has been that the O-ring temperature is the same as the bulk temperature, which we know is not the case. Mr. Malloy: You will see, sir, in the Thiokol presentation today that it is not the case. This was a specific calculation of what the O-ring temperature was on the day of the January 1985 launch. It is not the bulk temperature of the propellant, nor is it the ambient temperature of the air. It was Thiokol's calculation of what the lowest temperature an O-ring had seen in previous flights, and the engineering recommendation was that we should not move outside of that experience base. I asked Joe Kilminster, who is the program manager for the booster program at Thiokol, what his recommendation was, because he is the gentleman that I get my recommendations from in the program office. He stated that, based on that engineering recommendation, that he could not recommend launch. At that point, I restated, as I have testified to, the rationale that was essentially documented in the 1982 critical items list, that stated that the rationale had been that we were flying with a simplex joint seal. And you will see in the Thiokol presentation that the context of their presentation is that the primary ring, with the reduced temperatures and reduced resiliency, may not function as a primary seal, and we would be relying on the secondary. And without getting into their rationale and getting ahead, the point, the bottom line, is that we were continuing. The assessment was, my assessment at that time was, that we would have an effective simplex seal based upon the engineering data that Thiokol had presented, and that none of those engineering data seemed to change that basic rationale. Stan Reinertz then asked George Hardy, the Deputy Director of Science and Engineering at Marshall, what his opinion was. George stated that he agreed that the engineering data did not seem to change this basic rationale, but also stated on the telecon that he certainly would not recommend launching if Thiokol did not. At that time, Joe Kilminster requested a 5-minute off-net caucus, and that caucus lasted approximately 30 minutes. The teleconference was recessed at approximately 10:30 p.m. Eastern Standard Time. The off-net caucus of Thiokol personnel started and continued for about 30 minutes at the Wasatch office. The major issues, according to the testimony of Jerry Mason, Senior Vice President for Wasatch Operations, were the effect of temperature upon the O-rings and the history of erosion of the O-rings. Mr. Mason: Now, in the caucus, we revisited all of our previous discussions, and the important things that came out of that was that, as we had recognized, we did have the possibility that the primary O-ring might be slower to move into the seating position, and that was our concern, and that is what we had focused on originally. The fact that we couldn't show direct correlation with the O-ring temperature was discussed, but we still felt that there was some concern about it being colder. We then recognized that if the primary did move more slowly, that we could get some blow-by and erosion on the primary. But we had pointed out to us in that caucus a point that had not come across clearly in our earlier discussions, and that is that we had run tests where we deliberately cut large pieces out of the O-rings to see what the threshold of sealing was, and we found that we could go to 125 thousandths of a cut out of the O-ring and it would still seal. Approximately 10 engineers participated in the caucus, along with Mason, Kilminster, C.G. Wiggins, Vice President Space Division, and Lund. Arnold Thompson and Boisjoli voiced very strong objections to launch, and the suggestion in their testimony was that Lund was also reluctant to launch. Mr. Boisjoli. Okay, the caucus started by Mr. Mason stating a management decision was necessary. Those of us who opposed the launch continued to speak out, and I am specifically speaking of Mr. Thompson and myself, because in my recollection he and I were the only ones that vigorously continued to oppose the launch. And we were attempting to go back and re-review and try to make clear what we were trying to get across, and we couldn't understand why it was going to be reversed. So we spoke out and tried to explain once again the effects of low temperature. Arnie actually got up from his position, which was down the table, and walked up the table and put a quarter pad down in front of the table, in front of the management folks, and tried to sketch out once again what his concern was with the joint. And when he realized he wasn't getting through, he just stopped. I tried one more time with the photos. I grabbed the photos and I went up and discussed the photos once again, and tried to make the point that it was my opinion from actual observations that temperature was indeed a discriminator, and we should not ignore the physical evidence that we had observed. And again, I brought up the point that SRM-15, Flight 51C, January 1985, had a 110-degree arc of black grease, while SRM-22, Flight 61A, October 1985, had a relatively different amount, which was less and wasn't quite as black. I also stopped when it was apparent that I couldn't get anybody to listen. Dr. Walker. At this point, did anyone else speak up in favor of the launch? Mr. Boisjoli. No, sir, no one said anything in my recollection. Nobody said a word. It was then being discussed among the management folks. After Arnie and I had our last say, Mr. Mason said we have to make a management decision. He turned to Bob Lund and asked him to take off his engineering hat and put on his management hat. From this point on, management formulated the points to base their decision on. There was never one comment in favor, as I have said, of launching by any engineer or other non-management person in the room before or after the caucus. I was not even asked to participate in giving any input to the final decision charts. I went back on the net with the final charts or final chart, which was the rationale for launching, and that was presented by Mr. Kilminster. It was handwritten on a notepad, and he read from that notepad. I did not agree with some of the statements that were being made to support the decision. I was never asked nor polled, and it was clearly a management decision from that point. I must emphasize I had my say, and I never would take away any management right to take the input of an engineer and then make a decision based upon that input, and I truly believe that. I have worked at a lot of companies, and that has been done from time to time, and I truly believe that, so there was no point in me doing anything further than I had already attempted to do. I did not see the final version of the chart until the next day. I just heard it read. I left the room feeling badly defeated, but I felt I really did all I could to stop the launch. I felt, personally, that management was under a lot of pressure to launch, and that they made a very tough decision, but I didn't agree with it. One of my colleagues that was in the meeting summed it up best. This was a meeting where the determination was to launch, and it was up to us to prove, beyond a shadow of a doubt, that it was not safe to do so. This is in total reverse to what the position usually is in a pre-flight conversation or flight readiness review. It is usually exactly opposite that. Dr. Walker, do you know the source of the pressure on management that you alluded to? Mr. Boisjoli, well, the comments made over the net is what I felt. I can't speak for them, but I felt it. I felt the tone of the meeting exactly as I summed up, that we were being put in a position to prove that we should not launch, rather than being in the position and prove that we had enough data to launch. And I felt that was very real. Dr. Walker, these were the comments from the NASA people at Marshall and at Kennedy Space Center? Mr. Boisjoli, yes. Dr. Feynman, I take it you were trying to find proof that the seal would fail. Mr. Boisjoli, yes. Dr. Feynman, and of course you couldn't, because 5 of them didn't. And if you had proved that they would have all failed, you would have found yourself incorrect, because 5 of them didn't fail. Mr. Boisjoli, that is right. I was very concerned that the cold temperatures would change that timing and put us in another regime, and that was the whole basis of my fighting that night. As appears from the foregoing, after the discussion between Morton Thiokol management and the engineers, a final management review was conducted by Mason, Lund, Kilminster, and Wiggins. Lund and Mason recall this review as an unemotional, rational discussion of the engineering facts as they knew them at that time. Differences of opinion as to the impact of those facts, however, had to be resolved as a judgment call, and therefore a management decision. The testimony of Lund, taken by Commission staff investigators, is as follows. Mr. Lund, we tried to have the telecon, as I remember it was about 6 o'clock Mountain Standard Time, but we didn't quite get things in order, and we started transmitting charts down to Marshall around 6 o'clock or 6:30, something like that, and we were making charts in real time and seeing the data, and we were discussing them with the Marshall folks who went along. We finally got all the charts in, and when we got all the charts in, I stood at the board and tried to draw the conclusions that we had out of the charts that had been presented, and we came up with a conclusions chart and said that we didn't feel like it was a wise thing to fly. Question. What were some of the conclusions? Mr. Lund, I had better look at the chart. Well, we were concerned that the temperature was going to be lower than the 50 or 53 that had flown the previous January, and we had experienced some blow-by, so we were concerned about that. And although the erosion on the O-rings, and it wasn't critical, that, there had obviously been some little puff go through. It had been caught. There was no real extensive erosion of the O-ring, so that wasn't a major concern. But we said, we just don't know how much further we can go below the 51 or 53 degrees or whatever it was. So we were concerned with the unknown. And we presented that to Marshall, and that rationale was rejected. They said that they didn't accept that rationale, and they would like us to consider some other thoughts that they had had. Mr. Malloy said he did not accept that, and Mr. Hardy said he was appalled that we would make such a recommendation. And that made me ponder of what I had missed, and so we said, what did we miss? And Mr. Malloy said, well, I would like you to consider these other thoughts that we have down here. And he presented a very strong and forthright rationale of what they thought was going on in that joint, and how they thought that the thing was happening. And they said, we'd like you to consider that, when they had some thoughts that we had not considered. So after the discussion with Mr. Malloy, and he presented that, we said, well, let's ponder that a little bit. So we went offline to talk about what we... Question. Who requested to go offline? Mr. Lund. I guess it was Joe Kilminster. And so we went offline on the telecon, so we could have a roundtable discussion here. Question. Who were the management people that were there? Mr. Lund: Jerry Mason, Cal Wiggins, Joe, I, manager of engineering design, the manager of applied mechanics, on the chart. Before the Commission on February 25, 1986, Mr. Lund testified as follows regarding why he changed his position on launching Challenger during the Management Caucus when he was asked by Mr. Mason to take off his engineering hat and put on his management hat. Chairman Rogers: How do you explain the fact that you seemed to change your mind when you changed your hat? Mr. Lund: I guess we have got to go back a little further in the conversation than that. We have dealt with Marshall for a long time and have always been in the position of defending our position to make sure that we were ready to fly, and I guess I didn't realize until after that meeting, and after several days, that we had absolutely changed our position from what we had been before. But that evening, I guess I had never had those kinds of things come from the people at Marshall. We had to prove to them that we weren't ready, and so we got ourselves in the thought process that we were trying to find some way to prove to them that it wouldn't work, and we were unable to do that. We couldn't prove absolutely that the motor wouldn't work. Chairman Rogers: In other words, you honestly believed that you had a duty to prove that it would not work? Mr. Lund: Well, that is kind of the mode we got ourselves into that evening. It seems like we have always been in the opposite mode. I should have detected that, but I did not. But the roles kind of switched. Supplemental testimony of Mr. Mason obtained in a Commission staff interview is as follows. Question: Do you recall Mr. Hardy and Mr. Malloy's comments after Mr. Kilminster had got done, or Mr. Lund got done, presenting the charts? They had some comments. Do you recall? Mr. Mason: Oh yes, it was over and over. Hardy said that I'm appalled at your recommendation. Question: Well, did Mr. Hardy's appalled remark and Mr. Malloy's can't launch, we won't be able to launch until April remark, how did that affect your thinking and affect your decision? Mr. Mason: My personal thinking, it didn't make that much difference. And the comments that they made, in my view, probably had got more reaction from the engineers at the lower level than they would from the managers, because we deal with people and managers all the time. Mr. McDonald indicated that during the period of the internal Morton Thiokol caucus, he continued to argue for delay with Malloy, challenging, among other things, the rationale that the rocket motor was qualified down to 40 degrees Fahrenheit. Present were Reinertz, Jack Buchanan, the manager of Morton Thiokol Launch Support Services at Kennedy, and Cecil Houston. McDonald's testimony described that conversation. Mr. McDonald: While they were offline, reevaluating or reassessing this data, I got into a dialogue with the NASA people about such things as qualification and launch commit criteria. The comment I made was, is it my understanding that the motor was supposedly qualified to 40 to 90 degrees? I've only been on the program less than 3 years, but I don't believe it was. I don't believe that all of those systems, elements, and subsystems were qualified to that temperature. And Mr. Malloy said, well, 40 degrees is propellant mean bulk temperature, and we're well within that. That is a requirement. We're at 55 degrees for that, and that the other elements can be below that. That as long as we don't fall out of the propellant mean bulk temperature. I told him I thought that was asinine, because you could expose that large solid rocket motor to extremely low temperatures. I don't care if it's 100 below zero for several hours, with that massive amount of propellant, which is a great insulator, and not change the propellant mean bulk temperature but only a few degrees. And I don't think the spec really meant that. But that was my interpretation, because I had been working quite a bit on the filament wound case solid rocket motor. It was my impression that the qualification temperature was 40 to 90, and I knew everything wasn't qualified to that temperature, in my opinion. But we were trying to qualify that case itself at 40 to 90 degrees for the filament wound case. I then said, I may be naive about what generates launch commit criteria, but it was my impression that launch commit criteria was based upon whatever the lowest temperature or whatever loads or whatever environment was imposed on any element or subsystem of the shuttle. And if you are operating outside of those, no matter which one it was, then you had violated some launch commit criteria. That was my impression of what that was. And I still didn't understand how NASA could accept a recommendation to fly below 40 degrees. I could see why they took issue with the 53, but I could never see why they would have accepted a recommendation below 40 degrees, even though I didn't agree that the motor was fully qualified to 40. I made the statement that if we're wrong and something goes wrong on this flight, I wouldn't want to have to be the person to stand up in front of the Board of Inquiry and say that I went ahead and told them to go ahead and fly this thing outside what the motor was qualified to. I made that very statement. Mr. Malloy's recollections of these discussions are as follows. Mr. Malloy: Mr. Kilminster then requested an off-net caucus. It has been suggested, implied, or stated that we directed Thiokol to go reconsider these data. That is not true. Thiokol asked for a caucus so that they could consider the discussions that had ensued and the comments that Mr. Hardy and I and others had made. That caucus, as has been stated, was going to start at that point, and Mr. MacDonald interjected into the teleconference. At that point, he made the first comment that he had made during the entire teleconference. Mr. MacDonald testified for quite a while yesterday about his thoughts on this, but he did not say any of them until this point. At that point, he stated that he thought what George Hardy said was a very important consideration, and that consideration was, and he asked Mr. Kilminster to be sure and consider the comment made by George Hardy during the course of the discussions, that the concerns expressed were for primary O-ring blow-by, and that the secondary O-ring was in a position to seal during the time of blow-by and would do so before significant joint rotation had occurred. They then went into their caucus, having asked for 5 minutes. Mr. Hotz: It figures quite prominently in the discussion that you were quoted as saying, "Do you expect us to wait till April to launch?" Mr. Malloy: Yes, sir. Dr. Walker: Is that an accurate statement or not? Mr. Malloy: It is certainly a statement that is out of context. And the way I read the quote, sir, and I have seen it many times, too many times, the quote I read was, "My God, Thiokol, when do you want me to launch? Next April?" Mr. MacDonald testified to another quote that says, "You guys are generating new launch commit criteria." Now, both of those, I think, kind of go together, and that is what I'm saying. I don't know whether that occurred during the caucus or subsequent to. I just simply can't remember that. Mr. Hotz: Well, never mind the timing. Mr. Malloy: Well, yes, sir, I'm going to answer your question now. I think those quotes derive from a single thought that may have been expressed by me using some of those words. I have not yet encountered anyone other than those at KSC who heard those words, so I don't believe they were transmitted over the net. The total context, I think, in which those words may have been used is, there are currently no launch commit criteria, LCC, for joint temperature. What you are proposing to do is to generate a new launch commit criteria on the eve of launch, after we have successfully flown with the existing launch commit criteria 24 previous times. With this LCC, that is, do not launch with a temperature greater than 53 degrees, we may not be able to launch until next April. We need to consider this carefully before we jump to any conclusions. It's all in the context, again, with challenging your interpretation of the data. What does it mean, and is it logical? Is it truly logical that we really have a system that has to be 53 degrees to fly? At approximately 11 p.m. Eastern Standard Time, the Thiokol NASA teleconference resumed, the Thiokol management stating that they had reassessed the problem, that the temperature effects were a concern, but that the data were admittedly inconclusive. Kilminster read the rationale recommending launch and stated that that was Morton Thiokol's recommendation. Hardy requested that it be sent in writing by telefax both to Kennedy and to Marshall, and it was. The testimony of Malloy and Hardy regarding the remainder of the teleconference and their rationale for recommending launch follows. Mr. Malloy: Okay, sir. At the completion of the caucus, of course, Mr. Kilminster came back on the loop and stated they had assessed all the data and considered the discussions that had ensued for the past couple of hours and the discussions that occurred during their caucus. Chairman Rogers: Was it a couple of hours? Mr. Malloy: Yes, sir. We started at 8:45, and I believe it was probably 11 o'clock before he came back on the loop. It was a long discussion. And I must emphasize that I had no knowledge of what interchange occurred during the caucus at Thiokol, because all sites were on mute. We were on mute at KSC. No communications occurred between myself and Mr. Hardy at Huntsville, nor did any communication occur between KSC and Thiokol during that caucus. After Mr. Kilminster made that recommendation, Mr. Reinartz then asked if there were any further comments, and to my recollection there were none. There were no further comments made. I then asked Mr. Kilminster to send me a copy of his flight readiness rationale and recommendation. The conference was then terminated at approximately 11:15. I have no knowledge of, as has been testified, of Mr. MacDonald being asked to sign that documentation. That would have been unusual, because Mr. Kilminster signs all flight readiness documentation. Now, after the teleconference was complete, Mr. MacDonald informed Mr. Reinartz and me that if the Thiokol engineering concern for the effect of cold was not sufficient cause to recommend not launching, there were two other considerations: launch pad ice and recovery area weather. I stated that launch pad ice had been considered by mission management team. Chairman Rogers: Excuse me, could you identify that discussion, where that took place? Mr. Malloy: That was after the teleconference was completed, after Mr. Kilminster made his recommendation, after Mr. Reinartz asked are there any other comments. There were no other comments on the telecon from anyone. I stated that launch pad ice had been considered by the mission management team before deciding to proceed, and that a further periodic monitoring of that condition was planned. I further stated that I had been made aware of the recovery area weather previously and planned to place a call to Mr. Aldrich and advise him that the weather in the recovery area exceeded the launch commit criteria. So I stated earlier, when you asked what were the launch commit criteria, one of them was that the recovery area weather has limitations on it. The report we had, that Mr. MacDonald confirmed, was that we were outside of those limits. Now, I must point out that that is not a hard launch commit criteria. That is an advisory call, and the LCC so states that. It does require that we discuss the condition. So, at about 11:30 p.m., Mr. Cecil Houston established a teleconference with Mr. Aldrich and Mr. Sestile at KSC. I informed Mr. Aldrich that the weather in the recovery area could preclude immediate recovery of the SRBs, since the ships were in a survival mode and they were moving back toward Cape Kennedy at about 3 knots, and the estimate provided to us by Mr. Sestile was that they would be probably 40 miles from the SRB impact area at the time of launch, at 9:38, and then continuing at 3 knots, it was going to be some period of time before they could get back and locate the boosters. The concern I had for that was not loss of the total booster, but loss of the main parachutes for the booster, which are separated at water impact, and loss of the frustum of the boosters, which has the drogue parachute on it, which comes down separately, because with the 50-knot winds we had out there, and with the kind of sea states that we had, by the time the recovery ships got back out there, there was little probability of being able to recover those. I informed Mr. Aldrich of that, and he decided to proceed with the launch after that information. I did not discuss with Mr. Aldrich the conversations that we had just completed with Morton Thiokol. Chairman Rogers: Could you explain why? Mr. Malloy: Yes, sir. At that time, and I still consider it today, that was a Level 3 issue. Level 3 being an SRB element or an external tank element, or Space Shuttle main engine element or an orbiter. There was no violation of launch commit criteria. There was no waiver required in my judgment at that time, and still today. And we work many problems at the orbiter and the SRB and the external tank level that never get communicated to Mr. Aldrich or Mr. Moore. It was clearly a Level 3 issue that had been resolved. There were 27 full-scale seal tests with an O-ring groove damage tolerances, damage in the grooves and damage tolerance on O-rings, and then there were 2 cold gas tests, and these data were presented on the night of the 27th. All of that was at ambient temperature. And then we did discuss what is a development qualification motor experience range, and that is shown on the chart. We had experience everywhere from 40 to 85 degrees. There then were data presented on 2 cold gas tests at 30 degrees, where the O-ring was pressurized at the motor pressurization rate at 30 degrees, which would indicate that an O-ring would operate before joint rotation at 30 degrees. Dr. Ride: Was that actually in a joint? Mr. Malloy: No, it is not. It is a full-scale O-ring, full-scale groove, in a scaled test device, where the pressurized rate on that O-ring is 0 to 900 pounds per square inch, in 60 milliseconds at a temperature of 30 degrees. Dr. Walker: You would say then the O-ring was qualified to a temperature of 30 degrees? Would that be an accurate statement? Mr. Malloy: The day that we were looking at it, on the 27th, these 2 tests that we did indicated that it would perform at 30 degrees under the motor pressurization rate before the joint rotated. Dr. Walker: What about, let's consider, the putty and the O-ring, because that is really the system that responds to the pressure surge. What temperature was the putty O-ring system qualified to? Mr. Malloy: The lowest that I'm aware of, and we're still flushing this out because this is kind of what we talked about on the 27th, but the lowest that I'm aware of is the 40-degree test on one of the development motors. Dr. Walker: And of course during those tests the putty was modified before the test. The putty was not just laid up and then the seal made. The putty was then smoothed out, and some attempt was made to remove the volcanoes, I think. Mr. Malloy: Because the horizontal assembly caused that. Now, there's one other significant point on this chart that we did discuss, that we didn't have the quantities on the 27th, and I mentioned this earlier. We have 150 case segment proof tests, with a large number of joints, with a simulation of a cold O-ring. That is the 90 durometer, with a .275, and that was at about 35 degrees. So those are the certification data that we kind of discussed, all of which we didn't discuss. The 2 cold gas tests we did, the segment proof tests we did, the development and qualification motor test we did, as a basis for understanding what we could expect to happen at colder temperatures on the joints. Mr. Hardy testified as follows. Mr. Hardy: At the teleconference on the evening of January 27, 1986, Thiokol engineering personnel in Utah reviewed charts that had been data-faxed to Huntsville and KSC participants just prior to the beginning of the conference. Now, I am not going to repeat a lot of what you have already heard, but I will give you some of my views on the whole matter. The presentations were professional in nature. There were numerous questions and answers. There was a discussion of various data and points raised by individuals at Thiokol or at Marshall or at Kennedy. I think it was a rather full discussion. There were some 14 charts presented, and as has been mentioned earlier, we spent about 2.5 hours reviewing this. To my knowledge, anyone who desired to make a point, ask a question, or express a view was in no way restrained from doing so. As others have mentioned, I have heard this particular teleconference characterized as a heated discussion. I acknowledge that there were penetrating questions that were asked, I think, from all people involved. There were various points of view and an interpretation of the data that was exchanged. The discussion was not, in my view, uncharacteristic of discussions on many flight readiness issues on many previous occasions. Thiokol Engineering concluded their presentation with recommendation that the launch time be determined consistent with flight experience to date, and that is the launch with the O-ring temperatures at or greater than 53 degrees Fahrenheit. Mr. Kilminster at Thiokol stated, to best of my recollection, that with that engineering assessment, he recommended we not launch on Tuesday morning as scheduled. After some short discussion, Mr. Malloy at KSC summarized his assessment of the data and his rationale with that data, and I think he has testified to that. Mr. Reinertz, who was at KSC, asked me for comment, and I stated I was somewhat appalled, and that was referring specifically to some of the data or the interpretation of some of the data that Thiokol had presented with respect to its influence on the Joint SEAL performance relative to the issue under discussion, which specifically was the possibility that the primary SEAL may take longer to actuate and therefore to blow by the primary SEAL. The blow-by of the primary SEAL may be longer, and I am going to elaborate on that a little further in this statement. And then I went on to say that I supported the assessment of data presented essentially as summarized by Mr. Malloy, but I would not recommend launch over Thiokol's objections. Somewhere about this time, Mr. Kilminster at Utah stated that he wanted to go off the loop to caucus for about 5 minutes. I believe at this point Mr. McDonald, the senior Thiokol representative at KSC for this launch, suggested to Mr. Kilminster that he consider a point that I think I had made earlier, that the secondary O-ring is in the proper position to seal if blow-by of the primary O-ring occurred. I clearly interpreted this as a somewhat positive statement of supporting rationale for launch. The status of the caucus by Thiokol lasted some 30-35 minutes. At Huntsville, during this Thiokol caucus, we continued to discuss the data presented. We were off the loop. We were on mute. We were around a table in small groups. It was not an organized type discussion. But I did take that opportunity to discuss my assessment and understanding of the data with several of my key advisors, and none of us had any disagreement or differences in our interpretation of what we believed the data was telling us with regard to the primary issue at hand. When Thiokol came back online, Mr. Kilminster reviewed rationale that supported proceeding with the launch and so recommended. Mr. Reinertz asked if anyone in the loop had a different position or disagreed or something to that effect with the Thiokol recommendation as presented by Mr. Kilminster. There were no dissenting responses. The telecon was terminated shortly after, and I have no knowledge of any subsequent events or discussions between personnel at KSC or at Thiokol on this matter. At about 5 a.m. on January 28th, a discussion took place among Messrs. Malloy, Lucas, and Reinertz, in which Malloy reported to Lucas only that there had been a discussion with Thiokol over their concerns about temperature effects on the O-rings, and that it had been resolved in favor of launch. The following testimony of Mr. Malloy and Dr. Lucas recount that discussion. General Kutina: Larry, let me follow through on that, and I am kind of aware of the launch decision process, and you said you made the decision at your level on this thing. If this were an airplane, an airliner, and I just had a 2-hour argument with Boeing on whether the wing was going to fall off or not, I think I would tell the pilot, at least mention it. Why didn't we escalate a decision of this importance? Mr. Malloy, I did, sir. General Katina, you did? Mr. Malloy, yes, sir. General Katina, tell me what levels above you. Mr. Malloy, as I stated earlier, Mr. Reinertz, who is my manager, was at the meeting, and on the morning, about 5 o'clock in the operations support room where we all were, I informed Dr. Lucas of the content of the discussion. General Katina, but this is not in the launch decision chain. Mr. Malloy, no, sir. Mr. Reinertz is in the launch decision chain, though. General Katina, and is he at the highest level in that chain? Mr. Malloy, no. Normally it would go from me to Mr. Reinertz to Mr. Aldrich to Mr. Moore. End of Section 9. Recording by Maria Kasper. Section 10 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 5, The Contributing Cause of the Accident, Part 3. Dr. Lucas's testimony is as follows. Chairman Rogers, would you please tell the Commission when you first heard about the problem of the O-rings and the seals, insofar as it involves Launch 51L? And I don't want you to go way back, but go back to when you first heard. I guess it was on January 27th, was it? Dr. Lucas, yes, sir. It was on the early evening of the 27th, I think about 7 p.m., when I was in my motel room along with Mr. Kingsbury. And about that time, Mr. Reinertz and Mr. Malloy came to my room and told me that they had heard that some members of Thiokol had raised a concern about the performance of the solid rocket boosters in the low temperature that was anticipated for the next day, specifically on the seals, and that they were going out to the Kennedy Space Center to engage in a telecon with the appropriate engineers back at Marshall Space Flight Center in Huntsville, and with corresponding people back at the Wasatch Division of Thiokol in Utah. And we discussed it a few moments, and I said, fine, keep me informed, let me know what happens. Chairman Rogers, and when was the next time you heard something about that? Dr. Lucas, the next time was about 5 a.m. on the following morning, when I went to the Kennedy Space Center and went to the Launch Control Center. I immediately saw Mr. Reinertz and Mr. Malloy, and asked them how the matter of the previous evening was dispositioned. Chairman Rogers, you had heard nothing at all in between? Dr. Lucas, no, sir. Chairman Rogers, so from 8 o'clock that evening until 5 o'clock in the morning you had not heard a thing? Dr. Lucas, it was about 7 o'clock, I believe, sir, but for that period of time I heard nothing in the interim. Chairman Rogers, and you heard Mr. Reinertz say he didn't think he had to notify you, or did he notify you? Dr. Lucas, he told me, as I testified when I went into the control room, that an issue had been resolved, that there were some people at Thiokol who had a concern about the weather, that had been discussed very thoroughly by the Thiokol people and by the Marshall Space Flight Center people, and it had been concluded agreeably that there was no problem, that he had a recommendation by Thiokol to launch, and our most knowledgeable people and engineering talent agreed with that. So, from my perspective, I didn't see that as an issue. Chairman Rogers, and if you had known that Thiokol engineers almost to a man opposed the flight, would that have changed your view? Dr. Lucas, I'm certain that it would. Chairman Rogers, so your testimony is the same as Mr. Hardy's. Had he known, he would not have recommended the flight be launched on that day. Dr. Lucas: I didn't make a recommendation one way or the other, but had I known that, I would have then interposed an objection, yes. Chairman Rogers: I gather you didn't tell Mr. Aldrich or Mr. Moore what Mr. Reinertz had told you. Dr. Lucas: No, sir, that is not the reporting channel. Mr. Reinertz reports directly to Mr. Aldrich. In a sense, Mr. Reinertz informs me, as the institutional manager, of the progress that he is making in implementing his program, but that I have never on any occasion reported to Mr. Aldrich. Chairman Rogers: And you had subsequent conversations with Mr. Moore and Mr. Aldrich prior to the flight, and you never mentioned what Mr. Reinertz had told you? Dr. Lucas: I did not mention what Mr. Reinertz told me because Mr. Reinertz had indicated to me there was not an issue, that we had a unanimous position between Thiokol and the Marshall Space Flight Center, and there was no issue in his judgment, nor in mine, as he explained it to me. Chairman Rogers: But had you known, your attitude would have been totally different? Dr. Lucas: Had I had the advantage at that time of the testimony that I have heard here this week, I would have had a different attitude, certainly. Chairman Rogers: In view of the fact that you were running tests to improve the joint, didn't the fact that the weather was so bad, and Reinertz had told you about the questions that had been raised by Thiokol, at least, didn't that cause you serious concern? Dr. Lucas: I would have been concerned if Thiokol had come in and said, we don't think you should launch because we've got bad weather. Chairman Rogers: Well, that's what they did, of course, at first. That is exactly what they did. You didn't know that? Dr. Lucas: I knew only that Thiokol had raised a concern. Chairman Rogers: Did you know they came and recommended against the launch, is the question. Dr. Lucas: I knew that I was told on the morning of the launch that the initial position of some members of Thiokol, and I don't know who it was, had recommended that one not launch with the temperature less than 53 degrees Fahrenheit. Chairman Rogers: And that didn't cause you enough concern so that you passed that information on to either Mr. Moore or Mr. Aldrich? Dr. Lucas: No, sir, because I was shown a document signed by Mr. Kilminster that indicated that that would not be significant, that the temperature would not be, that it would be that much lower, as I recall it. It is clear that crucial information about the O-ring damage in prior flights and about the Thiokol engineers' argument with the NASA Telecon participants never reached Jesse Moore or Arnold Aldrich, the Levels 1 and 2 program officials, or J.A. Gene Thomas, the launch director for 51L. The testimony of Aldrich describes this failure of the communication system very aptly. Dr. Feynman: Have you collected your thoughts yet on what you think is the cause, I wouldn't call it of the accident, but the lack of communication which we have seen, and which everybody is worried about from one level to another? Mr. Aldrich: Well, there were two specific breakdowns, at least, in my impression, about that situation. One is the situation that occurred the night before the launch, and leading up to the launch, where there was a significant review that has been characterized in a number of ways before the Commission and the Commission's sub-panels, and the fact that that was not passed forward. And I can only conclude what has been reported, and that is that the people responsible for that work in the solid rocket booster project at Marshall believed that the concern was not of a significance that would be required to be brought forward, because clearly the program requirements specify that critical problems should be brought forward to Level 2, and not only to Level 2, but through myself to Level 1. The second breakdown in communications, however, and one that I personally am concerned about, is the situation of the variety of reviews that were conducted last summer between the NASA Headquarters Organization and the Marshall Organization on the same technical area, and the fact that that was not brought through my office in either direction. That is, it was not worked through by the NASA Headquarters Organization, nor when the Marshall Organization brought these concerns to be reported were we involved. And I believe that is a critical breakdown in process, and I think it is also against the documented reporting channels that the program is supposed to operate to. Now, it in fact did occur in that matter. In fact, there is a third area of concern to me in the way the program has operated. There is yet one other way that could have come to me, given a different program structure. I'm sure you've had it reported to you, as it has been reported to me, that in August, or at least at some time late in the summer or early fall, the Marshall SRB project went forward to procure some additional solid rocket motor casings to be machined and new configurations for testing of the joints. Now, it turns out that the budget for that kind of work does not come through my Level 2 office. It is worked directly between the Marshall Center in NASA headquarters, and there again, had I been responsible for the budget for that sort of work, it would have to come through me, and it would have been clear that something was going on here that I ought to know about. And so there are 3 areas of breakdown. And I haven't exactly answered your question, but I have explained it in the way that I best know it, and, well, I can say a 4th thing. There was some discussion earlier about the amount of material that was or was not reported on O-ring erosion in the FRR's flight readiness reviews, and I researched the FRR back reports and also the flight anomaly reports that were forwarded to my center, to my office, by the SRB, Solid Rocket Booster Project, and as was indicated, there is a treatment of the solid rocket motor O-ring erosion, I believe, for the STS-41C FRR, which quantifies it and indicates some limited amount of concern. The next time that is mentioned, I believe it is the STS-51E FRR in January 1985 or early in February, and that indicates again a reference to it, but refers back to the 41C as the only technical data. And then, from there forward, the comment on O-ring erosion only is that there was another instance and it is not of concern. Clearly, the amount of reporting in the FRR is of concern to me, but in parallel with that, each of the flight anomalies in the STS program are required to be logged and reviewed by each of the projects, and then submitted through the Level 2 system for formal closeout. And in looking back and reviewing the anomaly closeouts that were submitted to Level 2 from the SRB project, you find that O-ring erosion was not considered to be an anomaly, and therefore it was not logged, and therefore there are not anomaly reports that progress from one flight to the other. Yet that is another way that the information could have flagged the system, and the system is set up to use that technique for flagging. But if the erosion is classified as not an anomaly, it is then in some other category, and the system did not force it in that direction. None of those are very focused answers, but they were all factors. The Commission Chairman, Mr. Rogers, then asked 4 key officials about their knowledge of the Thiokol objections to launch. Chairman Rogers: by way of a question, could I ask, did any of your gentlemen prior to launch know about the objections of Thiokol to the launch? Mr. Smith, Kennedy Space Center Director: I did not. Mr. Thomas, Launch Director: no, sir. Mr. Aldrich, Shuttle Program Director: I did not. Mr. Moore, Associate Administrator for Spaceflight: I did not. Additionally, in further testimony, J.A. Gene Thomas commented on the launch. Mr. Holtz: Mr. Thomas, you are familiar with the testimony that this commission has taken in the last several days on the relationship of temperature to the seals in the solid rocket booster? Mr. Thomas: yes, sir, I have been here all week. Mr. Hotz, is this the type of information that you feel that you should have as launch director to make a launch decision? Mr. Thomas, if you refer to the fact that the temperature according to the launch commit criteria should have been 53 degrees, as has been testified, rather than 31, yes, I expect that to be in the LCC. That is a controlling document that we use in most cases to make a decision for launch. Mr. Hotz, but you are not really very happy about not having had this information before the launch? Mr. Thomas, no, sir. I can assure you that if we had had that information, we wouldn't have launched if it hadn't been 53 degrees. Findings. 1. The Commission concluded that there was a serious flaw in the decision-making process leading up to the launch of Flight 51L. A well-structured and managed system, emphasizing safety, would have flagged the rising doubts about the solid rocket booster joint seal. Had these matters been clearly stated and emphasized in the flight readiness process, in terms reflecting the views of most of the Thiokol engineers and at least some of the Marshall engineers, it seems likely that the launch of 51L might not have occurred when it did. 2. The waiving of launch constraints appears to have been at the expense of flight safety. There was no system which made it imperative that launch constraints and waivers of launch constraints be considered by all levels of management. 3. The Commission is troubled by what appears to be a propensity of management at Marshall to contain potentially serious problems and to attempt to resolve them internally rather than communicate them forward. This tendency is altogether at odds with the need for Marshall to function as part of a system working toward successful flight missions, interfacing and communicating with the other parts of the system that work to the same end. 4. The Commission concluded that the Thiokol management reversed its position and recommended the launch of 51L at the urging of Marshall and contrary to the views of its own engineers, in order to accommodate a major customer. Chronology of events related to temperature concerns prior to launch of Challenger STS-51L. Time: 12:36 p.m. Eastern Standard Time, January 27, 1986. Key participants: NASA project managers and contractor support personnel, including Morton Thiokol. Event: Launch Scrub. Decision is made to scrub due to high crosswinds at launch site. Time: approximately 1 p.m. Eastern Standard Time. Key participants same as above. Event: Post-scrub discussion. All appropriate personnel are polled as to feasibility to launch again within 24-hour cycle, and it results in no SRB constraints for launch at 9:38 a.m. 28 January 1986. Request is made for all participants to report any constraints. Time: approximately 1 p.m. Eastern Standard Time. Key participants: Kennedy Space Center. 1. Boyd C. Brinton, Manager, Space Booster Project, MTI. 2. Lawrence O. Weir, Manager, SRM Project Office, Marshall. Morton Thiokol, Utah. 1. Arnold R. Thompson, Supervisor, Rocket Motor Cases. 2. Robert Ebeling, Manager, Ignition System and Final Assembly, SRM Project. Event: Conversation. Weir asks Brinton if Thiokol had any concerns about predicted low temperatures and about what Thiokol had said about cold temperature effects following January 1985 Flight 51C. Brinton telephones Thompson and other MTI personnel to ask them to determine if there were concerns based on predicted weather conditions. Ebeling and other engineers are notified and asked for evaluation. Time: approximately 2 p.m. Eastern Standard Time. Key participants: NASA Levels 1 and 2 management with appropriate program managers and contract personnel. 1. Jesse W. Moore, Associate Administrator, Spaceflight, NASA HQ, and Director, JSC. 2. Arnold D. Aldrich, Manager, Space Transportation Systems Program, JSC. 3. Lawrence B. Malloy, Manager, SRB Project, Marshall Space Flight Center, MSFC. 4. Dr. William Lucas, Director, MSFC. Event: Mission Management Team Meeting. Discussion is centered around the temperature at the launch facility and weather conditions predicted for launch at 9:38 a.m. on 28 January 1986. Time: approximately 2:30 p.m. Key participants: at Thiokol, Utah. 1. R. Beaujolais, SEAL Task Force, Morton Thiokol, Utah. 2. Robert Eberling, Manager, Ignition System and Final Assembly, SRM Project. Event: Beaujolais learns of cold temperatures at Cape at meeting convened by Eberling. Time: approximately 4 p.m. Eastern Standard Time. Key participants: at Kennedy Space Center. 1. Alan J. McDonald, Director, SRM Project, Morton Thiokol. 2. Carver Kennedy, Director of Vehicle Assembly Building Operations and Vice President of Space Operations at KSC. For Morton Thiokol, at Thiokol, Utah, Robert Eberling, Department Manager, Ignition System and Final Assembly SRM Project. Event: telephone conversation. McDonald receives call at Carver Kennedy's residence from Eberling, expressing concern about performance of SRB field joints at low temperatures. McDonald indicates he will call back latest temperature predictions up to launch time. Carver Kennedy calls Launch Operations Center and received latest temperature information. McDonald transmits data to Utah and indicates he will set up telecon and asks engineering to prepare. Time: approximately 5:15 p.m. Eastern Standard Time. Key participants at Kennedy Space Center. 1. Alan J. McDonald, Director, SRM Project, Morton Thiokol, Incorporated. 2. Cecil Houston, MSFC Resident Manager at KSC. Event: telephone conversation. McDonald calls Cecil Houston, informing him that Morton Thiokol Engineering had concerns regarding O-ring temperatures. Cecil Houston indicates he will set up teleconference with Marshall Space Flight Center and Morton Thiokol. Time: approximately 5:25 p.m. Eastern Standard Time. Key participants at Kennedy Space Center: Cecil Houston, MSFC Resident Manager at KSC. At Marshall Space Flight Center, Judson A. Lovingood, Deputy Manager, Shuttle Projects Office, MSFC. Event: telephone conversation. Cecil Houston calls Lovingood, informing him of the concerns of temperature on the O-rings, and asks him to establish a telecon with 1. Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC, at Kennedy. 2. Lawrence B. Malloy, Manager, SRB Project, MSFC, at Kennedy. 3. George Hardy, Deputy Director, Science and Engineering, at Marshall. 4. Thiokol Wasatch Division Personnel. Time: approximately 5:30 p.m. Eastern Standard Time. Key participants at Kennedy Space Center: Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC. At Marshall Space Flight Center, Judson A. Lovingood, Deputy Manager, Shuttle Projects Office, MSFC. Event: telephone conversation. Lovingood calls Reinertz to inform him of planned 5:45 p.m. Eastern Standard Time teleconference. Lovingood proposes that Kingsbury, Director of Science and Engineering, MSFC, participate in teleconference. Time: approximately 5:45 p.m. Eastern Standard Time. Key participants at Kennedy Space Center: Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC. At Marshall Space Flight Center, Judson A. Lovingood, Deputy Manager, Shuttle Projects Office, MSFC, plus other personnel at Kennedy, Marshall, and Thiokol, Utah. Event: First teleconference. Concerns regarding temperature effects on the O-rings are discussed. MTI is of the opinion launch should be delayed until noon or afternoon. It is decided that another telecon at 8:15 p.m. will be set up to transmit the data to all of the parties and to have more personnel involved. Lovingood recommends to Reinertz to include Lucas, Director MSFC, and Kingsbury in 8:45 p.m. conference, and to plan to go to Level 2 if MTI recommends not launching. Time: approximately 6:30 p.m. Eastern Standard Time. Key participants at Marshall Space Flight Center: Judson A. Lovingood, Deputy Manager, Shuttle Projects Office, MSFC. At Kennedy Space Center, Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC. Event: Telephone conversation. Lovingood calls Reinertz and tells him that if Thiokol persists, they should not launch. Lovingood also suggests advising Aldrich, Manager, National Transportation System, Level 2, of teleconference, to prepare him for Level 1 meeting to inform of possible recommendation to delay. Time: approximately 7 p.m. Eastern Standard Time. Key participants at Kennedy Space Center: 1. Lawrence B. Malloy, Manager, SRB Project, MSFC. 2. Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC. 3. Dr. William Lucas, Director, MSFC. 4. Jim Kingsbury, Director of Science and Engineering, MSFC. Event: Conversation. Reinertz and Malloy visit Lucas and Kingsbury in their motel rooms to inform them of Thiokol concern and planned teleconference. Time: approximately 8:45 p.m. Eastern Standard Time. Key participants at Morton Thiokol, Utah: 1. Gerald Mason, Senior Vice President, Wasatch Operations. 2. Calvin Wiggins, Vice President and General Manager, Space Division, Wasatch. 3. Joe C. Kilminster, Vice President, Space Booster Programs, Wasatch. 4. Robert K. Lund, Vice President, Engineering. 5. Roger Beaujolais, Member, SEAL Task Force. 6. Arnold R. Thompson, Supervisor, Rocket Motor Cases. At Kennedy Space Center: 1. Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC. 2. Lawrence B. Malloy, Manager, SRB Project, MSFC. 3. Alan J. McDonald, Director, SRM Project, MTI. At Marshall Space Flight Center: 1. George B. Hardy, Deputy Director, Science and Engineering. 2. Judson A. Lovingood, Deputy Manager, Shuttle Project Office. 3. Ben Powers, Engineering Structures and Propulsion. Plus other personnel, see table, page 111. Event: Second teleconference. Charts present a history of the O-ring erosion and blow-by for the primary seal in the field joints, including results of subscale tests, previous flights, and static tests of solid rocket motors. The data shows that the timing function of the O-rings will be slower due to lower temperatures, and that the worst blow-by occurred on SRM-15, STS-51C, in January 1985, with O-ring temperatures of 53 degrees Fahrenheit. Recommendation by Thiokol, Lund, is not to fly STS-51L, SAM-25, until the temperature of the O-ring reached 53 degrees Fahrenheit, which was the lowest temperature of any previous flight. Malloy asks for recommendation from Kilminster. Kilminster states that based upon the engineering recommendation, he cannot recommend launch. Hardy is reported by both MacDonald and Boisjoli to have said he is appalled by Thiokol's recommendation. Reinertz comments that he is under the impression that SRM is qualified from 40 degrees Fahrenheit to 90 degrees Fahrenheit. NASA personnel challenge conclusions and recommendations. Kilminster asks for 5 minutes off. Time, approximately 10:30 p.m. Eastern Standard Time. Key participants, Thiokol personnel. 1. Gerald Mason, Senior Vice President, Wasatch Operations. 2. Joe C. Kilminster, Vice President, Space Booster Program. 3. Calvin Wiggins, Vice President and General Manager, Space Division. 4. Robert K. Lund, Vice President, Engineering. 5. Arnold R. Thompson, Supervisor, Rocket Motor Cases. 6. Roger Boisjoli, Member, SEAL Task Force. 7. Brian Russell, Special Projects SRM Program Office. 8. Robert Ebeling, Manager, Ignition System and Final Assembly SRM Project, plus other personnel. Event, Thiokol Caucus. Caucus continues for about 30 minutes at Thiokol, Wasatch, Utah. Major issues are 1. Temperature effects on O-ring, and 2. Erosion of the O-ring. Thompson and Boisjoli voice objections to launch. An indication is that Lund is also reluctant to launch. A final management review is conducted with only Mason, Lund, Kilminster, and Wiggins. Lund is asked to put on management hat by Mason. Final agreement is 1. There is a substantial margin to erode the primary O-ring by a factor of 3 times the previous worst case. And 2. Even if the primary O-ring does not seal, the secondary is in position and will. Time, approximately 10:30 p.m. to 11 p.m. Eastern Standard Time. Key participants at Kennedy Space Center. 1. Alan J. MacDonald, Manager, Space Booster Project, Morton Thiokol, MTI. 2. Lawrence B. Malloy, Manager, SRB Projects, MSFC. 3. Stanley R. Reinertz, Manager, Shuttle Projects, MSFC. 4. Jack Buchanan, Manager, KSC Operations for MTI. 5. Cecil Houston, MSFC Resident Manager at KSC. Event, conversation at Kennedy. MacDonald continues to argue for delay. MacDonald challenges Reinert's rationale that the SRM is qualified at 40 degrees Fahrenheit to 90 degrees Fahrenheit, and Malloy's explanation that propellant mean bulk temperatures are within specifications. Time, approximately 11 p.m. Eastern Standard Time. Key participants, same participants as 8:45 p.m. teleconference. Event, second teleconference, continued. Thiokol indicates it had reassessed. Temperature effects are concern, but data is inconclusive. Kilminster reads the rationale for recommending launch. Thiokol recommends launch. Hardy requests that Thiokol put in writing their recommendation and send it by fax to both Kennedy and Marshall. Time, approximately 11:15 to 11:30 p.m. Eastern Standard Time. Key participants at Kennedy Space Center. Alan J. MacDonald, Manager, Space Booster Project, MTI. 2. Lawrence Malloy, Manager, SRB Projects Office, MSFC. 3. Stanley R. Reinertz, Manager, Shuttle Projects Office, MSFC. 4. Jack Buchanan, Manager, KSC Operations for MTI. 5. Cecil Houston, Manager, MSFC Resident Office at KSC. Event, conversation at Kennedy. McDonald argues again for delay, asking how NASA could rationalize launching below qualification temperature. McDonald indicates if anything happened, he would not want to have to explain to Board of Inquiry. McDonald indicates he would cancel launch, since 1. O-ring problem at low temperatures, 2. Booster recovery ships heading into wind toward shore due to high seas, and 3. Icing conditions on launch pad. McDonald is told it is not his concern, and that his above concerns will be passed on in advisory capacity. Time, approximately 11:45 p.m. Eastern Standard Time. Event, telefax. Kilminster faxes Thiokol's recommendation to launch at 9:45 Mountain Standard Time, 27th January 1986, 11:45 Eastern Standard Time. Fax is signed by Kilminster. McDonald retrieves fax at KSC. Time, approximately 11:30 p.m. to 12 a.m. Eastern Standard Time. Key participants at Kennedy Space Center: 1. Lawrence B. Malloy, Manager, SRB Projects Office, MSFC. 2. Stanley R. Reinertz, Manager, Shuttle Projects, MSFC. 3. Arnold D. Aldrich, Manager, National Space Transportation System Program Office, JSC. Event, teleconference. Discussion centers around the recovery ship's activities and brief discussion of the ice issue on the launch complex area. Reinertz and Malloy place call to Aldrich. McDonald delivers fax to Jack Buchanan's office at Kennedy Space Center and overhears part of conversation. Aldrich is apparently not informed of the O-ring concerns. Time, approximately 12:01 a.m. Eastern Standard Time, January 28th. Event, Kennedy Space Center meeting breaks up. Time, approximately 1:30 to 3 a.m. Eastern Standard Time. Key participants at Kennedy Space Center: 1. Charles Stevenson, Supervisor of Ice Crew, KSC. 2. B.K. Davis, Ice Team Member, MSFC. Event, Ice Crew Inspection of Launch Pad B. Ice Crew finds large quantity of ice on fixed service structure, mobile launch platform, and pad apron, and reports conditions. Time, approximately 5 a.m. Eastern Standard Time. Key participants at Kennedy Space Center: 1. Lawrence B. Malloy, Manager, SRB Project, MSFC. 2. Dr. William Lucas, Director, MSFC. 3. Jim Kingsbury, Director of Science and Engineering, MSFC. Event, conversation. Malloy tells Lucas of Thiokol's concerns over temperature effects on O-rings and final resolution. Lucas is shown copy of Thiokol telefax. Time, approximately 7 to 9 a.m. Eastern Standard Time. Key participants at Kennedy Space Center: 1. Charles Stevenson, Supervisor of Ice Crew, KSC. 2. B.K. Davis, Ice Team Member, MSFC. Event, Ice Crew Inspection of Launch Pad B. Ice Crew inspects Launch Pad B and Challenger for ice formation. Davis measures temperatures on SRB's external tank, orbiter, and launch pad with infrared pyrometer. Left-hand SRB appears to be about 25 degrees Fahrenheit, and right-hand SRB appears to be about 8 degrees Fahrenheit near the aft region. Ice Crew is not concerned since there is no launch commit criteria on surface temperatures and does not report. Crew reports patches of sheet ice on lower segment and skirt of left solid rocket booster. Time, approximately 8 a.m. Eastern Standard Time. Key participants at Marshall Space Flight Center: 1. Judson A. Lovingood, Deputy Manager, Shuttle Projects Office, MSFC. 2. Jack Lee, Deputy Director, MSFC. Event, conversation. Lovingood informs Lee of previous night's discussions. He indicates that Thiokol had at first recommended not launching, but then, after Wasatch Conference, recommended launching. He also informs Lee that Thiokol is providing in writing their recommendation for launch. Time, approximately 9 a.m. Eastern Standard Time. Key participants: NASA Level 1 and Level 2 management with appropriate project managers and contract personnel. Event: Mission Management Team meeting. Ice conditions at Launch Complex are discussed. There is no apparent discussion of temperature effects on O-ring seal. Time, approximately 10:30 a.m. Eastern Standard Time. Key participants at Kennedy Space Center: 1. Charles Stevenson, Supervisor of Ice Crew. 2. B.K. Davis, Ice Team Member. Event: Ice Crew inspection of Launchpad B. Ice Crew inspects Launchpad B for third time. Crew removes ice from water troughs, returns to Launch Control Center at T-20 minutes, reports conditions to Mission Management Team, including fact that ice is still on left solid rocket booster. Time, 11:38 a.m. Eastern Standard Time. Event, launch. Challenger, STS-51L, is launched. End of Section 10. Recording by Maria Kasper. Section 11 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 5, The Contributing Cause of the Accident, Part 4. Ambiguities in the decision-making process. During the night and early morning of January 28th, another problem was developing due to the extreme cold weather, predicted to be in the low 20s for approximately 11 hours. Reaction control system heaters on the orbiter were activated, and the solid rocket booster recovery batteries were checked and found to be functioning within specifications. There were no serious concerns regarding the external tank. The freeze protection plan for the launch pad was implemented, but the results were not what had been anticipated. The freeze protection plan usually involves completely draining the water system. However, this was not possible because of the imminent launch of 51L. In order to prevent pipes from freezing, a decision was made to allow water to run slowly from the system. This had never been done before, and the combination of freezing temperatures and stiff winds caused large amounts of ice to form below the 240-foot level of the fixed service structure, including the access to the crew emergency egress slide wire baskets. Ice was also forming in the water trays beneath the vehicle. These conditions were first identified by the ice team at approximately 2 a.m. on January 28th and were assessed by management and engineering throughout the night, culminating with a mission management team meeting at 9 a.m. At this meeting, representatives for the orbiter prime contractor, Rockwell International, expressed their concern about what effects the ice might have on the orbiter during launch. Rockwell had been alerted about the icing conditions during the early morning and was working on the problem at its Downey, California facility. During Commission's hearings, the president of Rockwell's Space Transportation Systems Division, Dr. Rocco Petrone, and two of his vice presidents, Robert Glacier and Martin Ciaffoletti, all described the work done regarding the ice conditions and the Rockwell position at the 9 a.m. meeting with regard to launch. Dr. Petrone had arrived at Kennedy on Friday, January 24th. On Monday the 27th, he left to return to Rockwell's facility in California, but Glacier and Cifolletti remained at Kennedy. Dr. Petrone testified that he first heard about the ice at 4 a.m. Pacific Standard Time. He explained what followed. I had gotten up and went to the support room to support this launch. We have people monitoring consoles, and I checked in, and they told me there was a concern. And when I arrived at about 4:40 Pacific Standard Time, I was informed we were working the problem with our aerodynamicist and debris people. But very importantly, we would have to make an input to Kennedy for a meeting scheduled at 6 o'clock our time and 9 o'clock Florida time. We had approximately an hour of work to bring together. The work had been underway when I arrived and was continuing. At that time, I got on the phone with my orbiter program managers just to discuss background of where we were, how things stood, and what their concerns were locally. They described what they knew in Florida, and we also in Downey did television input, and we could see some of the ice scenes that were shown here this morning. We arrived through a series of meetings to a top-level discussion at approximately 5:30 Pacific Standard Time, from which we drew the following conclusions. Ice on the mobile launcher itself, it could be debris. We were very concerned with debris of any kind at the time of launch. With this particular ice, could it hit the orbiter? There was wind blowing from the west. That appeared not to be so, that it wouldn't hit the orbiter but would land on the mobile launcher. The second concern was what happens to that ice at the time you light your liquid fuel engines, the SSMEs, and would it throw it around and ricochet and potentially hit the orbiter? The third aspect is the one that has been discussed here of aspiration. What would happen when the large SRM solid rocket motors ignite and in effect suck in air, referred to as aspiration, and ice additionally would come down, how much unknown. The prime thing we were concerned about was the unknown baseline. We had not launched in conditions of that nature, and we just felt we had an unknown. I then called my program managers over in Florida at 5:45 Pacific Standard Time and said we could not recommend launching from here from what we could see. We think the tiles would be endangered, and we had a very short conversation. We had a meeting to go through, and I said, let's make sure that NASA understands that Rockwell feels it is not safe to launch, and that was the end of my conversation. Mr. Glacier, who was at Kennedy, came to the center at approximately 7:45 a.m. Eastern Standard Time. He conferred with Rockwell's chief engineer, as well as the vice president of engineering, Dr. John Peller, at Rockwell's Downey plant. At 9 a.m., after the ice debris team had reported back from the pad inspection, Glacier was asked for Rockwell's position on launch. He discussed aspiration effects, the possible ricochet of ice from the fixed service structure, and what the ice resting on the mobile launch platform would do at ignition. Glacier said he told the mission management team when it met at 9 a.m. that the ice was an unknown condition, and Rockwell was unable to predict where the ice would go or the degree of potential damage to the orbiter thermal protection system if it were struck by the ice. He testified that his recommendation to NASA was, my exact quote, and it comes in two parts. The first one was, Rockwell could not 100% assure that it is safe to fly, which I quickly changed to Rockwell cannot assure that it is safe to fly. Rockwell's other vice president at Kennedy, Martin Cifolletti, described the concern about ice in a slightly different manner. Mr. Cifolletti: similarly, I was called in and told about the problem and came into the 6 o'clock meeting, which you heard about a few minutes ago, and at the conclusion of that meeting, I spoke with Mr. Dick Kors, the Deputy Program Manager from Johnson Space Flight Center, and he asked if we could get the Downey folks to look at the falling ice and how it might reverse toward the vehicle, and also did we have any information on aspiration effects. So I did call back to Downey and got the John Peller folks working on that problem, and they did, as you saw from Charlie Stevenson's sketches, predict that the ice would travel only about halfway to the vehicle, free-falling ice carried by the winds. So we felt that the ice was not a problem. However, it would land on the mobile launch platform. That we considered a problem. We also investigated the aspiration database we had, and we had seen the aspiration effect on previous launches where things were pulled into the solid rocket booster hole after ignition, but we had never seen anything out as far as the fixed surface tower. So we felt, in fact, it was an unknown. We did not have the database to operate from an aspiration effect. At the 9 o'clock meeting, I was asked by Arnie Aldrich, the program manager, to give him the results of our analysis, and I essentially told him what I just told you, and felt that we did not have a sufficient database to absolutely assure that nothing would strike the vehicle, and so we could not lend our 100% credence, if you will, to the fact that it was safe to fly. I said I could not predict the trajectory that the ice on the mobile launch platform would take at SRB ignition. Chairman Rogers: But I think NASA's position probably would be that they thought that you were satisfied with the launch. Did you convey to them in a way that they were able to understand that you were not approving the launch from your standpoint? Mr. Cifolletti: I felt that by telling them we did not have sufficient database and could not analyze the trajectory of the ice, I felt he understood that Rockwell was not giving a positive indication that we were for the launch. After Cifolletti's testimony at the commission hearings, Dr. Patrone was pressed for a more detailed description of Rockwell's launch recommendation. General Kutina: Dr. Patrone, you've got a lot more experience than I have in this business, but the few launch conferences that I have been on, the question is very simple. Are you go or are you no-go for launch? And maybe isn't an answer. I hear all kinds of qualifications and cautions and considerations here. Did someone ask you, are you go or no-go? Was that not asked? Dr. Patrone: At this particular meeting, as far as, and I was not in Florida, so I cannot answer that, it had not been done at earlier meetings. This was a technical evaluation of a series of problems, and we talked about debris hitting the thermal protection system and the tiles, and the long series of reviews that we had done that morning, and all led us to a conclusion that they were not safe to fly, and we transmitted that to program managers along with the technical evaluation quickly of why we had arrived at that. So much of it is how the question gets raised, because earlier we had aspiration work, ricochet work, a number of things which we did, and then we came up with our recommendation. Chairman Rogers: And your recommendation now, you say it was unsafe to fly? Dr. Patrone: Correct, sir. Two things are apparent from the Rockwell testimony. First, Rockwell did not feel it had sufficient time to research and resolve the ice on the pad problem. Second, even though there was considerable discussion about ice, Rockwell's position on launch, described above, was not clearly communicated to NASA officials in the launch decision chain during the hours preceding 51L's launch. At a meeting with Commission investigators on March 4, 1986, at Kennedy, Horace Lamberth, NASA Director of Shuttle Engineering, said he did not interpret Rockwell's position at the 9 a.m. Mission Management Team meeting on January 28 as being no-go. Lamberth said the language used by Rockwell was, "We can't give you 100% assurance," but there was no feeling in his mind that Rockwell was voicing a no-go recommendation. It just didn't come across as the normal Rockwell no-go safety of flight issues come across. This conclusion is confirmed in part by an interview of Dr. John Peller, Rockwell's Vice President of Engineering, who was assigned the ice problem early Tuesday morning. Dr. Peller, in describing a telephone conversation with the Johnson Director of Engineering, Tom Mosier, stated, Dr. Peller, "That was a call from Tom Mosier to me in which he asked again to understand my concerns, and I just repeated the same concerns. And he asked, did I think it was likely that the vehicle would take safety-critical damage? And I said, from the possibility that the vehicle would take safety-critical damage, I said, there is a probability in a sense that it was probably an unlikely event, but I could not prove that it wouldn't happen. I never used the words no-go for launch. I did use the words that we cannot prove it is safe. And that's normally what we are asked to do. We were unable to do that in this particular case, although it was a strange case that we normally don't get involved in." Arnold Aldrich, NASA Mission Management Team Leader, described NASA's view of the ice situation and his recollection of Rockwell's position. He said that on Tuesday morning, the mission management team did a detailed analysis of the ice on the fixed service structure. Representatives from the ICE team, Rockwell, and the directors of engineering, Horace Lamberth, and the orbiter project, Richard Colonna, all considered the problem. Aldrich reported this discussion as follows. Following the discussion of the acceptability of the ice threat to the orbiter, based upon the conditions described in detail of the fixed service structure and some of what you've seen here portrayed well this morning, I asked the NASA managers involved for their position on what they felt about the threat of that to the orbiter. Mr. Lamberth reported that KSC, Kennedy Space Center Engineering, had calculated the trajectories, as you've heard, of the falling ice from the fixed service structure's east side with current 10-knot winds at 300 degrees, and predicted that none of this ice would contact the orbiter during its ignition or launch sequence, and that their calculations even showed that if the wind would increase to 15 knots, we still would not have contact with the orbiter. Mr. Colonna, orbiter project manager, reported that similar calculations had been performed in Houston by the mission evaluation team there. They concurred in this assessment. And further, Mr. Colonna stated, even if these calculations were significantly in error, that it was their belief that falling ice from the fixed service structure, if it were in fact to make its way to the orbiter, it would only be the most lightweight ice that was in that falling stream, and it would impact the orbiter at a very oblique angle. Impacts of this type would have very low probability of causing any serious damage to the orbiter, and at most would result in post-flight turnaround repairs. At this point, I placed a phone call to Mr. Mosier that I had previously mentioned, Director of Engineering at the Johnson Space Center, who was in the mission evaluation room, and he confirmed the detailed agreement with Mr. Lamberth's and Mr. Colonna's position. And both Mr. Lamberth and Mr. Colonna reported that their assessment was that the time it took for the ice to fall, to hit the orbiter and to rebound, and the location of the fixed service structure on the mobile launch platform would not cause that ice, in their view, to be a concern to rebound and come up and impact the rear end of the orbiter. Following these discussions, I asked for a position regarding proceeding with the launch. Mr. Colonna, Mr. Lamberth, and Mr. Mosier all recommended that we proceed. At that time, I also polled Mr. Robert Glacier, the Vice President, Orbiter Project Manager, Rockwell International STS Division, and Mr. Marty Cifolletti, Shuttle Integration Project Manager, Rockwell International STS Division. Mr. Glacier stated, and he had been listening to this entire discussion, and had not been directly involved with it, but had been party to it this whole time. His statement to me, as best I can reconstruct it, to report to you at this time, was that while he did not disagree with the analysis that Johnson Space Center and KSC had reported, that they would not give an unqualified go for launch, as ice on the launch complex was a condition which had not previously been experienced, and thus this posed a small, additional, but unquantifiable risk. Mr. Glacier did not ask or insist that we not launch, however. At the conclusion of the above review, I felt reasonably confident that the launch should proceed. In addition to Rockwell's input, Mr. Aldrich also had reports from other contractors and the ice, frost, and debris team at the 9 o'clock session. Ice on the vehicle assembly appeared to be of no concern. Sheet ice in the noise suppression trays had been broken up and removed. As previously noted, the ice team reported that there was ice on the fixed service structure between 95 feet above ground and 215 feet. No ice above 255 feet. The north and west sides had large amounts of ice and icicles. The final assessment was made that the ice on the fixed service structure would not strike or damage the orbiter tiles or the vehicle assembly during ignition or ascent, owing to the considerable horizontal distance between the service structure and the vehicle assembly. The decision was made to launch pending a final ice team review of the launch complex in order to assess any changes in the situation. This inspection was completed following the mission management team meeting, and the ice team report indicated no significant change. Findings. The Commission is concerned about 3 aspects of the ice on the pad issue. 1. An analysis of all the testimony and interviews establishes that Rockwell's recommendation on the launch was ambiguous. The Commission finds it difficult, as did Mr. Aldrich, to conclude that there was a no-launch recommendation. Moreover, all parties were asked specifically to contact Aldrich or Moore about launch objections due to weather. Rockwell made no phone calls or further objections to Aldrich or other NASA officials after the 9 o'clock mission management team meeting and subsequent to the resumption of the countdown. 2. The Commission is also concerned about the NASA response to the Rockwell position at the 9 a.m. meeting. While it is understood that decisions have to be made in launching a shuttle, the Commission is not convinced that Levels 1 and 2 appropriately considered Rockwell's concerns about the ice. However ambiguous Rockwell's position was, it is clear that they did tell NASA that the ice was an unknown condition. Given the extent of the ice on the pad, see photos pages 112 and 113, the admitted unknown effect of the solid rocket motor and Space Shuttle main engine's ignition on the ice, as well as the fact that debris striking the orbiter was a potential flight safety hazard, the Commission finds the decision to launch questionable under those circumstances. In this situation, NASA appeared to be requiring a contractor to prove that it was not safe to launch, rather than proving it was safe. Nevertheless, the Commission has determined that the ice was not a cause of the 51L accident, and does not conclude that NASA's decision to launch specifically overrode a no-launch recommendation by an element contractor. 3. The Commission concluded that the freeze protection plan for Launch Pad 39B was inadequate. The Commission believes that the severe cold and presence of so much ice on the fixed service structure made it inadvisable to launch on the morning of January 28th, and that margins of safety were whittled down too far. Additionally, access to the crew emergency slide wire baskets was hazardous due to the ice conditions. Had the crew been required to evacuate the orbiter on the launch pad, they would have been running on an icy surface. The Commission believes the crew should have been made aware of the situation, and based on the seriousness of the condition, greater consideration should have been given to delaying the launch. End of Section 11. Recording by Maria Kasper.
Section 12 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by jmichl, Sussex, Wisconsin, USA, February 2021. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident, Section 12. Chapter 6. An Accident Rooted in History. Early Design. The Space Shuttle's solid rocket booster problem began with the faulty design of its joint and increased as both NASA and contractor management first failed to recognize it as a problem, then failed to fix it, and finally treated it as an acceptable flight risk. Morton Thiokol, Inc., the contractor, did not accept the implication of tests early in the program that the design had a serious and unanticipated flaw. NASA did not accept the judgment of its engineers that the design was unacceptable, and as the joint problems grew in number and severity, NASA minimized them in management briefings and reports. Thiokol's stated position was that, quote, "the condition is not desirable but is acceptable," end quote. Neither Thiokol nor NASA expected the rubber O-rings sealing the joints to be touched by hot gases of motor ignition, much less to be partially burned. However, as tests and then flights confirmed damage to the sealing rings, the reaction by both NASA and Thiokol was to increase the amount of damage considered acceptable. At no time did management either recommend a redesign of the joint or call for the shuttle's grounding until the problem was solved. Thiokol was selected to receive the NASA contract to design and build the solid rocket boosters on November 20, 1973. The booster was the largest solid rocket motor ever produced in the United States. It was also the first solid motor program managed by NASA's Marshall Space Flight Center in Huntsville, Alabama. Costs were the primary concern of NASA's selection board, particularly those incurred early in the program. Thiokol's three competitors were Aerojet Solid Propulsion Company, Lockheed Propulsion Company, and United Technologies. The Source Evaluation Board on the proposals rated Thiokol fourth under the Design, Development, and Verification factor, second under the Manufacturing, Refurbishment, and Product Support factor, and first under the Management factor. Thiokol received the second highest overall mission suitability score, tied with United Technologies. In a December 12, 1973 report, NASA selection officials said Thiokol's, quote, "cost advantages were substantial and consistent throughout all areas evaluated," end quote. They also singled out Thiokol's joint design for special mention. Quote, "The Thiokol motor case joints utilized dual O-rings and test ports between seals, enabling a simple leak check without pressurizing the entire motor," end quote, the officials' report said. Quote, "This innovative design feature increased reliability and decreased operations at the launch site, indicating good intention to low cost, design, development, testing, and engineering, and production. We noted that the NASA Source Selection Board's analysis of cost factors indicated that Thiokol could do a more economical job than any of the other proposers in both the development and the production phases of the program, and that, accordingly, the cost per flight to be expected from a Thiokol-built motor would be the lowest," end quote, the officials said. Quote, "We therefore concluded that any selection other than Thiokol would give rise to an additional cost of appreciable size," end quote. The selection officials said that they, quote, "found no other factors bearing upon the selection that ranked in weight with the foregoing," end quote. Cost consideration overrode any other objections, they decided. "We concluded that the main criticisms of the Thiokol proposal in the mission suitability evaluation were technical in nature, were readily correctable, and the cost to correct did not negate the sizable Thiokol cost advantage," the selection officials concluded. The cost plus award fee contract, estimated to be worth $800 million, was awarded to Thiokol. The design of the Shuttle's solid rocket booster was primarily based on the Air Force's Titan III solid rocket, one of the most reliable ever produced. Thiokol hoped to reduce new design problems, speed up the development program, and cut costs by borrowing from the Titan design. In Thiokol's solid rocket motor proposal, the rocket fuel is contained in 4 forged steel cases, which are stacked one on top of the other. The casings were connected by a circumferential tang and clevis, as were the Titans. Despite their many similarities, the Thiokol solid rocket booster and the Titan motors had some significant design differences. For example, the joints of the Titan were designed so that the insulation of one case fits tightly against the insulation of the adjacent case to form a more gas-tight fit than the Thiokol design. One O-ring bore seal was used in each Titan joint to stop any hot gas pressure that might pass by the insulation overlap. But in the Titan design, the O-ring was able but not intended to take the brunt of the combustion pressure. In contrast, the Thiokol O-rings were designed to take the brunt of the combustion pressure, with no other gas barriers present except an insulating putty. Also, the solid rocket motor joint had 2 O-rings, the second to provide a backup in case the primary seal failed. Asbestos-filled putty was used in the solid rocket motor to pack the space between the 2 case segments to prevent O-ring damage from the heat of combustion gases. Thiokol believed the putty was plastic, so when acted on by the combustion pressure at the motor's ignition, the putty flow towards the O-ring would compress the air in the gap between the putty and the primary O-ring. The compressed air, in turn, would cause the primary O-ring to extrude into the gap between the clevis and the tang, behind the primary O-ring groove, thereby sealing the opening. If the primary O-ring did not seal, the intent was that the secondary would pressurize and seal the joint by extruding into the gap behind its groove. Another difference in the solid rocket motor and the Titan was that the tang portion of the Thiokol joint was longer in order to accommodate 2 O-rings instead of 1. It was more susceptible to bending under combustion pressure than the Titan joint, as post-design tests and later flight experience demonstrated. The initial Thiokol design proposal was changed before the production motors were manufactured. Originally, the joint seal design incorporated both a face seal and a bore seal. However, the motor that was eventually used had double bore O-rings. The original bore seal face seal design was chosen because it was anticipated that it, quote, provides better redundance over a double bore ring seal, since each is controlled by different manufacturing tolerances and each responds differently during joint assembly, end quote. Because the early design incorporated tolerances similar to the Titan, and it also incorporated a face seal, Thiokol believed it possessed, quote, complete redundant seal capability, end quote. Nevertheless, as the solid rocket motor program progressed, Thiokol's, with NASA's concurrence, dropped the face bore seal design for one using a double bore seal. NASA engineers at Marshall said the original design would have required tapered pins to maintain necessary tolerances and assure enough, quote, squeeze on the face sealing O-ring. However, design analysis determined that motor ignition would create tension loads on the joint sufficient to cause the tapered pins to pop out. Solving that would have meant designing some type of pin retainers. Moreover, the rocket assembly was much easier with the dual bore seals. Because inspections and tests had to be conducted on the solid rocket motor stack, horizontal assembly was required. Thiokol engineer Howard McIntosh described this in a commission interview on April 2, 1986. Quote, we were concerned very much about the horizontal assembly that we had to do the static tests. The Titan had always been assembled vertically, and so there had never been a larger rocket motor, to our knowledge, that was assembled horizontally. End quote. Because of the extremely tight tolerances in the joints caused by horizontal assembly, McIntosh noted, quote, "We put the bore seals in there, and we opened the tolerance in the gaps slightly to accommodate that." End quote. To tighten the joint's fit and to increase the squeeze in the O-rings to compensate for the larger tolerances, Thiokol subsequently put thin metal shims between the outer walls of the tang and clevis. Another significant feature of the Thiokol design was a vent or port on the side of the motor case used after assembly to check the sealing of the O-rings. As will be noted later, this leak check eventually became a significant aspect of the O-ring erosion phenomenon. The manufacture of the O-rings themselves constituted another difference between the Titan and the Thiokol solid rocket motor. While both O-rings were Viton rubber, the Titan O-rings were molded in one piece. The solid rocket motor O-rings were made from sections of rubber O-ring material glued together. The specifications allowed 5 such joints, a number chosen arbitrarily, and the vendor routinely made repairs of voids and inclusions after getting the material supplies. Only surface inspections were performed by Thiokol and by the manufacturer. Finally, unlike the Titan, the Thiokol solid rocket motor was designed for multiple firings. To reduce program costs, each Thiokol motor case for the shuttle was to be recovered after flight and reused up to 20 times. Early tests. Thiokol began testing the solid rocket motor in the mid-1970s. One of the early important tests was a 1977 hydro burst test. Its purpose was to test the strength of the steel cases by simulating a motor firing. The case was pressurized with water to about 1 1/2 times the pressure of an ignited motor, about 1,500 pounds per square inch, to make certain the case had adequate structural margin. Also, to measure the pressure between the O-rings, engineers attached instruments to the leak test port at a segment joint. Although the test was successful in that it demonstrated the case met strength requirements, test measurements showed that, contrary to design expectations, the joint tang and inside clevis bent away from each other instead of toward each other, and by doing so, reduced, instead of increased, pressure on the O-ring in the milliseconds after ignition. This phenomena was called joint rotation. Testifying before the commission, Arnold Thompson, Thiokol's supervisor of structures, said, "We discovered that the joint was opening rather than closing, as our original analysis had indicated, and in fact it was quite a bit. I think it was up to 52 1/1000ths of an inch at that time to the primary O-ring." End quote. Thiokol reported these initial test findings to the NASA program office at Marshall. Thiokol engineers did not believe the test results really proved that joint rotation would cause significant problems, and scheduled no additional tests for the specific purpose of confirming or disproving the joint gap behavior. Design objections. Reaction from Marshall to the early solid rocket motor test results was rapid and totally opposite of Thiokol's. In a September 2, 1977 memorandum, Glenn Udy, Marshall's chief engineer of the Solid Rocket Motor Division, informed Alex McCool, director of Structures and Propulsion Laboratory, that the assembly of a developmental motor provided early indications that the Thiokol design, quote, allowed O-ring clearance. Some people believe this design deficiency must be corrected by some method, such as shimming, and perhaps design modification to the case joint for hardware which has not been final machined. I personally believe that our first choice should be to correct the design in a way that eliminates the possibility of O-ring clearance. Since this is a very critical SRM issue, it is requested that the assignment results be compiled in such a manner as to permit review at the S&E director's level, as well as project manager. End quote. After seeing the data from the September 1977 hydroburst test, Marshall engineer Leon Ray submitted a report entitled Solid Rocket Motor Joint Leakage Study, dated October 21, 1977. It characterizes no change in the thiacol design as unacceptable. Tang can move outboard and cause excessive joint clearance, resulting in seal leakage. Eccentric Tang-Clevis interface can cause O-ring extrusion when case is pressurized. End quote. Ray recommended a redesign of the Tang and reduced tolerance on the clevis as the best option for a long-term fix. After Ray's 1977 report, John Q. Miller, chief of the solid rocket motor branch at Marshall, signed and sent a memorandum on January 9, 1978, to his superior, Glenn Udy, describing the problems evident in the solid rocket motor joint seal. Quote, "We see no valid reason for not designing to accepted standards," end quote, the memo said, and it emphasized that proper sealing of the joint by use of shims to create necessary O-ring pressure was, quote, "mandatory to prevent hot gas leaks and resulting catastrophic failure," end quote. 1 year later, not having received a response to his 1978 memo, Miller signed and forwarded a second memo strenuously objecting to Thiacol's solid rocket motor joint seal design. This memo, dated January 19, 1979, opened with, "We find the Thiacol position regarding design adequacy of the clevis joint to be completely unacceptable." The memorandum made 3 principal objections to Thiacol's joint design. The first was the large sealing surface gap created by extensive Tang-Clevis relative movement. The memo said this movement, the so-called joint rotation, caused the primary O-ring to extrude into the gap, forcing the seal to function in a way that violates industry and government O-ring application practices. Moreover, joint rotation allowed the secondary O-ring to become completely disengaged from its sealing surface on the Tang. Finally, the memorandum noted that although Thiacol's contract required all high-pressure case seals to be verified, the clevis joint secondary O-ring seal had been verified by tests to be unsatisfactory. A copy of the second memorandum was sent to George Hardy, then Solid Rocket Booster project manager at Marshall. Thiacol apparently did not receive copies of either Miller memorandum, and no reply from Udy to Miller has been found. The Commission has learned that Leon Ray actually authored the Miller memos to Udy, although Miller signed them and concurred in the objections raised. During February 1979, Ray also reported on a visit he made to 2 O-ring manufacturers, the Precision Rubber Products Corporation at Lebanon, Tennessee, and the Parker Seal Company at Lexington, Kentucky. Udy accompanied Ray on the Precision visit. The purpose of the trips was to give the manufacturers the data on the O-ring experiences at Thiacol, and to, quote, "seek opinions regarding potential risks involved," Ray wrote in a February 9, 1979 memo describing the visit. Officials at Precision did voice concern for the design, stating that the solid rocket motor O-ring extrusion gap was larger than that covered by their experience, Ray reported. Their first thought was that the O-ring was being asked to perform beyond its intended design, and that a different type of seal should be considered, Ray added. During the Commission hearing on May 2, 1986, Ray was asked why the 1978 and 1979 memoranda were written. Mr. Ray: "The reason they were written was as a result of test data that we had, and I have to go back to, I guess, a little bit further back in time than these memos. When the joint was first designed, the analysis produced by Thiacol says the joint would close. The extrusion gap would actually close. We had quite a debate about that until we did a test on the first couple of segments that we received from the manufacturer, which in fact showed that the joint did open. Later on, we did some tests with the structural test article, and this is mentioned in the memo as STA-1, structural test article. At that time, we really nailed it down. We got some very accurate numbers on the joint rotation, and we know for a fact that during these tests that just what the memo says, the joint rotated. The primary O-ring was extruded up into the joint. The secondary O-ring did in fact detach from the seat. No records show Thiokol was informed of the visits, and the O-ring design was not changed. Thiokol's Phase 1 certification review on March 23, 1979 mentioned leak check failures and forces during case joint assembly that resulted in clevis O-ring grooves not conforming with tang sealing surfaces. However, this was not listed as a problem or a failure. Verification and Certification Committee. While Ray was warning of problems with joint rotation, static motor tests in July 1978 and April 1980 again were demonstrating that inner tang clevis relative movement was greater than originally predicted. Thiokol continued to question the validity of these joint rotation measurements and their effect on the availability of the secondary O-ring. In 1980, NASA empaneled a Space Shuttle Verification Certification Committee to study the flightworthiness of the entire shuttle system. A subdivision of that group, the Propulsion Committee, met with NASA Solid Rocket Motor Program personnel and raised several concerns about the joint design. The committee pointed out that the booster's leak test pressurized the primary O-ring in the wrong direction, so that the motor ignition would have to move the ring across its groove before it's sealed. The committee added that the effect of the insulation putty was not certain. Redundancy of the O-rings was also listed as a verification concern. The same report, however, said the committee understands from a telecon that the primary purpose of the second O-ring is to test the primary, and that redundancy is not a requirement. George Hardy testified that the committee's statement conflicted with his understanding. Quote, "The discussion there or the reference there to a telecon, and I don't know who that was with, that implies there was no intent for the joint to be redundant, is totally foreign to me. I don't know where they would have gotten that information because that was the design requirement for the joint." End quote. In May 1980, the Verification Certification Committee recommended that NASA conduct full-scale tests to verify the field joint integrity, including firing motors at a mean bulk propellant temperature range of 40 to 90 degrees Fahrenheit. The panel also asked NASA to, quote, perform case burst test with one O-ring removed. During the burst test for final verification of the motor case safety factor, one of the two O-rings failed by extrusion and leaked. The analysis used for additional verification did not include further gap openings caused by joint deflection at pressurization or any deflections caused by bending loads. The panel considers the above to be inadequate to provide operational program reliability and marginal to provide adequate safety factor confidence on Shuttle Flight 1. End quote. The NASA program response to these issues was included in the final committee report in September 1980. It said that the original hydroburst tests and the lightweight case tests being conducted at the time satisfied the intent of the committee's recommendations. Moreover, the response stated, NASA specialists have reviewed the field joint design, updated with larger O-rings and thicker shims, and found the safety factors to be adequate for the current design. Reanalysis of the joint with larger O-rings and thicker shims is being accomplished as part of the lightweight case program. The joint has been sufficiently verified with the testing accomplished to date, joint lab tests, structural test article, and 7 static firings and the 2 case configuration burst tests, and currently scheduled for lightweight case program. End of section 12. Recording by jmichl, Sussex, Wisconsin, USA, February 2021.
Section 13 of Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Penny Witt, voiceoverwithp.com. Report to the President by the Presidential Commission on the Space Shuttle Challenger Accident. Chapter 6, An Accident Rooted in History, Part 2. Criticality, Classification, and Changes. The solid rocket motor certification was deemed satisfactory by the Propulsion Committee of the Verification Certification Group on September 15, 1980. Shortly thereafter, on November 24, 1980, the solid rocket booster joint was classified on the Solid Rocket Booster Critical Items List as Criticality Category 1R. NASA defines Criticality 1R as any subsystem of the shuttle that contains, quote, redundant hardware, total element failure of which could cause loss of life or vehicle, end quote. The use of R representing redundancy meant that NASA believed the secondary O-ring would pressurize and seal if the primary O-ring did not. Nonetheless, the 1980 Critical Items List, CIL, states, quote, redundancy of the secondary field joint seal cannot be verified after motor case pressure reaches approximately 40% of maximum expected operating pressure. It is known that joint rotation occurring at this pressure level with a resulting enlarged extrusion gap causes the secondary O-ring to lose compression as a seal. It is not known if the secondary O-ring would successfully reseal if the primary O-ring should fail after motor case pressure reaches or exceeds 40% of maximum expected operating pressure. End quote. When asked about the text of the 1980 Criticality 1R classification, Arnold Aldridge, NASA manager of the National Space Transportation System, said, quote, the way that language reads, I would call it Criticality 1, end quote. Notwithstanding this apparent contradiction in the classification 1R and the questionable status of the secondary described in the text of the CIL, the joint carried a 1R classification from November 1980 through the flight of the STS-5, November 1982. The Space Shuttle first flew on April 12 to 14, 1981. After the second flight, the STS-2, in November 1981, inspection revealed the first in-flight erosion of the primary O-ring. It occurred in the right solid rocket booster's aft field joint and was caused by hot motor gases. The damage to the ring proved to be the worst ever found on a primary O-ring in a field joint on any recovered solid rocket booster. Post-flight examination found an erosion depth of 0.053 inches on the primary O-ring. Nonetheless, the anomaly was not reported in the Level 1 Flight Readiness Review for STS-3, held on March 9, 1982. Furthermore, in 1982, the STS-2 O-ring erosion was not reported on the Marshall Problem Assessment System and given a tracking number, as were other flight anomalies. In mid-1982, two significant developments took place. Because Thiokol believed blowholes in the insulating putty were a cause of the erosion on STS-2, they began tests of the method of putty lay-up and the effect of the assembly of the rocket stages on the integrity of the putty. The manufacturer of the original putty, Fuller O'Brien, discontinued the product, and a new putty from the Randolph Products Company was tested and selected in May 1982. The new Randolph putty was eventually substituted for the old putty in the summer of 1983 for the STS-8 solid rocket motor flow. A second major event regarding the joint seal occurred in the summer of 1982. As noted before, in 1977 through 78, Leon Ray had concluded that joint rotation caused the loss of the secondary O-ring as a backup seal. Because of May 1982 high-pressure O-ring tests and the tests of the new lightweight motor case, Marshall Management finally accepted the conclusion that the secondary O-ring was no longer functional after the joints rotated when the solid rocket motor reached 40% of its maximum expected operating pressure. It obviously followed that the dual O-rings were not a completely redundant system, so the criticality 1R had to be changed to criticality 1. This was done at Marshall on December 17, 1982. The revised critical items list read, see pages 157 and 158, quote, Criticality Category 1. Failure mode and causes. Leakage at case assembly joints due to redundant O-ring seal failures or primary seal and leak check port O-ring failure. Note leakage of the primary O-ring seal is classified as a single failure point due to possibility of loss of sealing at the secondary O-ring because of joint rotation after motor pressurization. Failure effects summary. Actual loss of mission, vehicle, and crew due to metal erosion, burn through, and probable case burst resulting in fire and deflagration. Rationale for retention. The solid rocket motor case joint design is common in the lightweight and regular weight cases having identical dimensions. The joint concept is basically the same as the single O-ring joint successfully employed in the Titan III solid rocket motor. On the Shuttle solid rocket motor, the secondary O-ring was designed to provide redundancy and to permit a leak check, ensuring proper installation of the O-rings. Full redundancy exists at the moment of initial pressurization. However, test data shows that a phenomenon called joint rotation occurs as the pressure rises, opening up the O-ring extrusion gap and permitting the energized ring to protrude into the gap. This condition has been shown by tests to be well within the required for safety primary O-ring sealing. This gap may, however, in some cases increase sufficiently to cause the unenergized secondary O-ring to lose compression, raising question as to its ability to energize and seal if called upon to do so by primary seal failure. Since under this latter condition only the single O-ring is sealing, a rationale for retention is provided for the simplex mode where only one O-ring is acting. End quote, emphasis added. The retention rationale for the simplex or single O-ring seal was written on December 1, 1982 by Howard McIntosh, a Thiokol engineer. This document gave the justification for flight with the single functional O-ring. It reported that tests showed the Thiokol design should be retained, citing that the Titan history the leak and the hydroburst tests and static motor firings as justification. However, it is also contained in the following rationale, which appeared to conflict with the criticality 1 classification, that the secondary O-ring was not redundant. Quote, initial information generated in the lightweight cylinder-to-cylinder proof test shows a total movement of only 0.030 inch at pounds per square inch, gauge pressure in the center joint. This indicates that the tang-to-cleaves movement will not unseat the secondary O-ring at operating pressures. End quote. Testimony in hearings and statements given in commission interviews support the view that NASA management and Thiokol still considered the joint to be a redundant seal even after the change from criticality 1R to 1. For example, McIntosh's interview states, question, after the criticality 1 classification, what did you think it would take to make the joint seal 1R? Mr. McIntosh, I thought it was already 1R. I thought that after those tests that would have been enough to do it. Question, well, you know it was 1, but you were hoping for 1R? Mr. McIntosh, yeah, I was hoping for 1R, and I thought this test data would do it, but it didn't. At the time, in 1982-83, the redundancy of the secondary O-ring was analyzed in terms of joint or hardware geometry, with no consideration being given to the resiliency of the ring as affected by temperatures. Moreover, Marshall engineers like Ray and Miller disagreed with Thiokol's calculations on the measurement of the joint opening. That engineering debate eventually went to a referee for testing, which was not concluded until after the 5-1-L accident. Notwithstanding the view of some of Marshall engineers that the secondary ring was not redundant, even at the time of the criticality revision, Marshall Solid Rocket Motor Program Management appeared to believe the seal was redundant in all but exceptional cases. Dr. Judson Lovingood told the commission, quote, there are 2 conditions you have to have before you don't have redundancy. One of them is what I call a spatial condition, which says that the dimensional tolerances have to be such that you get a bad stack-up. You don't have proper squeeze, etc. on the O-ring so that when you get joint rotation, you will lift the metal surfaces off the O-ring. All right, that's the one condition, and that is the worst case condition involving dimensional tolerances. The other condition is a temporal condition, which says that you have to be past a point of joint rotation, and of course that relates back to what I just said. So first of all, if you don't have this bad stack-up, then you don't have full redundancy. Now secondly, if you do have the bad stack-up, you had redundancy during the ignition transient up to the 170 millisecond point, whatever it is, but that is the way I understand the critical items list. End quote. George Hardy and Lawrence Mulroy shared Lovingood's view that the secondary seal was redundant in all but situations of worst-case tolerances. However, there is no mention of this caveat in the critical items list itself, nor does it appear in the subsequent waiver of the criticality 1 status granted by NASA levels 1 and 2 in March 1983. This waiver was approved to avoid the obligations imposed on the Shuttle program by paragraph 2.8 of the Space Shuttle Program Requirements Document, Level 1, dated June 30th, 1977. That paragraph states, quote, the redundancy requirements for all flight vehicle subsystems, except primary structure, thermal protection system, and pressure vessels, shall be established on an individual subsystems basis, but shall not be less than fail-safe. Fail-safe is defined as the ability to sustain a failure and retain the capability to successfully terminate the mission. Redundant systems shall be designed so that their operational status can be verified during ground turn around and to the maximum extent possible while in flight." End quote. Glenn Looney, the former manager of the STS program, Level 2 at JSC, described the Criticality 1 change and resulting waiver to the Commission on May 2nd. Quote, Mr. Looney: "Well, the approval of the waiver in March of '83, at the time I was involved in that. I was operating on the assumption that there really would be redundancy most of the time, except when the secondary O-ring had a set of dimensional tolerances add up, and in that extreme case there would not be a secondary seal. So I was dealing with what I thought was a case where there were two seals, unless the dimensional tolerances were such that there might only be one seal in certain cases." Chairman Rogers: "Now, to me, if you will excuse the expression, that sounds almost contradictory, what you just said. What you first said was that you came to the conclusion that you could only rely on the primary seal, and therefore you removed the R." Mr. Looney: "Yes, sir." Chairman Rogers: "And now you're saying, if I understand it, that experience showed that there was redundancy after all." Mr. Looney: "No, I don't know of any experience showing that. What I'm saying is that the removal of the R is an indicator that under all circumstances we did not have redundancy. There were a certain number of cases under which we would not have redundancy of the secondary O-ring. Recognizing that even though there were a lot of cases where we expected would have redundancy, we changed the criticality designation." Chairman Rogers: "It was saying to everybody else you can't necessarily rely on the primary seal, and if the primary seal fails, as you have said here, there may be loss of vehicle, mission, and crew." Mr. Looney: "I would adjust that to only say you cannot rely on the secondary O-ring, but we would expect the primary O-ring to always be there." The criticality waiver was processed outside the formal NASA program requirements control board. However, representatives of that group signed off on the document. It was forwarded to Level 1 and approved by Associate Administrator for Spaceflight Technical L. Michael Weeks on March 28, 1983. Weeks told the Commission he signed the waiver because of the certification verification review of the Propulsion Committee in 1980. Weeks explained, quote, "We felt at the time, all of the people in the program, I think, felt that this solid rocket motor in particular, or the solid rocket booster, was probably one of the least worrisome things we had in the program." End quote. The waiver was signed less than 1 week prior to the launch of STS-6 on April 4th. According to interviews of Arnold Aldrich and of Richard Kors, the latter having been involved with the waiver review at Johnson Level 2, the waiver was approved so that STS-6 could fly. However, Weeks denied any connection between the Level 1 waiver approval and the flight of the STS-6. Although some Thiokol engineers and officials claimed that they had no notice of the criticality change and waiver in December 1982 and in March 1983 from the approval signatures, including Thiokol's operation manager at Marshall, Maurice Parker. and the distribution of the criticality and waiver documents, apparently Thiokol officials were sent copies and were involved in the criticality reclassification. Nonetheless, the Commission has also determined that several documents tracking the O-ring erosion at Thiokol and Marshall referred to the solid rocket motor field joint seal as criticality 1R long after the status was changed to criticality 1. STS-41-B O-ring erosion. As Figure 2 shows, prior to STS-41-B, the O-ring erosion blow-by problem was infrequent, occurring on a field joint of STS-2, November 1981, nozzles of STS-6, April 1983, and a nozzle of QM-4, March 1983, a qualification test motor fired by Thiokol. However, when STS-41-B flew on February 3, 1984, the left solid rocket booster forward field joint and the right nozzle joint primary O-rings both suffered erosion damage. Thiokol engineers reacted to this discovery by filing a problem report on the O-ring erosion found on STS-41-B. Thiokol presented a series of charts to the Marshall Solid Rocket Booster Engineering Office about the 41-B O-ring erosion. Thiokol told Marshall that recent joint rotation measurements in test indicated the secondary O-ring will not unseat, providing confidence that the secondary was an adequate backup. Keith Coates described his view about Thiokol's data in a February 29, 1984 memorandum to George Hardy. Quote, "We have two problems with their rationale. The effect of the 0.065-inch erosion on the O-ring sealing capability is not addressed. We have asked Thiokol to provide their data to justify their confidence in the degraded O-ring. The second concern is the amount of joint rotation. L. Ray does not agree with Thiokol's numbers, and he has action to discuss his concern with R. Boisjoulet, Thiokol, and to reach agreement. Thiokol definition of their plans on resolution of the problem is very weak." End quote. The erosion problem was identified and tracked by the Marshall Problem Assessment System as Marshall Record A07934 and by Thiokol as Thiokol Contractor Record DR4-5/30. Slight char condition in primary O-ring seal in forward field joint on SRM A57 of STS-11 Flight Mission 41B. The Marshall Problem Assessment System report states, quote, "Remedial action none required. Problem occurred during flight. The primary O-ring seal in the forward field joint exhibited a charred area approximately 1 inch long, 0.03 to 0.050 inches deep, and 0.100 inches wide. This was discovered during the post-flight segment disassembly at KSC." End quote. A March 8, 1984 entry on the same report continues, quote, "Possibility exists for some O-ring erosion on future flights. Analysis indicates maximum erosion possible is 0.90 inches according to flight readiness review findings for STS-13. Laboratory tests shows sealing integrity at 3,000 psi using an O-ring with simulated erosion depth of 0.095 inches. Therefore, this is not a constraint to future launches." End quote. This last entry is also a summary of the briefing given by Thiokol to Lawrence Malloy about the 41-B erosion at the Level 3 Flight Readiness Review for STS-41-C, held at Marshall on March 8, 1984. At that same briefing, the chief engineer for United Space Boosters, George Moorfield, raised prior Titan experience with O-ring problems. He explained in a memorandum to Malloy the following day, quote, "I alluded to the Titan III SRM history, which is quite similar to the current STS solid rocket motor experience. Post-fire inspection of the Titan solid rocket motor static test motors showed that pressurization of the single O-rings in the pressure vessel routinely occurred via a single breakdown path across the joint putty. There was also evidence that some O-rings never see pressure in the Titan motor. The segment-to-segment case insulation design results in a compression but joint which apparently is often sufficient to withstand PC. Your review showed that there was sufficient margin of O-ring remaining to do the job. I'm sure you have considered that if it does burn through, the secondary O-ring will then be similarly pressurized through a single port, so some concern remains. I recommended that you set up a panel to study the use of putty and consider some alternatives. 1. Is putty needed at all? 2. If the tradition can't be broken, can the putty be applied with multiple 6 or 8 pressurization paths built in? I think that the primary seal should be allowed to work in its classical design mode. Both the Titan and the STS solid rocket motors have been designed for this not to happen. Titan has flown over 1,000 pressure joints with no failure. My opinion is that the potential for failure for the joint is higher for the STS solid rocket motor, especially when occasionally the secondary seal may not be totally effective." End quote. When the 41B erosion was taken to the Level 1 Flight Readiness Review for 41C on March 30th, 1984, it was briefed as a technical issue. A recommendation to fly 41C was approved by Level 1, accepting the possibility of some O-ring erosion due to the hot gas impingement. The rationale for acceptance was the same as that given at the Level 3 Flight Readiness Review and entered into the Marshall Problem Assessment Report. An outgrowth of this review was an April 5, 1984 directive from NASA Deputy Administrator Dr. Hans Mark to Lawrence Malloy at Marshall. This programmatic action item was signed by Weeks and asked Malloy to conduct a formal review of the solid rocket motor case-to-case and case-to-nozzle joint sealing procedures to ensure satisfactory, consistent closeouts. This action item had been preceded by a letter written from NASA Associate Administrator for Space Flight General Abramson to Marshall Center Director Lucas. The letter, sent January 18, 1984, requested that Marshall develop a plan of action to make improvement in NASA's ability to design, manufacture, and fly solid rocket motors. Abramson pointed out that NASA was flying motors where basic design and test results were not well understood. The letter addressed the overall general solid rocket motor design, but did not specifically mention O-ring erosion. After Malloy received the April 5, 1984 STS-41-C action item on the O-rings, he had Lawrence Ware forward a letter to Thiokol, which asked for a formal review of the booster field joint and nozzle joint sealing procedures. Thiokol was to identify the cause of the erosion, determine whether it was acceptable, define necessary changes, and reevaluate the putty then in use. The Ware letter also requested small motor tests reflecting joint dynamics as well as analysis of booster assembly process. Thiokol replied to the Marshall STS-41C action item on May 4, 1984, with a program plan entitled Protection of SRM Primary Motor Seals. The plan was prepared by Brian Russell, then Thiokol's Manager of Systems Engineering. It outlined a systemic problem to isolate the O-ring erosion and charring problem and to eliminate damage to the joint seals. Proposed areas of the inquiry included the leak check pressures, assembly loads, case eccentricity, and putty layup. The Thiokol response in May 1984 was merely a proposal. The actual final response to the directive from Marshall was not completed until August 19, 1985, briefing on the solid rocket motor seal held at NASA headquarters some 15 months later. End of section 13. Recording by Penny Witt. Voiceover with P.com.